Good morning.
Good morning.
This is like herding cats. There we go. Faculty. Okay, welcome. We're going to start with 15 minutes of just the quick introductions. Anna, do you want to go first?
Hi, Anna Russo, Harvard.
Wolfram Schlenker, Kennedy School.
Ryan Kellogg, Chicago.
Lynn Barrage, ETH Zurich.
Alan Shaw, Stanford.
Juliana Asunción, Catholic University of Rio.
Hernández Cortés, Arizona State.
Mathias Abitbol.
Arik Levinson, Georgetown.
Charles Taylor, Harvard.
Elsa Severnini, Boston College.
Matt Cochrane, Yale. Steve Sakala, University of Zurich and Tufts.
Jing Li, Tufts University.
Bob Dyke, MIT.
Maureen Cropper, University of Maryland.
Janet Curry, Yale.
Corbett Granger, Wisconsin.
Ben Collier, Wisconsin.
Michael Hanneman, Arizona State and Berkeley.
Alan Hong from University of Pittsburgh.
Jim Stock, Harvard.
Joe Shapiro, Berkeley.
David Molitor, Illinois.
Sarah Armitage, Boston University.
Koichiro Ito, Chicago.
Jim Salee, Berkeley.
Aaron Mansur, Dartmouth.
Judd Boomhauer, UC San Diego.
Rob Williams, Maryland.
Gazi Kabash, Tilburg.
Karthik Shastri, Princeton. Sebastian Tebbe, Melbourne.
Hannah Druckenmiller, Caltech.
Constanza William, Johns Hopkins.
Jonathan Elliott, Johns Hopkins.
Shifra Arendine, Berkeley.
Wen Wang, Hong Kong University of Science and Technology.
Ignacio Bañares, between LSE and Berkeley.
Molly Lipscomb, UVA.
Robin Meeks, Duke.
Louis Prionis, Maryland.
Yichun Fan, Duke.
Pari Sastry, Wharton.
Billy Ferguson, Berkeley. Evan Michelson, Alfred P. Sloan Foundation.
Cody Nahiba, EPA.
William Tan, Claremont McKenna College.
Nathaniel Hickok, MIT.
Aaron Berman, MIT.
Sarah Beres-Tiki, Columbia.
Jacob Moscona, MIT.
Ben Olkin, MIT.
Jay Shimshak, Virginia.
Kelly Bishop, Arizona State.
Nicholas Frigdenhuh, Arizona State.
Paul Simpson, LSE.
David Demus, University of Zurich.
Meredith Fowley, UC Berkeley.
Paulina Oliva, USC.
Jacqueline Plus, Toronto.
Ishan Nath, Harvard Kennedy School. Ashley Langer, University of Arizona.
Ulrich Wagner, Mannheim.
Claire Balboni, LSE.
Sheila Olmsted, Cornell.
Wayne Gray, Clark University.
Cage Sims, Amherst College.
Farid Farouki, Boston College.
Benjamin Langereau, INSEAD, Collège de France.
Keisuke Ito, Chicago.
Eric Richard, Chicago.
Steve Puller, Texas A&M.
Abby Ostreicher, Boston University.
Akram Balker, UC Berkeley.
Mike Wallach, Stanford.
Nicolas Astier, Paris School of Economics.
Rob McMillan, University of Toronto.
Mira Mahadevan, UC San Diego.
Eyal Frank, Chicago.
Laura Backinson, Oregon.
Nick Sanders, Cornell.
Ivan Root at Cornell.
I think that's everybody. Great. So we are going to kick things off. As a reminder on format, we're going to do 25 minutes for each presentation without interruptions, 10 minutes for the discussant, and then we will open it up to Q&A. For the Q&A portion, we have two standing mics, one at each corner. So if you want to ask a question, again, questions have question marks at the end of them, line up at behind each microphone, and then we'll probably sort of take them in batches and sort of take that how it goes. Welcome, everybody. It's great to have everybody here. Just like one more thought from the organizers. We had something approximately 250 submissions for this meeting, which is just a great signal of how much amazing work is being done in this space. So we are happy to have Karthik kick it off. Tell us about climate change, deforestation, and the expansion of the global agricultural frontier.
Wonderful. Thanks so much for the introduction. I'm very excited to present this new work, which is joint with Alan, Jacob, and Ben, who are kind of spread across the room. Okay. Planetary warming is here, and it's affecting global agricultural productivity. But what happens next? That is, what decisions do farmers make in response to this, and how does that affect the environment? I think it's helpful to frame this debate by introducing two kind of contrasting and extreme views about how this process is going to play out. I'll call one the, quote, reallocation view. And it's going to say that, well, places respecialize with respect to comparative advantage. So if parts of the world become lower productivity for agriculture, they're going to move towards doing less farming. And potentially a first order consequence of this in terms of the environment is to slow down the recent acceleration in deforestation, especially in tropical latitudes. And it's estimated, for example, that 90% of deforestation is due to cropland expansion. On the other hand, there is a big tradition in economics that emphasizes essentially the opposite phenomenon, that when farmers become unproductive, they double down and move to more resource-intensive and land-intensive agricultural strategies. So this is something we're familiar with even from Theodore Schultz's old work on the food problem, the entrenchment of agriculture in low-income, low-productivity countries. It's quite related to Norman Borlaug's famous hypothesis that low productivity is a principal driver of deforestation, especially in the tropics. And if you take this view, well, climate change is kind of an additional weight on top of that could accelerate deforestation, especially in these areas that are most critical in terms of carbon and biodiversity. So in short, what is this paper? It's about, well, we want to know which of these two views, or where in the middle, better describes what's happening in the world right now as the climate continues to change and agricultural productivity continues to change, and why? What are the economic mechanisms that underpin this? I'm not going to bury the lead. What we're going to find is global evidence that entrenchment is winning out. And how are we going to do this? In terms of measurement, we're going to use global data on deforestation and extreme temperature exposure since 2001. And the latter is going to capture what we know to be the facet of climate change that's most affecting agricultural productivity globally. Our main headline result is going to be that when we look at the entire world split into 1 degree grid cells, extreme heat is leading to more deforestation. These effects build up over time. They're concentrated in the tropics, both in terms of where the temperature incidence is and where the marginal effects seem to be highest. They're accompanied by fire setting, which we can measure directly, and the environmental consequences thereof directly. And they're not counteracted by equilibrium effects or leakage, where deforestation is happening here, but it's being saved elsewhere in the world. Why is this happening? We're going to find a slew of pieces of evidence that are consistent with the Borlaug hypothesis that agricultural economies on what we call the global agricultural frontier are somewhat isolated, and there are large price effects that give farmers incentives to deforest. We're going to find that effects are driven by places that grow heat-sensitive crops and where price elasticities of demand are estimated to be low. Quantitatively, we measure substantial cropland expansion, and that's enough to account for all the deforestation that we've measured. And then finally, we can use on the ground data in Brazil from agricultural censuses to show direct evidence of the mechanism that we have in mind, where there are lower yields offset by price increases that potentially give incentives for additional deforestation. How much is this in sample? It's going to explain about 1.4 million hectares of lost forest since 2005, almost all of which is in the tropics. And if you plug in projections for temperature change until 2100, these numbers are going to amplify substantially and be quite comparable to the total in-sample deforestation and tropical deforestation that we've actually seen since about 2000. Very briefly on the subject of the literature, there is a lot of work on the economics of deforestation and various economic drivers. One thing I want to emphasize about our paper is that we show that perhaps for worse in terms of the world, that there's really a two-way feedback loop here, where environmental change also drives deforestation and incentives for deforestation, which potentially feeds back into the same global challenges. And second, there is a lot of work on spatial reallocation and resource use in agriculture. And I just want to mention that our results definitely pose a challenge for views of the world positively and normatively that suggest that there's great potential or a great likelihood that reallocation across space can mitigate climate damages, as what we see on the ground is a lot of entrenchment of existing modes of production. Okay. And to give an outline of the talk, I'm going to start with a simple model to organize thoughts, and then get into the data and main results, and then finish by rounding out the quantification. Okay. So to set the scene a bit for the analysis, I want to present a simple model, and this is not a bluff. This model is simple enough that I think I will successfully show you all of it in the next 60 seconds or so. And it's meant to just emphasize that it's theoretically ambiguous whether productivity shocks increase or decrease incentives for deforestation because of counteracting effects of productivity, costs, and prices. So to be more specific, we're just going to think about the world as consisting of a bunch of different locations indexed by I, in which there are farmers who are making a decision of how much land to use, which I've denoted by X sub I. On a benefit side, there is constant returns to scale production. So A times X is the amount of food that you get out of the ground, and you can sell that or you value that at a price P. There's cost to clearing land, and that's just going to be reflected by this simple quadratic function C over 2 times X squared. Agricultural prices are determined in equilibrium, and we're going to keep this flexible for now, where this big P is a function that's going to take in the amount of food produced everywhere in the world, and it's going to spit out the price in any location I. And we just want to maintain this flexibility for now to take into account the fact that perhaps some parts of the world are very integrated. They're operating at a world price that depends on the food grown everywhere. Some parts could be very isolated. It could just depend on the amount of food produced in a particular region I. And as suggested, we're going to think about what happens in equilibrium as farmers choose how much land to use, taking P as given, with A and C, these forcing variables that they're going to take as given and could be shifted by patterns of the weather. So this model is described basically by one first order condition, right? Where P times A is the marginal product of land, and C times X is the marginal cost of clearing it. So essentially, how much land do you clear? It's P times A divided by C. And just rearranging that, you can see that there's three forces that are going to determine your incentive to clear land. And you know, in the context we're going to study, a lot of this is just practically speaking going to be done by deforesting. And let me go over those three effects in turn. The first is productivity. So holding fixed costs and prices. If you're more productive, you want to use more land. If you're less productive, you want to use less land. And that's quite intuitive. On the other hand, we have these price effects where if prices go up, and that could be accompanied by scarcity of food or lower physical productivity, one wants to use more land. And this distinction between productivity and price effects is really, in terms of the literature, where a lot of the distinction between the reallocation and the entrenchment view is going to come in. If we were in a global market and my little price shock had no dent on international prices, there's no such thing as a local price effect. It's all about productivity. On the other hand, at the opposite extreme, say everywhere was an isolated economy with inelastic demand for agricultural products. It's the food we need to eat within our little location I. Then it has to be the case if I'm less productive, I have to use more resources. There's simply no other way to feed myself. And that's tantamount to saying the price effect is big enough to exactly offset what's happening with productivity and costs. And finally, we want to keep in mind there is potentially this direct cost effect. Weather can affect the cost of clearing land, and that could directly matter on top of everything that I've mentioned so far. Finally, what about the rest of the world if I were to look beyond these individual locations I? Well, this simple model suggests that we should look at product markets as the main place where equilibrium adjustment could happen. And moreover, it actually has a prediction about what sign that is. If there's food shortages in one region of the world, we might expect that to weakly increase prices elsewhere in the world and put a weakly positive pressure on land clearing and deforestation elsewhere. So summing up, what the simple model tells us is that there are kind of two possible configurations of the world that are embodied by the two views that I described earlier. There's the reallocation view, which is really emphasizing these productivity effects. There is this entrenchment view, which is instead emphasizing price and cost effects. And that's going to sort of set up the ambiguity that motivates our empirical analysis. In the paper, we also talk about dynamics. And the main thing I want to emphasize here is that if you were to incorporate dynamics into all of this, you might expect responses to occur over time and with a delay. And that's something that we're going to investigate directly. So let me now kind of dive into that, starting with a brief description of the data. Our main global data on deforestation is going to come from this global forest change data set of Hansen et al. The way that this data set works, and many of you might be familiar with it, is it reports two key quantities: forest cover in a base year, which they're going to estimate is 2000. So here's a picture of the northern part of South America and the Amazon in terms of this forest cover. And at the level of individual pixels in the world, lost years of forest cover. So in what year was that forest deforested? You're going to see this variable a lot, deforestation sub IT. So we're going to do analysis primarily at the level of 1 degree grid cells of the world. You'll see a picture in a second, but those are 111 kilometers at the equator. And deforestation IT is in units of what percent of the total area of that grid cell was deforested as a flow within that year. And you can calculate that by aggregating over pixels in the way described here. I will not, in the short talk, really walk you through the robustness checks of every result, but the primary alternative data set we can use is a more standard land cover data set, like that reported by the ESA as part of their Copernicus program. We get very similar results there, and we think that's handy because they're using different satellite measures and also treating and measuring afforestation a little bit differently. Okay. So the second ingredient is going to be, I've alluded to a little bit generally that this is happening at the agricultural frontier, at the edge of the forest. So what is that? We think, first of all, that's where our hypothesis lives. We're interested in the places where marginally available land is what's currently forested. So to do this, we're going to generalize a concept that people have used to study deforestation in the Amazon, which is this notion of an arc of deforestation on the edge of the forest. Practically speaking, we'll do this as follows. Using the Hansen data, we'll say that grid cells of the world are the forest if they have more than 50% tree canopy cover by area. And the arc of deforestation is going to be the part of the forest that's on the edge, meaning it's within 2 grid cells of the boundary of the forest. So here's a picture to kind of immediately give you a sense of what that looks like. Everything that is blue is the forest by our definition. And what is dark blue is the arc of deforestation. And where forests are deep enough, for example, in the Amazon, in Siberia, in the Congo, for example, there is this light blue, which we're going to refer to a bit as the deep forest throughout the presentation. Now, throughout the paper, we want to do a lot to make sure that our results are not driven by just one particular definition of the sample here. I will show you a lot of results as we go about how effects are different in and out of the arc of deforestation. We also try many ways of defining it differently, including changing the threshold of what is the forest, whether we take the arc as static or dynamic, and if we sort of change any of the tuning parameters that define exactly what the arc is. And then finally, temperature and productivity shocks. So our basic data set is going to be the ERA5 land reanalysis data set of local temperature realizations. And we're going to calculate killing degree days as exposure to temperatures above 32 degrees Celsius. So a motivation for this is based on prior work, which shows that it's a primary channel through which temperature change affects agricultural productivity. At our global scale, the direct validation we can do is we can show that this affects NDVI and NDVI in cropland squares of the world in a way that seems very precisely measured, and it lines up with the timing of how we measure it in our data set. Okay, so let me now get to the main results. So our regression model for kind of the first graph I'm going to show you is the following: distributed lag regression, where deforestation IT, that flow variable of deforestation at the grid cell level, is on the left-hand side. The data set is a 1 degree by 1 degree grid cell by year panel. And on the right-hand side, we have this distributed lag of first differences in killing degree days. So you can think of this as if the model you have in the back of your head is land use depends on productivity, this is changes in land use, i.e. deforestation, depending on changes in the variable that affects productivity. We're always going to run things with grid cell fixed effects. And because it's in differences, those really embody differential trends in different parts of the world, which we think is important for ruling out spurious correlation. Everything is going to have year fixed effects. So we'll use purely cross-sectional variation. And our preferred specification throughout will have country by year fixed effects in light of the fact that we know there are a lot of national level, for example, policy variables that affect rates of deforestation. And everything I'll show you will have standard errors clustered at the level of GID1 units, a little bit within the lingo. Those are states within countries. Okay. So the first result, extreme heat induces deforestation. So both of these panels show the coefficients from the distributed lag regression that I described, and focus for a minute, or at least to start with, on the darker estimates, which are those within the arc of deforestation. So what we see is that changes in killing degree days lead to additional deforestation. And moreover, this effect is persistent. It lasts for a few years. And it's not reversed. So there's no evidence that, for example, a change in deforestation just leads to retiming of deforestation. And that result looks very similar quantitatively and qualitatively with the cell by year fixed effects, as well as the cell and country year fixed effects on the right-hand side. Next, the light blue estimates show you what happened if you estimate the same thing outside of the forest by our definition. And there we see close to no effect. And we think that's consistent with the idea that it's really within the arc where deforesting is where there's marginal land is really coming from clearing the forest. This is the same result in tabular form, showing you the sum of coefficients, which we think is kind of the right thing to look at to estimate the effects of cumulative persistent warming in the world. The only thing I will add based on this is something I alluded to earlier. If you compare columns 3 and 4, where we split by whether you're in the tropics, that's just based on whether you're within the Tropic of Cancer and Capricorn, the marginal effects are much bigger. Another way of looking at dynamics, instead of looking at the distributed lag, is to do this at a lower frequency. So what this bar graph shows you is estimates from a long difference, or a stacked long difference, where we use the 2000s and 2010s as 2 different decades. Again, we see big effects in the arc, no effects outside. And the magnitudes are very similar to the sum of coefficients, suggesting that gave a good account for how effects build up over time. Now, to give some confidence in this result, we want to look at some different outcomes. One of interest is fire setting, both because of its direct environmental consequences and because it can be measured in effectively a rather different way. So to do this, we're going to run our distributed lag regression, where the outcome is going to be the share of area burned within a particular year in each of our grid cells. And the econometric specification is exactly the same as I described earlier. And what we're going to find in the arc, which is again the dark blue estimates here, is a persistent effect that jumps up right in the year where the event is happening. And moreover, it's one that accounts for about 1/3 of the deforestation effects that we saw earlier, as well as an economically significant amount of carbon emissions as measured on the right. Interestingly, if we were to look in the deep forest, we're not seeing very big effects there. And we think that's consistent with the fact that these aren't incidental fires, that they're probably intentional ones that are for agricultural expansion. In the paper, we talk a bit more kind of on that spirit of how can we rule out kind of other more mechanical relationships that could exist between deforestation and temperature change. Incidental forest loss, we think there is a lot of anecdotal as well as direct evidence against. Reverse causality is one that you have in mind. But simply, I think the temperature changes are too big to be explained by reverse causality. But we can also directly calculate downwind exposure to deforestation, which is kind of known to be a proxy for indirect effects into temperature. And that doesn't seem to have any effects. And finally, I talked briefly about international spillovers. And in terms of the economic argument, it's possible there's additional deforestation hiding in places that are indirectly affected. So to account for this, we're going to calculate exposure to extreme temperatures based on the crops that are grown according to a cross-section as measured by the ERTStat database in 2000. So this KDD spillover measure is basically picking up if there's extreme temperature exposure in, say, soybean growing areas of Brazil, there's this indirect exposure where they're growing soybeans in the United States or China, for example. What we find quite across the board is that spillover effects seem very small. We can't rule out that they're zero, and therefore they add kind of a negligible amount to the total. And that's going to be consistent with the idea and the economic story where these forces are very, very localized. Okay, so let me now talk about mechanisms. We're in Borlaug's world, or what we call the, quote, entrenchment case. And the story that I gave you briefly in the model is driven by agricultural productivity, and it has price changes as the intermediate variable, as well as potentially this cost of clearing. So what we're now going to do is try to find direct evidence of each step of the story by looking at heterogeneity of our effects in different parts of the world to sort of build up to the economic mechanism that I described earlier. And these analyses, I'll try and go a little bit through briefly. So the first, it starts with agricultural productivity. So a prediction here is we can split the world into places where the same temperature change affects productivity more or less. This whole pathway should be amplified where the productivity effect is predicted to be more. The way that we do that is using information on what's grown in these different grid cells, as well as the temperature tolerance of different crops based on these outside expert estimates that we've used in other work that's related to this one. So basically, we can calculate a grid cell-based measure of are you growing more or less temperature-tolerant crops? And we can split the world based on who's growing these low-tolerance crops versus these high-tolerance crops. And a prediction is that the marginal effect of this whole pathway from extreme heat to deforestation is higher if you're growing the low-tolerance crops. And that's exactly what we find splitting the arc of deforestation sample by those growing the low tolerance crops, which are the dark blue here, versus the high tolerance crops, which are the light blue. Second, we want to know if this is driven by the price effects that we've hypothesized. Now, there's ideal data that we don't really have, which is grid cell level data on agricultural prices from which we could estimate our own elasticities of demand and proceed as follows. At the world level, we don't have that. So we're going to do what we think is the next best thing, which is to take the best estimates that we know of from this USDA commodity and food elasticities data set, which is going to aggregate across 77 studies in 117 countries. Again, use information on what's being grown in different grid cells in the world and calculate this sort of shift share measure of elasticity based on what you grow and how elastic is demand for that product in the country that you're in. And again, we're going to split the world based on low and high elasticity and show you a figure kind of much like the one that I showed you earlier. And what we're going to find here is that it's really in the low demand elasticity parts of the world where the effect is magnified, although there still is evidence of an effect in the high demand elasticity parts of the world. And finally, what about cropland expansion? You might reasonably ask, well, why didn't we start here? Primarily a measurement thing, although we know 90% of deforestation results from agricultural expansion, according to best estimates from the FAO, precisely measuring cropland expansion across space and across time, which is the game that we're playing, is kind of known to be difficult just for pure remote sensing reasons. Nonetheless, what we're going to do is we're going to use land cover data from the ESA, and we're going to calculate in the same units as earlier this cropland expansion variable. So this is, again, sort of the fraction of the grid or percent of the grid cell that is cropland expanded as a flow within that year, and run the same regression that we've seen a few times already. Dynamically, what we find is evidence of cropland expansion, but it's only in the arc of deforestation. It's slower than deforestation, which makes sense if clearing land happens in advance of actually using it for cropland. And it's not happening outside of the forest, which again is kind of consistent with the same pattern that we saw for deforestation earlier. Moreover, the marginal effects are bigger in the tropics, again, kind of consistent with what we've seen so far. Now, quantitatively, does this add up is the next question you might ask. I'm showing you here the long difference specification, where the left bar we've seen before, that's the effect in deforestation. The middle bar is the effect on cropland and the arc of deforestation, and they're essentially the same size as each other. So that suggests that one can account for the other. We can even do sort of a fancier version of that, where we kind of look cell by cell and see if the deforestation and cropland expansion are happening in these same places. The answer is yes, that all of our effects are on deforestation that can be attributed to cropland expansion in the sense that it doesn't exceed the amount of cropland expansion within that cell within a year. Wonderful. And then finally, in the last couple of minutes, what we haven't been able to do so far is use on-the-ground data in order to see directly effects on different kinds of land uses, input adjustments, as well as agricultural revenues and prices. So to do that, we have to sacrifice the global nature of the study and just look at one country where we think we have the right direct census data. And we're going to do this in Brazil. We're going to build sort of a skew panel, I don't know how to describe that, using these 3 rounds of the Brazilian agricultural census. And we're going to run a bunch of regressions now at the level of municipalities and these quasi-decades, if I'm being completely precise, of different agricultural outcomes on the same regressor, which is this change in exposure to killing degree days. And what we're going to find here will sort of be consistent with our global story, but also enrich it in a couple ways. So first, this is consistent. Across Brazilian municipalities, extreme heat leads to deforestation in the arc, defined in an analogous way, but now for municipalities, but not so outside of the forest as we've defined it. We see direct evidence that cropland area expands, now measured from the ground and not from space. Interestingly, not that pasture area responds, and not that forestry area responds, the last of which is kind of an alternative hypothesis that exists for what drives deforestation in these areas. And then finally, what about direct agricultural outcomes? Here we find something that we think is quite interesting and quite consistent with the model, where revenue per area actually isn't moving much, but that's sort of belying these opposite effects on prices, which we can directly calculate using sort of the value and the quantity of different crops in each municipality in Brazil and quantities. And if you were to kind of look at these results, these effects are almost equal and opposite. You get a very noisy estimate of the elasticity of demand of basically 1, which is exactly the region in which you'd have these very strong price effects. Okay. I suspect I have like a minute left. Okay. So, the last thing I want to tell you about are sort of, I told you this quantification numbers at the beginning. So this is just to be clear, what is that? It's taking the distributed lag regression from earlier, and plugging in realized temperature change and adding up the effects. We know that there are a lot of assumptions behind this that I want to be rather clear about, including the linear functional form, intercept, stability of these coefficients. Although towards intercept, if everything is quite localized, it may not actually be as big a problem as you might suspect. And this table is just going to summarize kind of the whole set of, say, predictions you can do here, where from left to right, we focus on the world versus just the tropics versus just Brazil. And notice there that a lot of the stuff is concentrated, on the rightmost columns. And as we go down, we compare what's in sample to what we predict out of sample. The middle is what we might reasonably say is a baseline scenario for warming. And then, of course, these estimates are much, much more extreme if you were to plug in a really dramatic scenario where the temperature goes up by say, 6 or 7 degrees Celsius by the end of century. But we just want to emphasize, we think these are economically and environmentally quite substantial effects, especially when you project forward. Okay, so I'm just going to conclude by flashing up the slide. Thank you very much, and I'm looking forward to seeing what Giuliano says and for answering questions.
Thank you very much. Our discussant is Giuliano Asciuto.
Good morning. Thank you, everyone, for the opportunity of coming here for reading this amazing paper. Just to start with a bit of context, because the first thing that I like about this paper is that it deals with the very first order kind of problem. And on your left, you can see that this is data from the most recent UNEP report on emissions gap that shows that emissions is not only that the emissions is out of control in the sense that haven't been able to decline emissions, but also deforestation accounts for the most important part of the increase that we observed between 2023 and 2024. So, deforestation is an important source of emissions. And it's primarily on the right, you can see that this is primarily something that's happening at the tropical world, right? And in addition to that, if you look at the expansion of agriculture between temperate and tropical zones, the expansion has happened primarily on the tropical area, right? If anything, the global area to agriculture has been stable or declined a little bit, but there's this important shift. So this paper, which is about agriculture expansion and deforestation in the tropics in the end of the day, where most of the action is pretty much connected with those topics which are quite relevant globally, right? So the first thing that I really like about the paper is the fact that it provides a quite powerful and useful way of studying deforestation at a global scale, right? The concept of the global arc of deforestation provides a quite interesting empirical setting for studying this process, and I think the paper does a great job in providing not only a way of dealing with those issues, but also illustrating how interesting many of those patterns can arrive. And the paper documents how climate change can affect deforestation, showing that this nexus between climate and forest is a kind of a two-way avenue, right? Most of the times people are more concerned of deforestation as a source of emissions and then as a source of climate change, but the paper does a quite interesting job showing that temperature shocks can reduce productivity, leading to increase in prices, and then inducing farmers to expand lands and in deforesting those areas, right? And also, one of the alternative story that could be compatible with those, at least on the first set of the results, is the fact that temperature shocks could increase fires, right, and other related phenomena. But the set of heterogeneity results that they provide, they are very useful, not only to get deeper into the mechanism, but also to rule out some of these alternative stories. So things like, the heterogeneity across demand elasticity, temperature tolerance, and tropics versus non-tropics, they are quite interesting in ruling out those alternative stories. And I think this provides a reinforce the overall interpretation of the results. This on top of many robustness checks that involves a substantial amount of data work, which is quite impressive as well. And to me, this paper illustrates well the fact that the Burlog hypothesis is more than a theoretical possibility, something that is happening at the global scale, right? And this story on the entrenchment versus the reallocation. I'm going to focus my comments in three areas here. The first one is most of those comments are more about the interpretation of the results. I think the paper is super consistent and the results are quite well polished and convincing. But there are some issues in terms of interpretation that I'd like to emphasize in terms of the modeling, the external validity on the entrenchment versus the reallocation story, and two smaller points to take into account. So we start with the model. I'm going to exploit something that Karthik hasn't had the time to exploit here, which is the fact that the model is about decomposing deforestation in terms of its drivers in terms of productivity gains, price effects, and the cost of conversion, right? In a way that if you have data on revenues, this will be replaced by just the revenue and the conversion cost. And when you apply that equation to the Brazilian data, what you get is that, they estimate a very zero impact on the revenue, on the temperature shocks on revenue, right? And an expansion of about 3 percentage points for each killing days, for the agriculture expansion. And this would imply that that result will be absorbed by the conversion cost, right? So using looking at the Brazilian data through the lens of the model, this would imply that the conversion costs would have be affected by these temperature shocks, right? But this is not consistent with the fact that they also estimate a zero impact for pastures and commercial forests, right? And this is because the only margin in the model, the only margin that can absorb this kind of results is the cost of clearing. And this is where I think there is a possibility to make the model a little less simple and add a kind of an extensive margin to explain some of these results, right? So suppose that farmers differ in the value of the best alternative of the forest, right? And you have a kind of a pie bar that is distributed according to G. And they might be scaled through a local shifter, mu I, in a way that farmers would operate only if their profits will be higher enough, right, to stay in agriculture. This would create a situation in which the aggregate amount of land that is allocated to agriculture will depend not only on the revenue and the productivity, but also on the selection into farming, right? And this is a way of incorporating the fact that these temperature shocks affect not only agriculture, but also the local economy in a way, the alternative activities that those farmers have available can change due to these temperature shocks, right? So in this case, that equation will have a kind of an extra term associated with the selection into agriculture, right? And coming back to the Brazilian case, this would imply that facing these temperature shocks, the marginal farmers who would have left might stay, explaining the rising in deforestation, even with the same clearing costs, right? So I think that expanding the model, accounting for that kind of margin can help explaining that thing that the authors claim in a very honest way in the paper, that is the controversy, right? The second point is about external validity of the entrenchment and reallocation thing. And when you look about the empirical setting, especially when you take into account the fact that the estimates are implemented through many fixed effects, the kind of variation that is identifying the results is pretty much short term, right? And it might be in a case in which, we are relying pretty much on temporary shocks rather than long-term regime changes in order to study this relationship between entrenchment and reallocation, right? And facing temporary shocks, farmers and the economy might not be in a position to make bigger changes. So in a sense, I think that the empirical setting is better suited to detect entrenchment versus reallocation. So the way that I read this result is not the fact that it is unlikely that climate change will induce reallocation, but rather the fact that the Burlock hypothesis is something that is happening at this moment, right? It's more about bringing an empirical appeal for the Burlock hypothesis rather than predicting that climate change will deepen this process, right? Because as things gets worse, we might see much more reallocation, and I think that the paper is not well suited in order to deliver that kind of answer at this moment. And two minor other comments. The first one is about international spillovers, in which the paper builds this interesting measure on the spillovers. And this measure doesn't account for distance between, sites I and J. And if you look at the results from the Brazilian data, there's some flavor of some market segmentation there. So maybe incorporating some, playing with some distance and interacting distance with this measure can help identifying some more interesting results on the spillovers. And finally, when you do the quantification exercises, which is quite interesting and points to a very dramatic set of results, I think it would be important to connect with this literature on tipping points on forests, because this will make the results even more dramatic in a sense. Thank you so much.
Thank you so much. So we are going to move into Q&A. If you have a question, go to one of the two mics. We have 20 minutes allocated for this, so do not be shy. While people step up, Karthik, if you want to say just a couple words to reflect on the comments, take a minute or two.
Well, I mean, the first words have to be thank you so much, Giuliano, for giving really thoughtful comments about the paper. I'll only say something about the short versus long run, which I find super interesting. One thought is that we have estimates on whatever you want to call it, the run of 10-year long differences. And we think that's using more long run variation. And it's coming up with quantitatively similar results. And the second, this is just a reflection, for some of the points about economic specialization, even say things did reverse after 30 years, the Amazon would still be gone. And I think it's just important to remember that, like, for the physical systems, deforestation is not as easily reversible, kind of regardless of whether economic activities reallocate in various ways. So. But the 3 years analysis, yeah. The shock is still temporary. Well, I think it is certainly a deviation from the global a deviation from the global trend. I don't think that necessarily means it's temporary. So it would be using differences in trend warming, let's say, across places. But the point is well taken, and I think we can explore that even more. Perfect. Yeah.
I was wondering if you could say a little bit more about what is an event when you're doing your event studies, and what do you do about repeated events, which must be a thing here.
Perfect. And because the mic wasn't on, the question is, what is an event in the event study, and what do you do about repeated events? I just want to be crystal clear. The regression is a distributed lag of changes in temperature, right? So that's, and the coefficient should be understood as an effect of the change in temperature in this year, controlling for the effects of the change in temperature in other years. And there are kind of other ways of running that regression where you just look at the kind of impulse response to a one-time change in temperature. And those results are in the paper. So the right interpretation of an event, I think, in the figures I showed you, is a permanent change in temperature, sort of as estimated from the variation that we see in the data. I don't know if that helps answer the question. The events are not binary, because the change in temperature is a continuous variable. Got it. And we could perhaps use different strategies like instrumenting with like particular years where there's a dramatic change in temperature. And that would be more just like a traditional event study. And it might just be easier to see sort of the interpretation you're describing.
N has very nice aggregation estimates that compare deforestation against like total forest area of Arizona. And I wondered if another interesting benchmark would be CO2 fertilization effect for wood biomass and forest. Is that similar order of magnitude or dramatically different?
I don't know. All I'll clarify is I'm pretty sure it's the size of all of Arizona, not just Arizona's forests. I don't know, and I think that's a super good question.
Really interesting paper. You didn't have much time to talk about international spillover regressions, but I picked up, if I'm not mistaken, that you had country year fixed effects. The extent to which these international spillovers are between countries, could it be that that fixed effect is absorbing some of the effect?
That's a very good suggestion. Fareed was too modest to lead his question by saying that he's written some of the best work on international spillovers for exactly this question. Best I recall, the estimates are pretty similar, even removing that fixed effect. But I think conceptually you are right that if a lot of this is sort of mediated across borders, potentially that's absorbing some of it.
I think this. Well, good morning, everybody. I think this fits in with the time horizon discussion, but it seems like we're thinking about deforestation as an absorbing state, an irreversible thing. And so why isn't the right model a non-renewable resource model where it's not so much about, like in that model, do your estimates tell us how the total amount that will eventually be cleared is going to change, or just the rate at which we are clearing that amount, that you would get in a hoteling model? And so I'd like to understand that.
Yeah. I'll just say, what we see in the data is that when we look at our distributed lag regression, say out, 5 years in both directions, we don't see any reversal, which is maybe what I would expect if over that time horizon, things are behaving like the hoteling model that you have in mind. Like we cut down this much forest and we run out of forest to cut down. So there's actually a negative effect, so many years into the future. Moreover, when we run the 10-year chunks, whatever you want to call them, that's similar to the sum of coefficients. So I don't think there's any sort of demons hiding between years 5 and 10. I think your interpretation, for some aspects of your question, maybe we just don't have enough data to tell, right? Because it could be that we only see those backlash effects in year, 30 to 40. And we're sort of not observing that right now in our data set. So I think it's a really interesting question. And it is, of course, quite important for thinking about the economics of this.
I think the definition of the arc of the forest is a very nice feature and decision that you've made here. I was just curious how that is defined relative to the event years. And so if it's fixed, the arc is relative to each event, then I imagine by like year 4 or 5, you run potentially exhaust the arc. But then if you try and kind of change the definition every year, then the costs of clearing would be changing relative to the event. So I'm just curious how you thought about this implementation decision.
Totally. And that's something I should have spoken about more in the presentation. Baseline results are using a dynamic arc, meaning we recalculate it every year. Results are quite similar quantitatively if we were to freeze it as of its definition in 2000. And just as a matter of fact, where a lot of our action is happening is the edge of the rainforest in South America and in Central Africa. And there's not, it's also related to the previous question, there is plenty of forest, meaning, you're not going to get to the middle for a very long time, to put it mildly. So within our sample, we think that there's not really the possibility, although it is, of course, interesting, that econometrically you run into issues because you exhaust the arc. David?
Hey, yeah, so I think one of the policy implications is that basically you want to make the agricultural good more tradable. And I was wondering, at the end, when you do the projections, you could do an alternative projections where now by 2100, we also trade these goods more, and that could kind of illustrate benefits, environmental benefits from trade?
I think it's a fascinating question. Truthfully, and hopefully this was clear, the way we're doing those projections is too low tech for that to be an easy undertaking. But I will mention, because I think it's interesting, related to previous work that Alan Chow and Jacob and I have done, we've explored in sample how to trade restrictions respond to climate shocks. And in a lot of cases, it goes the other way. And there's a lot of anecdotal evidence for this, and this shows up econometrically if you look at it carefully, that when there's these climate-induced food shortages, countries clam up. And that seems to be the direction in which things go politically. So I think it's worth doing that calculation, but also worth wondering if the world is going to push in that direction out of necessity or not. In the long run.
Very interesting paper. My question relates to one point that Julian made about the international spillovers or spillovers, and part also the definition of the arc of deforestation. Because when you showed us the map, at least in Brazil, you're focusing on the Amazon area, and I think part of this is related to how you define forest. Like I think 50% tree canopy, right? But there are other important biomes, and I was wondering if there is some spillover for those. For example, in Brazil, you have the savannas, right? So if it is the marginal land that is being converted, so I wonder if there's a conversion of those potentially easier to clear, and so that might be also an important margin to explore.
No, I think it's a very good question. And just more broadly, like all land is cleared of some ecosystem. And just because it's bigger carbon stock in the forest doesn't mean it's the only one that matters. I mean, I will say just factually in our results, when we look in Brazil outside of the arc, which as you say is outside of the Amazon, so, you know, in the Cerrado and the Atlantic forest and all that stuff, we don't see nearly as big a marginal effect of extreme heat on land expansion itself measured in the census. And there's a few reasons to think about why that is, including but not limited. I mean, I'm going back to sort of the more depletion of stock view of the world, which is that so much of that was just depleted in the 80s and 90s for urban expansion and agricultural expansion. So that is what we see in our data. But sort of, yeah, I think there's more general aspect of that in the whole world, right? That if forests are being depleted, there's other biomes that maybe aren't. And I think that would be interesting to explore more.
So it's a very nice paper. I have just 3 quick questions. First, when you look at deforestation, are you looking at net or gross? So for example, in the past 10 years, net deforestation is about half of what gross deforestation was, because there's regrowth and some replanting. So I don't know what your data is, whether it's net or gross. And also temperature affects crops, but so does rainfall. Most of the crop in the tropical and subtropical areas, like in Brazil, most of the irrigation is natural. There's no, artificial irrigation that's done. So when there are dry spells, when there's not enough rainfall or there's long droughts, that kills crops. And of course, temperature can affect rainfall, but that could be part of what's going on. And you're looking only at temperature. And lastly, in your forecast out to, what is it, 2100 or 2099, what is the CO2 absorption rate that you're using to get the impact on climate?
Thank you. Okay, your question's in reverse. For 3, we're just using temperature as a forcing variable. So notwithstanding the fact that we think it's intellectually interesting that there's a two-way feedback, that's not represented in those calculations, and I agree it would matter. For 2, I agree it would be interesting to directly look at rainfall. I mean, I suspect what we might find is that a lot of the effects of temperature are coming through dryness precisely because it's rain-fed. To the first, and I should have used exactly this language, the Hansen data set measures what you'd call gross deforestation. The sort of secondary data set that I didn't directly show you any results from the ESA, that would measure net. And what we find is qualitatively the same effects in both. I think marginal effects are a little bit smaller in the ESA data set, but the same order of magnitude. And that's kind of consistent with exactly what you have in mind. Thanks.
Hey, very interesting paper. So we're just wondering about your specification about these international spillovers. Does your econometric framework handle a possible dilution effect? Because the way that I'm thinking is that there could be one treated unit and then maybe multiple, maybe 10 control units. And then the possible spillover effect will be diluted into 10 different units, right? And then this will reduce the estimated magnitude and then probably will inflate the standard errors. And the image that you show us is kind of in line like this. So maybe lack of empirical evidence doesn't necessarily mean that there is no international spillover effects, but maybe one needs a different statistical framework to capture that international spillover with a kind of a slightly more statistical power, I think.
I think that's a totally fair point. For what it's, just in terms of choice of estimators, we erred on the side of using the most precise possible variation, but then an honest assessment of those results is that the confidence interval is kind of big. In theory, suggests that the effect would be positive, if anything. So, it's entirely possible that if we looked at this at a different level of aggregate, it's related also to Fareed's question earlier as well. And that point is well taken.
Yeah, super cool paper. I was wondering how much the deep forest null rule out like physical fires. So fires that are like near settlements that escape because of the heat, it's drier fuel. Deforests are also wetter, I think, and like far away from the settlement, so maybe they won't truly capture physical fire. So maybe you could use seasonality somehow, like dry heat, like dry season versus cropping season or something. Have you thought about that?
No, the concrete suggestion to use different times of the year is really interesting, and we've not explored that too much. Yeah, I agree much is different about the deep forest in the Arc, including but not limited to, just the amount of human settlements. And there I just think a lot of the other results about sort of the coincidence of these effects with cropland expansion, the heterogeneity analysis, might be some of the strongest evidence that it's not incidental. Thanks.
This is a bit of a high-level exploratory question where, bio identification, but if you strip out some of those fixed effects, can you tell us anything about the country-level heterogeneity you see? I mean, it's a Brazil and Congo story, or are there kind of other things going on, particularly where forests are expanding in the northern latitudes?
Yeah.
Could this go kind of in parallel and reverse to explain some of that? Better weather?
Yeah, it's a good question. I mean, I'll just say as we measure extreme temperature exposure, which as has come up is, not like the one-dimensional, only relevant measure of climatic change. We see big marginal effects. I said in the tropics, if you zoom in on Brazil, you zoom in on the Congolese rainforest, the marginal effects are really big. They're not so big in temperate areas, for example. But I just think it's speculation that this phenomenon is happening in reverse, and that explains some of the afforestation in northern latitudes. It's kind of interesting. I mean, especially over like a longer time period. Much of the U.S. Northeast was agricultural, and now it's forest, and that's sort of been a 100-year land transition that is just inherently very interesting and potentially related to some of the same economics. So yeah, it would be interesting to explore that in a little bit more detail.
One more question, organizer prerogative. Zach, one of the things I was really struck by in the results was when you add the country year fixed effects, basically everything more or less stays the same, which I think is telling us that these sort of like, if it's price effects, they have to be really localized at a subnational level. And I'm wondering if there's like anything you can do to push on that. Like it suggests like there have to be barriers to trade in terms of road and transportation infrastructure, or the particular crops are just sort of hard to move around in terms of just like value to weight ratio or something like that. And like, is there sort of heterogeneity you can use and transport availability, nature of the crop to push on that a little bit harder? I know local price data are not something you can do.
Yeah. No, I think that's a really great suggestion. The only kind of other thing I might sort of mention in that genre is one thing we think is interesting, and we could do more quantitative comparison to is there are a few microeconomic studies of, say, local price effects, both of weather shocks, but also things like in-kind transfer shocks, which kind of dramatically increase the food supply in sort of isolated rural economies. And they tend to find large price effects. And we could even use that, to get form even sharper hypotheses about where in the world and for what markets this is most likely to be the case. It's a bit more black box, but we think that must be lurking within, for example, the USDA elasticity estimates, but we could square the circle a little bit more on that. And I think it's a great suggestion. Thanks.
All right, we'll get set up. Our next presenter is Claire Balboni.
Thank you so much. Great. Thank you very much for the opportunity to present this. This is joint work with Aaron Berman, who's over there, Johannes Böhm, Lorenzo Marzano, and Mazar Wassim. So this is a project that's really at the intersection of two very rapidly growing literatures. The first finding that expansions in transport infrastructure can be an important catalyst for economic development through increasing market integration, labor mobility, and so on. And the second, a rapidly growing evidence base on the importance of a series of documented costs associated with air pollution, including from vehicular sources. So for instance, documented impacts on health, on productivity and cognition, and a kind of fast expanding set of outcomes. And we might expect this tension to be especially acute in rapidly urbanizing areas of particularly low and middle income countries, where these transportation infrastructure expansions are often happening in contexts characterized by very high levels of traffic congestion, alongside weaker environmental regulation and very, very high ambient levels of local pollution concentrations. So our study is going to be set in Lahore in Pakistan. This is one of the world's most polluted cities, where the latest estimates from the Energy Policy Institute at Chicago suggest that the average resident is losing more than 5 years of life expectancy to particulate pollution. So in this context, the key question that we're going to be focused on is trying to understand what the returns are to investing in urban road infrastructure projects if we account both for the economic gains that they confer in terms of trade and commuting benefits and so on, as well as the costs from local pollution exposure induced by these changes in market access from the road. As I've mentioned, we're going to be studying this in Lahore. Lahore is a sort of acute exposure location, but this is not atypical of many fast-growing, fast urbanizing regions of particularly South and East Asia. Here's just a couple of examples highlighting peak pollution periods in this context that have led to both stay-at-home orders and sort of large-scale hospitalizations. And on the right, just to put some sort of a magnitude benchmark on this, this is a day in Lahore in 2019 when the recorded levels of particulate matter 2.5, so particulate matter with a diameter up to 2.5 micrometers, exceeded concentrations of 1,000 micrograms per meters cubed. So the level that the World Health Organization deems to be safe is 5. So these are really, really acute levels. So in this paper, I will start by presenting just a series of reduced form facts based on measured ground station monitor data on particulate concentrations in Lahore. The purpose here is twofold, really. Firstly, to try to convince you that traffic is an important contributor to local particulate concentrations in this context. Hopefully that's not too surprising, but much of this is going to be focused on trying to highlight characteristics about the nature of this pollution, and in particular the spatial distribution of this pollution, that really motivates the data exercise and the empirical work that we're going to be doing in the paper. At the heart of the paper, then, we're going to be developing a quantitative urban equilibrium model that is going to combine elements of canonical trade and commuting frameworks with an atmospheric pollution dispersion model. I'll spend some time talking about that. And we will calibrate this data using a series of new data sets from Lahore on pollutant emissions, on pollutant concentrations, commuting, and goods trade. And then we'll use the structure of the model together with these data sets to estimate the distribution of both the economic and the pollution-related impacts from both realized and counterfactual road infrastructure improvements in this context, where the idea is to try to understand how our estimates of the net aggregate welfare impacts of these road projects change once we account for local pollution impacts, both as a result of roads changing the location of where traffic is, commuter and goods traffic, and through endogenous changes in the location of polluting industrial activity as a result of market access changes across the city. And we'll be looking both at the aggregate numbers and in particular focusing a lot on the distribution, the changing distributional implications once we start to account for pollution impacts. So starting first with these motivating facts. For the motivating facts and the motivating facts only, I will be focused on a series of reduced form facts that draw on data from 13 ground station monitors across Lahore that measure hourly concentrations of PM2.5. PM2.5 is going to be the pollutant here that is best measured, that we have the most data on, particularly at high temporal frequency, and is a pollutant where there's kind of documented widespread evidence about its deleterious impacts. So the first of these facts is just showing you pollution deviations on weekdays relative to unconditional averages by hour of the day. Okay, so here you can see that the sort of pronounced spikes are occurring during the periods, which I don't know if you can see the shading, but we've shaded the morning and the afternoon rush hour in gray here. And we see on weekdays relative to weekends a pronounced spike coincident with the timing during the day of the traffic rush hour. That's about 5 to 10% increase relative to an already very high baseline level of about 100 micrograms per meters cubed on average. And importantly, those spikes don't coincide with times when we would expect elevated concentrations from other sources. So industrial activity, which is happening throughout the working day, or crop burning, which again wouldn't be expected to be concentrated on those time periods. The second motivating fact then is trying to emphasize how spatially localized these effects are. So here, each of those is a different estimated coefficient from a different regression, where we regress ground station monitor PM2.5 measured concentrations on a series of meteorological determinants, and then the number of GPS signals that we observe from trucks within a given radius. And what you can see on the left-hand estimates is that we see a pretty pronounced signal associated with trucks within a radius of 250 meters or 500 meters, that there we're seeing elevated PM2.5 levels associated with having trucks that are really nearby. But by the time we get out to a radius of about 750 meters or a kilometer, that signal is attenuated down towards zero. And what we're really trying to emphasize here is that these effects are very, very spatially localized. And if we want to estimate damages accurately, we're going to need very fine spatial resolution data, and in particular, the 13 ground station monitor observations that we have available for using measured data in this context are going to be very, very inadequate for capturing spatial pattern of damages accurately. And finally, this is just showing you the full set of regressors in those estimates. These are just highlighting the importance of a series of other complex factors. So we've got a dummy for whether it's Ramadan or whether it's the weekend, and then a series of meteorological conditions, all of which can be shown to be important in determining how emissions in one location translate into concentrations in other locations across the city. And this is really highlighting that in order to capture this accurately, we're going to need to have a detailed model of chemistry and atmospheric processes that transport and disperse pollutants. And that's really going to motivate the modeling and the empirical approach. So in line with that, I'll move on to the high level of the model. In a talk of this length, I'm afraid I have not included all of the detail of the model that's in the paper. I'm very happy to talk about aspects of this in more detail in the questions, but I want to just highlight some of the key features and how we are capturing this. What's the aim of the model here? So the overarching aim is to develop a quantitative spatial equilibrium model of the city of Lahore that combines commuting and trade frameworks that capture the market access improvements and benefits associated with investing in road infrastructure, with then a model of emissions and the dispersion of local air pollutants. We're then going to calibrate this model using a series of data sets I'll describe in the next section, and use these to try to answer counterfactual questions about how the market integration benefits compare to the pollution costs associated with them. So at a very high level, we're going to have locations indexed by I and J within the city, and edges indexed by E that connect these locations. We'll have a residential population Li0 in each location. They're going to commute from their location of residence to their location of work and source consumption goods from across locations. We've got firms that produce and trade varieties of goods. And these we have within each location, we're going to have a location-specific productivity with agglomeration and congestion forces. We're going to add into this then pollution concentrations denoted by MI that take the following form, have the following key features. So we've got pollution that is endogenously generated in the model by production across each of these locations IJ, and by traffic generated both by commuting traffic and goods traffic that traverses all of these edges E in the model. The impacts of pollution in the model are then going to be twofold. We're going to have pollution at my location of residence that reduces my utility, and pollution at my location of work that reduces my productivity. And we're going to calibrate that in line with a sort of growing literature that tries to estimate those two elasticities. And those impacts of pollution at my in my residential and workplace location are going to affect my welfare, which is captured in the model's welfare estimates, and are going to influence my choice of workplace and routes that I choose to commute to my workplace. We've got congestion forces in traffic, such that as traffic on a given edge in the model increases, that increases the transportation cost associated with traversing that edge. And the very sort of elegant commuting trade and route choice infrastructure here is going to build on the canonical framework of Trebanel and Kostas Arkalakis, which gives us closed form expressions for goods traffic and commuter traffic on each edge as a function of trade costs and then the market access terms associated with the origin and the destination nodes. The beauty of that for the estimation that we're doing here is that this allows for us to solve the equilibrium system in changes in line with the Dickel, Eden and Corton setup. I just want to highlight how I'm trying to sort of abstract from the equations underlying all of those components of the model, but I want to focus on the key sort of innovation that we put into this model. So the set of externalities that are going to be key in the model are productive agglomeration externalities and traffic congestion externalities that build on canonical frameworks in the way that I've discussed in the previous slide. What we're going to add to this is a third key form of externalities in the model, which comes from air pollution transport externalities. And we model this as follows. So the pollution concentrations in a location J are MJ, and they're going to be the sum of pollution derived from industrial sources across all locations, and then pollution from goods traffic and commuter traffic across all edges in the model, together with a exogenous background term that captures pollution from other sources. So domestic and crop burning sources are going to be exogenous to the mechanisms within the model. Within each of these, we've got these emissions per unit of production or traffic terms. And then importantly, and this is going to be the focus of the calibration using the atmospheric dispersion model, is this pollution transport matrix gamma. This is governing how much an increase of 1 unit of emissions, from each of these 3 sources in any location affects the ambient concentration levels in my location J. Okay, briefly on the data, then our setting is Lahore, as I've said. Our estimation is going to be at the level of 1,655 Voronoi cells. We construct these based on the middle panel in the first instance. The middle panel is the full road network across Lahore down to the tertiary road network. We're going to use this to construct Voronoi cells, which just divide the plane according to those points which are closest to each of the nodes in that road network, so endpoints and intersection points. And that's going to yield the set of Voronoi cells you see on the left. I will just briefly mention we do an extension where we also allow for goods trade to be occurring with locations outside Lahore. We're going to do that in a simple way that just models other locations as being located at the province centroids of Pakistan's other provinces. So for each of these cells, we need a series of data inputs. We need residential population, which we're going to get from the global human settlement layer. We need output. We're going to take our central estimates are going to use the night lights data. In a separate set of estimates, we will use, we prefer these because they're going to capture the informal sector as well. In a second set of estimates, we also use formal sector data derived from VAT transaction data. Commuting traffic is going to come from nearly 200 million GPS signals, from slightly less than 400,000 cell phones across Lahore. And for goods traffic, similarly, we're going to have GPS signals observed from commercial trucks, about 5,000 commercial trucks traveling across the city. We're also going to have data from 671 traffic surveys. So these are ground station surveys, which allow us to see different vehicles by vehicle type and transport by mode and calibrate the units of these. The pollutant concentrations then is the sort of most complex novel data input at the level of the Voronoi cells. So here we're going to be using this atmospheric dispersion model of pollution that we have newly calibrated in Lahore using a series of inputs that I'd love to describe in more detail, and I'm happy to, they're in a very long appendix, but essentially these are drawing on a series of data sets on meteorological conditions, on background chemical concentrations, on a series of features of the Pakistani vehicle fleet that we observe, so traffic volumes, the exhaust and non-exhaust pollution emission factors, the different types of vehicles by mode, and then a gridded inventory of spatially aggregated traffic emissions from other sources. I will mention, you've already seen some already, we've already seen some data based on the ground station monitor data. The ground station monitor data will not be used in the model calibration. We will use it for validation only. Okay, so to estimate the model, we need to evaluate counterfactual changes in transport costs implied by the counterfactuals we're interested in. We're going to do this using the exact hat algebra based on the equilibrium conditions in first differences. In order to do that, we need a series of data sets at baseline. Some of these we're just going to get directly from the data sets I've just shown you, so production, residential population, and so on. I just want to say a brief note on workers and traffic, where we're getting that from. Homework location pairs, we're going to estimate based on Gabriel and Yuhei's work. So for each cell phone device by working day, we're going to say that its home location is where it appears overnight, and its work location is where it appears during the working day. We can aggregate that up to an origin-destination commuting matrix. Commuter traffic, we're going to obtain by projecting our cell phones to the edges in the road network and then constructing shortest paths, and similarly for goods traffic using the truck GPS signals. I'm going to run out of time, so I'll just show you very briefly that these look as we would hope they would. So commuter traffic is focused on sort of radial routes from the outskirts into the central business district, whereas goods traffic is more focused on through roads and radial roads. The pollution concentrations, that's the equation I showed you before. Taken in first differences, we get the bottom equation there. And these M terms are what we're going to use the atmospheric dispersion modeling system to calibrate the share of concentrations in any location J that derives from industrial sources in any other location I, and traffic sources on any road edge. And we're going to calibrate the external exogenous share from crop burning and so on to 60% following external estimates. This is just a map of what this is going to look like for a particular row of the pollution transport matrix. So for that cell, this is saying this is the share of concentrations, the marginal increase, sorry, of concentrations that derives from industrial activity in any other cell or from any edge on the right-hand side. This is where I would have to cut if I was running out of time. I would love to spend a lot of time here, given that this is newly calibrated in Lahore and the difficulty of data inputs here. We've invested really a lot of time in trying to do what we can on out-of-sample validation of the pollution model. Just to say very briefly, up on the right, top right there, you can see that how the cross-sectional variation correlates with untargeted data, both from ground station monitors or from gridded data, where it does pretty well, but really the toughest test we give it is the bottom. So that's modeled concentrations by hour of the day at the 13 ground station monitors. There's nothing in that is constructed such that it should look like the motivating figure that I showed you, but it looks very, very close to that, which is reassuring. In terms of the calibrated model parameters for the trade and commuting blocks, as far as possible, we're going to keep these sort of close to canonical frameworks to allow us to compare our results to the results that we get from the literature that thinks about trade and commuting frameworks in the absence of pollution effects. We test sensitivity to a very wide range of values here. The elasticity of utility with respect to pollution, our central estimate is going to be correspond very nicely actually to two very different ways of thinking about this. One comes from the Surat emissions markets estimates based on the value of statistical life in Pakistan. And the second comes from historical data on housing market transactions in the US. They're going to line up at that value. Again, we test a very wide range of values. And the earnings elasticity with respect to pollution comes from recent evidence from urban India. So the counterfactual simulations we're going to run through are threefold. So the first set of counterfactual simulations aims to ask the question, does accounting for the pollution channels in this model change our assessment of the welfare impacts of major road infrastructure projects relative to what we would have estimated had we ignored the pollution impacts? We're going to do this in the first instance by evaluating the opening of the Lahore Ring Road. This was sort of flagship major road infrastructure project in this setting over this period. And we're going to do a second exercise, which says that there's a very, very dirty vehicle fleet. If we make some reasonable, in this case, actually very, very ambitious assumptions about greening of the fleet, does this become a moot point? Secondly, we're going to find, I'm going to give the game away here a little bit, we're going to find that it matters. We're going to find that accounting for pollution reduces our estimates of the welfare impacts from these roads. The second exercise tries to sort of extend that and think, if that's the case, are there some road edges in this system for which the damaging impacts of changes in pollution exposure induced by the road are sufficient that actually they offset the market access gains associated with building the road? So for that, we're going to estimate the full general equilibrium welfare effects of removing each road segment in the city one by one. And then finally, we're going to do a different exercise which holds the allocation fixed at the baseline equilibrium and tries to estimate the marginal external damages from each road edge, and think about benchmarking that relative to the marginal external damages associated with pollution. So briefly on the Lahore Ring Road, this is a kind of major orbital highway built over the last 10 years or so, carries about 500,000 people each day. You can see it in red there. We're going to find that if we use the full structure of the model, including the pollution block, the estimated aggregate welfare loss is about 3.78%. So this is in line with what we see in, for instance, the magnitude of estimates of major urban transport infrastructure improvements in the work of, say, Nexivanidis or Roman Zarate. This reflects here the net impact of changes in trade and commuting costs and changes in air pollution damages, both through changes in traffic and changes in polluting industrial activity. But here we're going to then re-estimate the model to try to understand how wrong we would go if we ignored the impacts of pollution. So we just shut down all the pollution impacts in the model and re-simulate. We're going to find that if we shut down air pollution impacts, we would have pretty sizably overestimated the welfare gains from the ring road. So our estimates would have been about 13% higher of the welfare losses associated with removing the road. And importantly, we're going to see a very significant shift in the spatial distribution of those welfare gains. So in 21% of locations, accounting for pollution is actually going to change the sign. It's going to change our conclusion about whether that region was helped or hurt by the roads. So just to show you briefly the spatial distribution, this is what we see on the right here is excluding population, where you see, as you would expect to see, a very strong spatial signal of losses associated with removing the ring road right next to it, where the market access gains are most pronounced. Once we include pollution, we continue to see that signal, but we do see shifts. And in particular, if we look at sort of adjacent and downwind areas in the east there, you can see that some, once we account for pollution changes, removing the ring road switches to a benefit, and the aggregate numbers are as on the previous slide. Just briefly on this extension here, this is a very dirty vehicle fleet. So the Euro 2 standards, which are a pretty basic set of standards introduced in Europe in the 90s, is currently about 20 to 30% of the Pakistan, the Lahore vehicle fleet is estimated to comply with these. We're going to estimate how different this previous set of results would look if we overhauled the vehicle fleet such that we had 100% compliance. So this is a really quite significant, very, very ambitious greening of the vehicle fleet. Does this make this this effect not relevant anymore? Of course, as we'd expect in this case, the full model is going to give us estimates that are closer to the gains without pollution, but actually it's still leading to a pretty substantial decline in the estimated gains on the order of about 10%. And again, we see this distinct spatial shift in the distribution. As I've mentioned, the results here suggesting that accounting for pollution reduces our aggregate estimates of the welfare gains from the road raises the possibility that for some roads, it might be the case that these damages, these pollution-induced damages, are actually large enough that the net welfare impact of the road is negative. So we test that by doing this sort of looped estimate of every single road edge in the network, 2,000 odd roads. We switch each one off and re-estimate the full GE welfare impacts of doing so. And we can see that for about 3% of road edges, we find that that is the case. It's reassuring that that number is not higher than that. But there are some road edges in the city centre where we see, in particular in areas where there are lots of alternative routes and the market access gains are not so pronounced, but where you've still got a lot of adjacent and downwind people exposed to endogenous changes in pollution, that you can get negative effects. And then very briefly in my last 40 odd seconds, we're going to look at the separate exercise of holding the equilibrium allocation fixed at the baseline equilibrium. What are the marginal external damages from production on the left-hand side, as you can see, intuitively focused on the city centre. But where I just want to make the final point really is on the marginal external damages from traffic, where here this is going to incorporate both marginal external damages from pollution and from congestion. We're going to see that on average, the congestion is going to dominate here, but that pollution is still contributing a pretty meaningful share of the marginal external damages associated with traffic on each of these edges. And again, the distribution is really, really key here. So if we look at some of the, particularly the road edges in more densely populated areas, that we see a much, much higher share accounted for by the marginal external damages from pollution. I think I'm out of time, so I'm going to stop there and leave the conclusions up. Thank you.
Thank you very much. Our discussant is Gabriel Cranley.
Hello, thank you very much. I'm thrilled to discuss this paper. I've been waiting to read it for a long time, and it was great to do so. I'm going to start by hammering in even more strongly the motivation for this paper. I truly think that in urban transportation in low and middle income countries, understanding the air pollution costs is and weighing them against their well-documented benefits is probably the most important topic to study. A student, a graduate student, a couple of weeks ago told me they're in the context of pollution from Canadian wildfires. Look outside. This is how Lahore looks every day, right? The level of pollution is huge. Estimates of the share of that due to transportations are also very large, a quarter of that. So that means that people lose a year on the order of a year and a half of life because of transportation-related pollution. Another way to see it is that the vehicle fleet is, Claire's paper says, 5 times as dirty as in the US, whereas Lahore, like many cities in developing countries, has the added feature or bug of having very high population density, and especially close to roads, something that others have also documented. So it's really a maelstrom of problems. This paper does a lot and has many strengths. I'll mention a few. Clearly, the integrating the careful atmospheric model with quantitative spatial model is high up there. Even within quantitative spatial models, it has such detailed data on goods traffic within the city that is a contribution in and of itself. And the reduced form evidence on just how localized and driven by truck traffic and other traffic pollution effects are is also there. So I very much like this paper, and I think it has a solid methodological foundation for studying these issues. My main comment is going to be about how it can offer more transparency and handholding, which I kind of yearned for while reading the paper about, especially in terms of understanding and unpacking the bottom line results. So let me start with the bottom line result of the welfare impact of the ring road being over 4% and going down with that when the authors account for pollution. I have to be honest, I was a bit disappointed when I saw this. I thought pollution would account for more. So that led me into trying to understand what goes into these two numbers and their difference. And I think that's where the paper can help the readers more. Right. So what are the assumptions that are crucial here? What are also the key economic forces that drive this difference and these two magnitudes? And so one comment is that it just seems to me that the benefits not accounting for pollution seem too large. Now, I may be wrong, or there may be something here that's driving them above what we think is plausible. So just this number applied to urban GDP or urban income in Pakistan would mean that every resident of Lahore gains around on the order of $100, not PBP, per year, right? That's a very large amount. Just a very different back of the envelope calculation. There are around 500,000 vehicles that travel on these roads every day. Imagine they each save 15 minutes. Imagine generously that they have a value of time of $3 an hour. That would be something that's an order of magnitude lower. Now, on top of that, there's market access. There are general equilibrium forces. So surely these numbers absolutely do not need to agree one-to-one. This is also a large project, but the discrepancy seems large to me. Also, not from the paper, but from Claude's best understanding of like the costs of these projects, it seems that the cost is also on much lower than or on the order of a year's benefit as interpreted by the paper. So I'll do a bit more of this, of kind of just back of the envelope understanding what the forces are, but also try to now on this slide try to unpack what are the forces that we expect will be at play that create a trade-off. So I'll start from very partial equilibrium impacts of constructing or improving roads. And then add in G forces. So this is going to be easier for a marginal change. So just imagine all the roads in the entire city becoming 1% wider. So they increase capacity by 1%. What happens? Well, the first benefit is going to be faster travel time. If everything else stays put, we just have some congestion relief from that. on the order of maybe a third of a percent. What about economic benefits from that higher travel? So the most naive thing to do here is an envelope theorem or Halton theorem result, which is going to say the value of commuters that are currently using those edges and the value to goods is what we're going to gain. So I already did the goods one for commuters. That gives around $1 per year per person in benefits from this change. Okay. Now, again, this is not accounting for any GE. So how much should we expect that those added forces do? So Nick Tivanidis in his paper in Bogota conveniently kind of compares those two value of travel time savings with the full GE and finds that the GE effects are amplified by a factor of 2. Now, so far, there is no trade-off. In fact, if cars and vehicles drive faster, they idle less, there might even be emissions benefits. So where does the cost come in this aggregate exercise, which I want to emphasize is not what the paper does. But I think it has to be through some kind of induced demand. Travel time are faster now, so there will be more travel. Commuters will go further, there will be more trips, there will be more goods travel everywhere else. Now, that's maybe going to be somewhere between 0 and 100%. At 100%, that would mean that 1% capacity increase means 1% more traffic. There will be none of the benefits that I mentioned earlier because travel time is no longer faster. And we get all of these pollution costs. So with the numbers in the paper, that ends up at something around $2 per person per year. So my point here is that with this exercise in this other counterfactual, these things seem at least much more comparable. So it seems like some higher potential damages from pollution. And the second way is just that understanding what induced demand is in this setting seems important to talk about and discuss. However, this paper focuses a lot, and the strength of it is in the geographic richness of understanding effects that are localized. And so closer to what the paper does is an exercise where one road segment gets improved, and then there's a lot of spatial substitution that comes from traffic rerouting, as well as any increase in traffic on that particular edge is going to affect a particular set of people based on those who live close to that road segment and are downwind of it. That is what constitutes this externality matrix, gamma. That is where all of the atmospheric model goes in, and I think that's very helpful. So what happens with this one segment, then these forces need to be iterated because changes on one road segment affect traffic on all the other road segments through the arbitrage in the traffic network and affect also the desirability of working in different locations. And so those kinds of effects need to be iterated until we get to a new equilibrium. So here, my transparency comment is, I wonder if the paper can do a bit more to give us an intuition for why certain segments are better than others, that kind of we can see and connect more clearly with the data before all of the really rich but also complicated machinery of the model kicks in. And I think the answer is yes, this to a first order depends on this externality matrix as well as some equilibrium substitution matrix, which says if one edge becomes more attractive to traffic, so for example, travel time goes down, then what happens in equilibrium to everywhere else? So what is the substitution from or towards all the other edges in the network? And so to a first order, that's those two objects interact to give you the new equilibrium. That's something that goes back to Herberger and that I looked with Kartik Patekar on not a QSM model in a recent paper. All of the ingredients for this are already in the paper in the context of the QSM model. And there's this feedback matrix F. So I wonder if the paper can kind of highlight those more and help link the data it has and the model assumptions to the results. So just to wrap up, I'd love to learn more from this paper about what are the model assumptions and the empirical moments that tell us something about induced demand. I also think that before or in addition to showing welfare effects, showing a trade-off between economic benefits and something like years lost would be a bit more agnostic, but could increase transparency. And finally, I think this is, again, a fantastic machinery for evaluating road construction, but also a bunch of other really important policies like restrictions for truck traffic by time of day or in certain regions. Thank you.
Thank you so much. Please line up if you have questions. Claire, take a couple minutes.
Yes, great. Thank you so much. This was very, very thoughtful and helpful. Yes, all excellent points that we will take and reflect on where the welfare numbers come from. Yes, I think it's really important. I sort of sidestepped it a bit by saying this consistent with lots of estimates from elsewhere, which we find sort of reassuring. But I think a key thing to note here, you're right that where a lot of that is coming from is the sort of relatively high benefits relative to pollution costs. I would say, I think what might be of relevance here is this is a ring road. And so in some sense, and I think it's interesting to think about how far this would be different had we considered other sort of types of road project, but often parts of this particular road are redirecting traffic away from populated areas. It's not, you know, it was empirical that it should even be negative. There was a world in which it could have redirected it away sufficiently that you overturn the kind of pollution impact. So in that sense, I think that might be driving some of it, that the pollution effects of this particular road are such that some segments of the road are moving people away from particularly exposed areas. But there's a lot that we need to do in kind of unpacking how different outcomes are changing, which I think would be really important. And these are really helpful suggestions on that. Why some segments are better than others? Absolutely right. The kind of eyeballed exercise of these are next to densely populated areas where there are lots of other substitute routes is not sufficiently precise. And I think your suggestions as to how to make that more precise is great. One thing I just want to mention that we're currently doing actually is trying to use individual trips data. This is a kind of computational lift, but using individual trips data from the cell phones data together with data on traffic disruptions at a particular node to try to do a more precise job of testing the Alanon-Arkalakis routing structure assumptions a bit more, which I think would speak to some of your points about transparency and what's driving that, which would be great. Many other points there on the other policies. Yes, I completely agree. We've had a sort of counterfactual proliferation risk that we've been trying to rein into structure around the current set of counterfactuals, but I think there are many, many other interesting questions that we could think about here as well. Thank you so much.
Yeah, maybe I'll start.
Sure.
Yeah, just a question about the data that you're using for production and population. So it seems to me that both the lights and the settlements could proxy for population and production. So how are you making sure that lights are capturing production and settlements are capturing population and not like work location?
Yeah, so it's a great question, and we've gone through many iterations of thinking about this. The human settlements layer data is what we're using for the residential population data. To the extent there is some correlation between that and the night lights data, that may indeed reflect the fact that night lights is picking up residential lights, transport lights, and so on. We have done two things on that. One is a version of the night lights data where we've tried to take out obvious sort of sources of lights that would be problematic for their interpretation through the lens of our model. So the airport, kind of big transport facilities and so on, and rerun things, and that doesn't change things very much. The other thing we've done is to use a second imperfect data set on production, which is the VAT data, and for a long time that was actually our central data. I think the shortcoming of that data, that it only captures the formal sector, outweighed it. And so we've tried to just do sort of different versions and kind of manifold robustness to do what we can on this, but you're right that no measure of production at that kind of a spatial resolution is going to be perfect. Thanks.
Very interesting. How do you estimate the different emissions and how you differentiate types of pollution from industry, trade, and traffic, especially in the context of pollution where some of these pollutants may interact, form secondary PM2.5 or ozone, and create higher damages?
Yes, it's an excellent question. And for this, we lean very, very heavily on the ADMS machinery, and we've spent a sort of awful lot of time with the ADMS team. So the ADMS team have given us a lot of inputs on how to think about that in this context. So it captures across pollutants. We have, for traffic in particular, we've been very, very sort of involved in ensuring that we are capturing different different types of vehicle on the road. Within vehicle type, different truck axles, they all have different emissions factors. They have different exhaust and non-exhaust emissions factors by age of the vehicle fleet, by compliance with the emissions standard. All of that is in the ADMS model, in the calibrated the way in which we calibrate traffic emissions. We do have emissions from other sources. That's coming from EDGAR, I believe. That's in the appendix. But so there are sort of a series of different data sets that go into the ADMS model to capture emissions from different sources. On chemistry and transport, you're right. And this again, we went back and forth a lot with the dispersion modeling team over the timescales and distances that we're modeling here. Their sort of best estimates of this were that modeling this in the linear way that we're using in the model was sensible. Certainly for other types of atmospheric chemistry, for different types of pollutants and particularly over longer horizons, that becomes more challenging. But here we're modeling it as linear in line with the evidence on the pollutants we're using at this scale. Thanks.
I'm curious to ask about an item that's probably in your counterfactual proliferation risk set, which is a charge for trucks visiting the central business district.
Yeah.
And the reason to ask about it is it's a little closer to a Bogovian tax than turning off road segments. It's also something a bunch of countries are doing.
Yeah.
And then there's an interesting trade-off that the CBD has high productivity, and so the sign is ambiguous, and QSM is a good saying to it.
I think it's absolutely right. And this also really aligns with Gabriel's sort of suggestions on alternative counterfactuals. By counterfactual proliferation, I don't mean to suggest that we're drawing the line where we're drawing the line. And I think actually the very last slide I showed you on marginal external damages is our first step in probably what will end up there. In that we've tried to restrict this to a set of counterfactual policies that we think are relevant for policymakers and sort of potentially implementable or have been discussed or implemented in this or related contexts. And I think thinking about charging is the one that's sort of remaining here. So we've looked at the marginal external damages across pollution and congestion. I think this has been a very valuable exercise for us. But that has thrown up this very distinct spatial pattern, actually, of the areas where the pollution damages and the congestion damages are appearing most strongly. And I think the natural next step on that is to think about what that implies for a set of Bogovian taxes across the city. And the time of day thing is really a comparative advantage of our data. So I take that on board. And I think we really should incorporate that here. That's exactly what we could see. Sort of heterogeneous charging by vehicle type by time of day is exactly what that infrastructure allows us to capture. So yeah, thanks for the suggestion.
A very interesting paper. And continue on the counterfactuals. I was wondering if you could potentially entertain one that goes like the placement of the roads are, let's say, around the city. Like there's some work in São Paulo, for example, where you constructed the beltways, and then the trucks were going through the beltways, reducing pollution in the city. So you might have the benefits of the road still. I don't know the geography of Lahore, so maybe that's something to consider as well.
Yeah, this relates, I think, a bit to Gabriel's, my answer to Gabriel's point, which we had thought about this with the ring road. As it turns out, the geography of Lahore is such that because of how densely populated it is, and the ring road is very far away from the densely populated areas or areas that are upwind of the densely populated areas. And in addition, it's more complicated than that in GE because the road is also shifting the location, the incentives for firms to locate, and they are an endogenous source of pollution in the model. So the structure of that is very complicated. I think the ring road is sort of interesting in that it captures a bit of that motivation. I think both your question and Gabriel's comment has made me think we need to draw that out much more clearly and transparently in the paper, because I think that's it's a different type of road for exactly the reasons you highlight. Thanks.
Yeah, really cool work. My question is really about the modeling of the pollution impacts.
Yeah.
So the utility and earning elasticity. I wonder, like, is avoidance or adaptation behavior something within that? And since that developed country and developing country could be quite different, and how do you think about that? And the second question is related to, since the pollution peak is mainly during commuting time, so are you assigning that more to the utility elasticity, to earning elasticity, to both, and what the assumption baking that?
Okay, thanks. No, these are really, really important questions and have taken so much more time than was possible to reflect in this set of slides. So I'm glad to be able to talk about it a bit. On the utility, so the utility and the earnings elasticities in the central estimates. So I talked a bit about how we'd calibrated those based on kind of central approaches in the literature. We've done an enormously wide range there of robustness to different values for those elasticities, and in particular on the range is narrower. Estimates of the productivity elasticity on the utility elasticity, it's very difficult to estimate that, and there's a series of estimates in the literature. For instance, you get very, very much lower estimates in settings where we might expect information or behavioral frictions to be really important. Residential choice is not a margin here, so that wouldn't affect behavior in the model, but it would certainly affect the welfare estimates on the utility side. So we've tried a lot of different values for that to try and capture that. The results are going to be qualitatively robust, as you'd expect. If you make the elasticity smaller, you're going to make the estimates of the impact smaller. Okay, timing. Yes, that's absolutely right. Yes. So another thing we've done here, which I think relates to this, is exposure on the commute, which is, as you say, there's this kind of peak of when you would expect this thing to be relevant, which is exactly when people are traveling to work and they're out. I was actually surprised. We've done it in a robustness test where we allow for pollution to affect the welfare estimates, both through their impact on my utility and my residence location, my productivity, my workplace location, and my utility as a result of pollution exposure on my commute. I expected that to make much more of a difference it does make pollution more important quantitatively, but not by a huge amount. The reason for that, we kind of dug into a bit, and is twofold. One is you don't spend that much time on your commute relative to the amount of time you spend at work or at home. But the main reason for that is that in this setting, the pollution gradient between indoors and outdoors is not that large. So the sort of best estimates we can find, and we looked across Pakistani cities, there's a study in Dhaka in Bangladesh and some Indian cities, was about 1.2. So, and that's partly sort of poor insulation and so on. That means that the gradient's just not that huge. But it's a really important point. We thought it would be even more important. Yeah.
So impressive work. So in a model like this without emissions, I think that the first policy is to provide the right amount of transportation infrastructure in regard to congestion and commute. But here that's coupled with pollution taxes, a little bit like Picovian taxes that Joe picked about. So could you just like using your machinery do that, like couple it with like pollution taxes and benchmark it, so that whenever you do kind of like any other counterfactual, you can benchmark it toward that so-called first best.
No, this is great. And I think this kind of chimes a bit with Joe's suggestion, which is definitely what we're thinking about. To be clear, our kind of policy exercises at the moment are distinct. So we've thought about, the estimates suggest that when thinking about optimal placement, when thinking about design, that matters. In a world where we haven't introduced the taxes, then there's a separate set of exercises where we're looking at marginal external damages in pursuit of thinking about charging and so on. But I think that's absolutely right that it's a natural benchmark, and this is the sort of third data point to suggest that we should push a bit more on this amongst the set of counterfactuals that we round this off with. Thank you.
So this is really a comment about the interpretability and accessibility of the results. So what you've done is I think a natural thing was just to ask sort of ring road or no ring road, and sort of what's the welfare implication, which is a totally sensible thing to do. But sometimes results that are hard to interpret or understand the scale of. So the thought experiment I'm going to suggest to you is something that gets at the same question, but from a slightly different increment, which is in some sense taking as an assumption that there's going to be increasing economic activity in Lahore, and asking then, conditional on some increase in economic activity, what is the pollution effect if you are driving that economic activity through an infrastructure that has a ring road versus through an infrastructure that doesn't have a ring road? And you could do different kinds of economic activity. What if there were productive activity? What if there were retail activity? What if there were commuting activity, and you could ask hypothetically in different locations, maybe in some of the locations that your GE tells you would get if you have the ring road. But that gives you sort of a units that say if you add, $1 million worth of economic activity, what is the pollution consequences of having that in a system with a ring road and without a ring road? Might be numbers that might be more easily accessible in terms of their meaning and impact.
Absolutely. No, that's really interesting. That's sort of, in some sense, the flip side. We've thought of the baseline counterfactual plus change the polluting properties of the vehicle fleet, but there's the baseline counterfactuals plus change actually the characteristics of the distribution of economic activity in a way that could also change the calculation. We haven't thought of it. We haven't done it, but it's the sort of machinery is totally amenable to running something like that. So that's really helpful. Thank you.
Hi, Claire, really cool paper. I'm thinking, excuse me, a lot about informality. This seems like a context where both on the economic activity side, as we've talked about, and on the pollution side, it's like a really hard data problem and one that probably matters a lot. So on the economic activity side, I could think things like daytime imagery could help you over nighttime imagery, but then I'm curious in terms of how you're measuring traffic with trucks and cell phone GPS, and then how you're measuring the emissions that go into the chemical transport model and the air transport model. Like, how are we thinking about the vast amount of informal pollution, informal vehicles, like motorbikes with lots of people on them? Like, how are we measuring this, and how is that factoring into what you can and can't do with the data?
Great. This is super helpful. There's like 5 things there. So let me try and take them in turn. I think there are many, many things that are going to be important for this. Daytime imagery is a good one. We haven't done that. That's something else that, as per the previous discussion, I think the production data is one area where this is first order. And we've sort of done what we can on it, but we could try and incorporate it there. On informal sources, on traffic, I'm more confident. So certainly motorbike, other types of vehicles are captured here. And that's, we have ground station, the traffic survey station data where they record all vehicle types. And we've got incredibly comprehensive data on vehicle type, the fleet characteristics, emissions standards, and characteristics, and so on. So I think in terms of the vehicle fleet, that's one thing to say on that. On the nature of informal productive activity, one thing that we do, because we're capturing commuting via the cell phone data, that permits very, very local commuting. And we see that that's really important. And I think that's consistent with the story that informal activity is a large share of productive activity here. We capture that here. It's not treated any differently in the model. There's no sort of separate productivity term or separate sort of production block that is informal activity. We could think a little bit more about that, but we're capturing a series of features in the trade and commuting data that is consistent with informal activity being important. We're just not treating, other than through transport, where I think we capture it pretty well. We're not treating it any differently in the model. We could have a little think about under some sort of assumption on that share, whether we'd be likely to change the results. I don't know. We haven't done it. Thanks for the suggestion.
Just wondering if you could say anything about public transit at all. If there's any way to speak to like changing the composition of vehicles.
Yes. So
taking cars off the road and putting them onto buses.
Yeah. So that's interesting. We have public transit. So we have public road transit, and this is a period during which that's the relevant form of public transit in the city. So we have, amongst the vehicle types measured in the traffic survey data, we have buses, and they have a passenger car equivalent that we use for calibration in the model. That's that's captured empirically in the data. What is not captured is if there were to be an endogenous change in modal choice as a result of the counterfactual transport investments. So if X% travels by bus or whatever, that's there. But if by building the ring road, you induce changes in modal choice, that's not there. I think sort of reasonable assumptions about the sort of bounds of that kind of a change we could do. It's not hard to model. Thanks.
Thanks for a really great presentation. And this question is transparently more about sort of other interesting stuff you could do in this area and policy impacts this work could have. How much, or I'd just love to hear more about the positive political economy of all of this in Lahore. So, I mean, to be a bit more specific, do the people who like or want the ring road line up with who benefits in your calculations? And they certainly don't have to because of all the factors involved. And are people in and around the road well represented in Lahore's metro government, or is that sort of so far out that they're a little bit excluded from the I don't know anything about Lahore, so I'm not suggesting it's the case, but I think they would be interesting to know more about.
Yeah, this is very, very interesting. On the representation point, we haven't looked at that, and that's an interesting dimension of it. On one relevant factor that we have looked at is trying to look at distribution by characteristics other than space, and in particular looking at, say, income or sort of other measures that capture the incidence. That is incredibly hard to do at this resolution. So there's a bit of a trade-off here in that we have, there is a version of this analysis at a more spatially aggregated level on the order of 200 cells rather than 1,600 cells. Even at that level, we really didn't find compelling administrative data on kind of income distributions or even kind of demographic characteristics that would. We think this question is very interesting and important, and continue to pursue data leads to do more on it. I'm very pessimistic on our ability to do that at the level of the Voronoi cells, but I think there is certainly the possibility that at a more aggregate level, we could say something. And I do think it's very important, the political economy of this elsewhere, and this is sort of studied much more in developed country settings where we see that there is a hugely important set of distributional implications that would be really kind of remiss to not think about. And so, yes, I think the set of issues is important. It's not something we've been able to make much progress on. That's been a data constraint, but I think there is a question about at a more aggregate level whether we can say something on this. So thanks for that.
All right, I'll take the last question one more time. Organizer's prerogative. So you have this like model of sort of cells and sort of roads or edges between the cells. I think where I'm going is like roads in reality are two-dimensional things, not one-dimensional lines. Like they take up space, and I'm just wondering to what extent that's important as we go to sort of like a ring road. I have no idea how many lanes it is, but it's presumably taking up some space where people could live or a business could be or something like that. Like take it to the extreme, like an 8-lane road. I'm thinking like the Dan Ryan Expressway in Chicago. They bulldoze city blocks to build that thing.
Yes. Okay. So you're saying it would change sort of productive land availability or something in a way that could influence the model. Yes, that's not currently in the model. What certainly is in the model is by road width or road characteristics. We see differences in speeds and emissions and so on. So we account for the fact that roads look different in different areas of the city. The kind of endogenous feedback into what that does to local land availability, and through that firm behavior, for instance, we do not have, I'm trying to think how far it might be captured to some extent in the measured kind of location specific productivity terms. But again, that's not going to be part of the counterfactual. So it's an interesting thing to think about. We should.
Yeah, but you could even, there's even like a small back of the envelope thing put aside integrating into them.
Exactly.
Like what share of land area is being hoovered by the road or something.
I'm confident that share is reasonably small, but I should put a number on it. And I think we can probably do a little bit more on thinking about how it features some counterfactuals. Yeah. Thank you.
All right. Thanks, everyone. Thanks to the presenters and discussants thus far. Thanks to everybody for asking questions. This has been great. We're going to take a break. The egg timers are coming. If you are presenting an egg timer and you have not yet uploaded your slides, come up to the front right away. We will begin promptly at 11:35. So we have a good 35-minute break. All right, welcome back, everyone. Grab a seat. All right. We are on to the classic egg timers. In the spirit of ongoing egg timer innovation, we are trying a 9-minute format this year. Thoughts, questions? If you have thoughts on formatting, please let us know, or let the program directors know. Meredith and Chris are here. So each egg timer is going to be 9 minutes, no questions, and we are going to go straight from each one directly into the next one. And I strongly encourage you, if you have questions, comments, want to follow up, catch the presenters at lunch. So we'll fire it up. Take it away.
All right, yeah, thanks for inviting us and giving us the opportunity to present here our work on clean cars, dirty margins, portfolio leakage, and in electric vehicle subsidies. So climate models have typically assumed a one-for-one displacement, meaning that if you subsidize a plug-in hybrid electric vehicle or PHEV, it's assumed to displace exactly one internal combustion engine or ICE vehicle and all of its annual mileage. This assumption can fail for several reasons. We're going to focus on one within household decisions. So when you subsidize a single clean car, it affects several household decisions. First of all, the new car attributes will unambiguously be cleaner. However, how many cars the household retains, what cars exit, and what cars are kept, as well as the driving allocation on each of those cars, that's somewhat unknown. So therefore, our question is, how much gasoline demand is actually displaced if you subsidize one PHEV car across the entire vehicle portfolio? So this is, to the best of our knowledge, the first quasi-experimental evidence on this full portfolio response. And this matters for policy. If displacement is imperfect, meaning treated households retain more cars or retain dirtier cars, the expected emissions fall short and the cost per ton of CO2 abated rises. So identifying this effect has been notoriously difficult. EV policies, for at least 3 reasons. EV policies are not randomly assigned. Vehicle choice is correlated with driving demand, and observing individual level data as well as all cars in the household portfolio is quite rare. Our setting hopefully addresses all 3 of them. So we use Swedish administrative data, where we observe each car in the household portfolio when it was purchased, when it exits, and all of its annual driving. And we use 2 sources of variation here. First, we combine people who had a fixed 3-year lease renewal cycle, where over 40% of people adopt a new car at exactly this 3-year lease renewal, and combine that with a policy-induced subsidy change in January 2020 that increased the eligibility cutoff for PHEV cars and also implied a larger bonus for those cars. So how do we estimate this? So we use a predetermined lease renewal that was made way back before the actual policy change. So take the control household here at the top and the treatment household at the bottom. Both sign their first lease. The control household signs their first lease at the end of 2016. The treatment household signs their first lease at the beginning of 2017. Because both households are at the 3-year lease renewal cycle, the control household will adopt the new car at the end of 2019, whereas the treatment household will adopt their car at the beginning of 2020, and will therefore be eligible for the higher PHEV subsidy. So we will use this as exogenous shock to the likelihood of adopting a new PHEV car. So in order then to measure gasoline demand differences, we take the differences between 2021 and 2018 to measure the difference in gasoline demand, because these are our only lease intervention-free periods. So now the results. We observe that, or we estimate that treated households receive higher subsidies. So these are the households with a 2020 lease expiration. And then we use the same RD design to measure the effects on 4 outcomes that determine total gasoline demand reduction or change. We find that treated households are more likely to adopt more fuel-efficient cars compared to control households who adopted the car at the end of 2019 as intended by the policy. However, treated households also retain dirtier cars. And in terms of driving, they drove their new cars less, and they drove the dirtier cars more than the control households. So now to put this all together and convert these estimates into gasoline demand changes, we multiply the coefficients with pre-treatment means. And let's start with the new cars in the middle panel here. We observe a total gasoline demand reduction of around 85 liters per year. And this is due to having adopted cleaner cars, but also driving them less. Then the retained cars, on the other hand, of the treated group, there we estimate a total gasoline demand increase of around 72 liters, which is due to driving those retained cars more and keeping dirtier cars. So now if we put this together, we see that the total gasoline demand reduction of the entire household is only 12 liters. And so the total effect of the new cars is almost entirely offset by treated households having retained dirtier cars and driving the dirty cars more. So this effect is entirely driven by multi-car households. So in our sample in Sweden, around 40% of households own more than one vehicle, conditioning on owning a vehicle. In the US, the share is even higher. Around 64% of households, again, conditioning on owning a car, own two or more vehicles. So this household portfolio leakage effect, if anything, should matter even more here than it does in Sweden. And then at least one of the reasons why we observe this household portfolio leakage effect is that treated households retain more cars on average. And this has two direct consequences. One, in terms of driving, because you keep more cars in the portfolio, you will automatically allocate fewer kilometers on the new PHEV car. In terms of fuel intensity, because retained cars are dirtier on average, this will raise the average fuel intensity of that household. So we will drive more on dirtier cars on average. So what does this do to cost effectiveness? So here we calculate the marginal cost of carbon abatement, which simply divides the fiscal cost per adopter by the discounted lifetime CO2 abated. Here the red dashed line represents the social cost of carbon in Sweden, which is $126 roughly. And the light gray dot here reflects the CTA of the subsidized car. And the black one reflects the CTA of the entire full portfolio. So in a renewable grid, which is almost the case in Sweden, we find that if you only take into consideration the gasoline demand changes from new cars or for the subsidized cars, the CTA is almost cost effective. However, when you take into account the entire portfolio response, the CTA is roughly 5 times the social carbon estimate in Sweden. If you assume natural gas or coal for EV charging, those numbers become even worse. So a big takeaway here is that if you disregard the gasoline demand changes from retained cars, you may heavily overstate the environmental benefits. Thank you so much for your attention.
All right, thank you so much for including our paper on the program. This is joint work with Olivier Darmouni and Clemens Lehner. So in terms of motivations, rising global electricity demand is expected to generate large-scale investment in new power generation. In the US, the IEA estimates over $8 trillion will be invested over the next decade. And the question that we're interested in is whether renewables or fossil fuels are what's going to get built to meet this demand. That's obviously going to matter for US carbon emissions, and it will also depend heavily on which of the two technologies is cheaper to finance. And so I have this quote here from the International Renewable Energy Agency, IRENA, where they say the cost of capital, i.e. the financing cost for renewable power generation technologies is a very important driver of total costs. So what drives the cost of capital for renewables? According to modern finance theory, it's going to be a function of two things. It's going to be a function of the fundamental risk of the technology, but it's also going to be a function of the capital structure. So that leads us to a puzzle. What is actually the financing structures involved in new electricity generation? What's interesting is that the way in which renewables and fossil fuels are financed differ dramatically. And in particular, we're going to focus on the use of power purchase agreements, which are long-term financial contracts that fix prices and quantities. So as an example, we're going to look at Vineyard Wind, which is the largest US offshore wind plant, to give you an example of what financing looks like. So to build Vineyard Wind, there was a $2 billion loan taken across 9 banks, and that represented about 60% of the overall CapEx. On the asset side, to get this financing from the bank, Vineyard Wind needed to negotiate a 20-year PPA with the utility. And importantly, that was a condition of the loan. The banks would not provide financing to the project in the absence of this PPA. And this combination of bank debt with PPAs is ubiquitous across renewables financing. But what's interesting is that for fossil fuels, for example, if you want to build a new natural gas peaker plant, this is not how new generation is financed. Usually, fossil fuels are financed by regulated utilities that issue corporate bonds to build new electricity generation. And PPAs are much less common in this context. Bondholders do not require PPAs as a condition of the investment. So what's interesting is that both gas and renewables are used to produce electricity, and they both also face electricity price volatility, yet creditors only require power purchase agreements for renewables, but not for fossil fuels. We found this to be a puzzle, and we think this is also important to understand because PPAs are really hard to get. You need to have a reliable counterparty that's willing to take long-term price risk. So not that many agents in the US economy meet that criteria. So in this paper, we seek to understand this differential use of PPAs across renewables and fossil fuels. Our approach is going to be to present new stylized facts on energy finance, as well as a calibrated model of optimal financing. And we're going to have three key findings. The first is that PPAs are very useful for renewables because they lower cash flow volatility. And this lower cash flow volatility expands the amount of money banks are willing to lend to these projects. And this expanded debt capacity helps to reduce financing costs because debt is cheaper than equity. However, PPAs are not good for fossil fuels. And the biggest issue is that having a fixed electricity price reduces the option value from being able to produce flexibly. So a lot of the ex-ante value of gas production comes from the ability to produce more when prices are high. So if you fix prices, you erode that option value and you destroy profitability. So PPAs are good for renewables and bad for fossil fuels when you think about micro risks. But a challenge with PPAs, even for renewables, is that it's bad in the context of macro risks. So PPAs are going to have this unintended consequence where they remove a natural hedge between electricity prices and construction costs. So we're going to give an example of the 2022 inflationary episode where inflation went up, all prices went up, but because of the PPA, construction costs went up and prices were fixed. So that created abandonment and cancellation of projects. So a policy implication of our paper is that if you want to preserve the micro cash flow hedging benefits of the PPA, but address this macro downside, you would want to combine PPAs with a state-dependent investment tax credit. And that would help to stabilize private finance and private investment over the cycle. So the key core of our mechanism is a capital structure channel. So in modern finance theory, as I mentioned, the cost of capital is going to depend on whether you use debt or equity to finance your project. And so in the context of renewables, having a fixed price agreement will lead to lower cash flow volatility because you're fixing electricity prices. And that expands bank debt capacity and allows debt to replace equity, which is cheaper. So the two key financial frictions driving our results are that debt is cheaper than equity, and also that banks have risk-based debt limits. So they actually care about the cash flow volatility of the project, even if you fix the expected value of the project. And so obviously PPAs will lower cash flow volatility by fixing prices and therefore lower the cost of capital of the project. So that might be intuitive, but it raises the question of why that same logic doesn't apply for fossil fuels. Why is it the case that we like fixing cash flow volatility for renewables, but not for fossil fuels? Our answer is going to be that actually PPAs are bad for fossil fuels for two reasons. The first is that fuel prices are volatile, and the second is that this production flexibility is ex-ante valuable. So what are the sources of cash flow volatility for renewables versus fossil fuels? If you think about the margin, P minus C, for fossil fuels, you have both volatile electricity prices as well as volatile input costs. So gas prices are also volatile. So if you hedge the P but not the C, you're only partially hedging the cash flow risk. So you're going to leave substantial amount of cash flow risk unhedged if you have a PPA. However, for renewables, you have near zero marginal costs and stable costs. You know, the wind blows for free, the sun shines for free. And so if you hedge the electricity price risks, you hedge nearly all of the cash flow risks of the project. As a result, PPAs will have a significant impact on the cost of capital for renewables, but not so much for fossil fuels from the hedging side. In addition to that, there's this benefit that gas has, which is that they have elastically supplied production, so they can produce more when prices are high. In contrast, renewables produce when the wind is blowing or when the sun is shining. They don't adjust in response to prices. And that fundamental difference in supply elasticities creates an option value for fossil fuels that gets destroyed if you have a PPA. And so to understand the effects of PPA on financing, we interpret the LCOE through the lens of our model, and we find that the effect of a power purchase agreement is equivalent to having a 12% investment tax credit, purely coming from the cost of capital channel. A downside of PPAs, however, is that they introduce exposure to the macro cycle. So we calibrate our model to the 2022 offshore wind crisis, where over $30 billion of US offshore wind projects were canceled. And I want to note this was 2 years before President Trump came into office. So offshore wind was already in crisis even before the new administration. And what happened was that there was inflation that was exacerbated over that period that raised both construction costs and electricity prices. Without a PPA, both rise in tandem with inflation, so you're naturally hedged, and you would be fine. But with the PPA, your construction costs rise, but your price is fixed. And as a result, your project, which previously was profitable, is no longer profitable. And as a result, you saw major abandonment and cancellation of projects. And I have this quote here from the Wall Street Journal and also from the Financial Times, where they actually blame the PPAs for these cancellations and this abandonment. So we consider an optimal policy where we think about the combination of both PPAs as well as a state-dependent investment tax credit that would help to preserve the micro-hedging benefits of PPAs for renewables by expanding debt capacity, while also addressing this macro cycle by having a state-dependent investment tax credit. So to conclude, we introduce a macro corporate finance framework to try to understand the financing side of investment in electricity generation. The key takeaway is that renewables require different financing than conventional fossil fuels because of the nature of the production technology. And moving forward, I just wanted to mention that there are a few trends on the financing side that we should all be concerned about. We've seen that big tech companies are backing away from fairly priced and long duration PPAs. All of this will increase the cost of capital for renewables further. We're seeing increasing private equity ownership of utilities and a decline in federal subsidies, which is going to have an effect on the tax equity market. That's also going to make it harder to finance renewables. So this is all to say that my co-authors and I are interested in understanding how these changing financial conditions will impact the speed and scale of the energy transition. Thanks so much.
All right. So this is joint work with Frank Volek, who is hiding over there. So our motivation is to decarbonize energy supply, we will need vast amounts of low carbon electricity. And as of today, there are only 2 families of technology that can scale up to produce so vast amount of electricity. There is wind and solar on the one hand, and there is nuclear on the other hand. And so in a sense, what we are interested in this paper is to think about whether we have to choose one of the two, or whether we can rely on vast amount of both. And immediately, if you're thinking about the second option, there is a technical issue that arises, which is that the output from wind and solar fluctuates with weather conditions, while nuclear is generally perceived as inflexible. And if that's indeed the case, you have a problem. So to see this, consider an electricity mix that relies on large amount of both nuclear and renewables. So if you consider a given hour, you're going to have some amount of renewables that is available in green at 0 variable cost, and some online capacity of nuclear in orange at a positive variable cost. So if those are the 2 main technologies you have, inevitably there are going to be some hours where demand is going to be low, renewable output is going to be high, such that the sum of available renewable output and online nuclear capacity is going to be higher than demand. And during such hours, 2 cases can arise. Either nuclear is inflexible, in which case you have to use whichever capacity is online. And the only way to balance supply and demand is going to be to curtail renewable.
then market price collapse to zero, and that harms the profitability of both technology. It's unlikely to fly. Or it might be the case that nuclear can be operated flexibly, in which case you can ramp it down, market clear at a positive price, and you don't need to curtail renewables anymore. And so the research question we are interested in this work are one, is the second case possible at scale? Two, if so, what are the associated costs? And three, how far can you go before hitting some strong operating constraints? To answer this question empirically, we leverage the fact that France is already a jurisdiction that essentially relies on nuclear and renewables with about 60 gigawatts of nuclear and as of today, 50 gigawatts of wind and solar. So we start with our first research question. How can nuclear operation adjust to renewable output? To answer this question, we take our motivating graph to the data. So we regress the hourly output of the nuclear fleet on the hourly production of wind and solar on the one hand, and on residual demand on the other hand, so gross consumption adjusted for trade and for must-run generation other than wind and solar. If we don't add any time fixed effect to the regression, we get that a 1 unit increase in the joint production of wind and solar is associated with a 0.8 decrease in the output of nuclear. This substitution, however, could be driven by maintenance decision. Nuclear plant goes offline during the summer when solar output is high. However, we find that this is not the main driver, because when we add day of sample fixed effect to the regression, most of the effect survives. We still have a 0.6 substitution, which means that most of the substitution comes from within day variation in the nuclear output. So concretely, it looks like this. The graph on the right is the hourly operation of a given nuclear unit over a week. And as you can see, you have these large drops in production for a few hours and then back up again. Those drops are called in the industry load following events. And we flag them in the data by finding contiguous hours where we know that the unit is not outage and its output goes below 75% of nameplate capacity. Those are not rare events. When we look at a given year across units, the median unit has about 10 load following events, with a sharp increase in 2024 that we're going to come back to at the end. So since load following happens at scale, we next turn to our second research question, which is, okay, what are some of the associated costs with that? And to answer this question, it's important to have in mind that the relevant time scale to think about the economics of a nuclear power plant is what's called the fuel cycle. So it started when you loaded uranium in your core. From that point onward, you have to produce electricity for 12 to 18 months. You cannot top up fuel in the reactor, and then you shut down for refueling. So once you have that in mind, there's an obvious direct impact of load following, which is whatever energy you don't produce today has to be produced later on. And therefore, mechanically, if you load follow, you increase the duration of your fuel cycle, and therefore you decrease how intensively you can use your assets. So this is a mechanical effect. We can quantify it directly, and we find that it translates typically in a 1 to 2 percentage point decrease in the capacity factor, which is non-negligible, but not as high as we thought it might be. Of course, there can be other indirect impact of load following on a number of margins. We try to get to them by doing simple regression at the fuel cycle level. We find that the most interesting one is a positive correlation with outages, but with simple regression, this relationship is noisy and subject to identification concern. So to dive deeper into this specific relationship, we build in the literature, and in particular, the nice work of Katie Osman, and choose to focus attention on a subset of outages, which are called automatic shutdowns. So a very clearly defined set of outages that you basically cannot hide to the regulator. And what we do is we estimate a proportional hazard model. So we try to estimate the impact of one load following event on the instantaneous probability of a unit experiencing an automatic shutdown, conditional on not having one so far in the cycle. And we find that one additional load following event is associated with a 1% increase in the hazard rate, which is small, but if you remember from the previous graphs, there can be tens of load following events in the fuel cycle, so in cumulative effect, it's actually not negligible. And so finally, our third research question is to understand how far can we go? And so to understand the limit of load following, the most relevant operating constraint is what's called minimum output constraint. So that's the fact that in a given hour, you're not going to be allowed to operate your unit below a certain level. There are two main reasons for that. First, there is a purely engineering constraint, like in any thermal power plant. If you want your machine to be stable, you have to operate above a certain level. So typically 20% of nameplate capacity for nuclear units in France. This is the bottom red line on the graph. We find that this constraint rarely binds, but when it does, it's strongly associated with renewable output, and it seems to be exacerbated by grid constraints. But in any given hour, it might be the case that you are constrained to operate your unit even at a higher level. For example, if your nuclear power plant is needed for grid stability reason, that would correspond to this orange line here. And we find that those dynamic constraints bind much more often, but for reasons that are largely unrelated to renewables, such as fuel management constraints. And so we can use the fact that we observe this minimum output constraint at the unit level to aggregate those at the fleet level to get a sense of, okay, how much downward flexibility remains in my fleet. And going back to our motivating example, we want to understand, we want to test empirically whether it is the case that when we exhaust this flexibility, market prices collapse. This is particularly relevant in France these days because we experienced since 2024 a spike in the occurrence of zero negative prices that are up to 5% of hours. And when we do a simple bin scatter plot where we plot the remaining flexibility on the x-axis against spot prices on y-axis, we see a very strong association. So basically, when you exhaust your flexibility going on the left on the x-axis, day-ahead prices collapse. So to wrap up, we asked three research questions in this paper. First, we want to better understand empirically whether a nuclear unit can not follow. We found that yes. We try to quantify some of the associated economic costs that exist, but are not as usual. We thought they might be, at least for the one we are able to estimate. But we document that there are definitely operating limits and that we are starting to reach them more and more often in France than we used to. So thanks a lot for your attention and happy to chat more over coffee or lunch.
All right, great. So I'm Nathaniel Hickok, and I'm excited to tell you about this project, which is joint work with Aaron Berman and is about environmental regulation with irreversible investments in the setting of the High Plains Aquifer. And the key motivation for this project comes from a relatively simple observation, which is that water is both a critical resource for agricultural production, but also in many settings, a scarce resource. And there are many arid, semi-arid regions around the world where access to groundwater through these underground aquifer resources has enabled large advances in agricultural productivity over especially the past century. But an important consequence of this extensive use of groundwater for irrigation has been that many of these same aquifers are now rapidly being depleted. And of course, aquifers are a common pool resource, so this depletion can have really important consequences for welfare. You know, my water use lowers the water table for other users of the aquifer as well. This increases their future cost of extraction from the aquifer. And this dynamic common pool externality means that without regulation or coordination of some kind, depletion will generally be excessive. It will be above socially optimal. But importantly, this externality is not uniform across the aquifer or over time. It's actually highly heterogeneous. It depends on both local aquifer characteristics, like how fast the water flows through the aquifer, so how fast the aquifer re-equilibrates after pumping, as well as what we're going to call congestion, what I mean by that is really how many local farmers are pumping water in a particular area. And the way you can think about this is that areas with lots of farmers trying to pump water from the aquifer will typically have high externalities as well. What this means is that the first best regulation in the setting looks something like a differentiated water use tax that directly targets this intensive margin of water use. In practice, however, almost no aquifers are regulated on this intensive margin of water use, either through a water use tax or a similar policy. Most aquifers are either entirely unregulated or they're regulated on an entirely different margin, which is the extensive margin of entry into irrigation through, for example, a policy like a uniform entry permitting policy.
And the key reason for this is that groundwater extraction entails very large, irreversible investments, especially in the wells that are required to pump large volumes of water from deep underground and use it for agricultural production. And this means that regulations that operate on this extensive margin of entry rather than the intensive margin of direct water use have at least two potential advantages. The first advantage is really a technological advantage. It's much easier to monitor whether or not you've drilled a large well for groundwater than it is to monitor exactly how much water each individual user is pumping from every individual well across the entire aquifer. And the second potential advantage is really a political advantage, which is that it's costless for incumbent users of the aquifer to regulate on this extensive margin of entry, whereas something like a water use tax is going to be costly for incumbents. So this can make it easier, politically speaking, to implement these kinds of policies. So what do we do in this paper? We ask two questions. First, we ask, how do these two types of instruments, taxes on the intensive margin, entry fees on the extensive margin, compare in both their relative effectiveness in limiting this issue of aquifer depletion and also the potential political support they might engender through who wins or loses under each type of policy. And then we also think carefully about how this comparison might change over time due to the fact that these investments are irreversible, especially more and more fields are becoming incumbent users over time. And again, how should you think about these two types of policies? Well, water use tax, it reduces water use after entry, whereas an entry fee, of course, only affects entry. So conditional on entry, it won't limit water use. A water use tax is costly for incumbents, and entry fee is costless for incumbents. And in the paper, we think very carefully about the case in which, despite the fact that these externalities are really highly heterogeneous, policy might still be uniform. And if policy is uniform, then, well, a uniform water use tax will mean fields internalize something like the average externality. And a uniform entry fee is really going to be something like a screen on productivity. It's going to screen out low productivity users of the aquifer. And this means that the relative welfare of these two types of policies depends critically on the correlation between productivity and externalities. If low productivity users of the aquifer are also the high externality users of the aquifer, then a uniform entry fee can do very well in terms of welfare. In fact, even better than a uniform tax policy because it can screen out those low productivity but high externality users while allowing in the high productivity, low externality users without distorting their water use conditional on entry. And the reverse is true if this correlation is positive. So for our empirical setting in this project, as I mentioned, we're going to study groundwater use for irrigation in the Kansas High Plains aquifer. And we think this is a relatively ideal setting for this question, both because this is an agriculturally important region that covers a significant fraction of US cropland, but also it relies very heavily on groundwater for irrigation and also has experienced significant depletion of this critical aquifer resource. What do we do in the paper? We develop a dynamic equilibrium model of both agricultural production and water use, as well as this investment decision in well drilling. And the model has three really key components. On the intensive margin, fields and farmers are choosing how much water to apply to their crops in order to maximize crop yields, given the costs of water extraction that they face. And their different productivities are going to be what determines both the value of and also their demand for that water. On the extensive margin, fields are choosing whether and when to drill one of these wells for groundwater, and their heterogeneous entry costs, in particular how expensive it is to drill that well, is going to be what determines the timing of that entry decision. And then finally, to measure these externalities from water use, we develop a physically realistic model of groundwater flows through the aquifer that we take from the hydrogeology literature. We then estimate that model using a comprehensive water use and well construction data set that spans more than 60 years, going back to 1959. And then we apply that estimated model to study the counterfactual impacts of these two types of policies, taxes on the intensive margin and entry fees on the extensive margin. And we do that by computing a long-run equilibrium through the end of the century, till 2100. So what are we going to find? We're going to have three key findings, and I'll go through each one. We're going to find first that under the status quo, aquifer depletion will continue rapidly. So the model projects that by 2050, nearly 50% of fields in this region will no longer be able to irrigate. We're also going to find that what existing regulations do exist in this setting are going to be relatively unimpactful. So they're going to be equivalent to an entry fee of approximately $30,000, whereas our model is going to find an optimal entry fee more than an order of magnitude larger, on the order of $1 million, which is about the cost of drilling a well in this setting. As I told you at the beginning, what's going to be key for the empirical welfare trade-off that we're interested in is whether or not productivity and externalities are positively or negatively correlated. And what we're going to find empirically is that they're strongly positively correlated. And this is exactly what I'm showing you in this figure here. So here I'm showing you two gridded maps of the aquifer. In the left panel, I'm showing you productivity across the aquifer. So lighter regions are areas with higher productivity, darker areas are regions with lower productivity. And in the right panel, I'm showing you the same map, except now instead of productivity, I'm showing you externality. So light areas are areas with high externalities, dark areas are areas with low externalities. And what you can see is that the areas that are highly productive are also exactly the same areas that have high externalities as well. It's exactly the southwest region of the aquifer. And the key mechanism that drives this is spatial correlations in productivity, especially soil productivity, which means that the highly productive fields tend to be located close together in highly congested areas of the aquifer that become highly depleted and therefore have high externalities as well. And as a result, we find that even uniform water use taxes increase welfare more than entry-fee policies, although both policies increase welfare more than the status quo by a relatively significant amount. But we find that even though taxes result in a larger aggregate welfare increase, they disproportionately benefit the highly productive fields, which means that entry fees are at least initially preferred by a large majority of fields, almost 2/3 of fields, in the sense that they gain more under these entry fee policies than they do under these water use tax policies. Although this popularity starts to reverse as more of these fields enter and the effectiveness of the entry fee instrument starts to decline. Right, that's all I have. Thank you very much.
Okay, I think my voice is nice and clear. Okay, so hi everyone. Thanks up for being here. And I want to thank the organizers for including our paper in the program. And this is a joint work with Andreas Fischer, Vincenzo Fazon, and Kasper Rosbach. As we all know, cap and trade systems have an important role in the fight against climate change. As of 2025, these systems cover 26% of the global greenhouse gas emissions. And a few countries already announced that, such as Brazil and India, they will also implement cap and trade systems in the coming years. And when we look at the prices in these markets, we see that these prices have been rising. However, the levels of these prices are still not high enough for us to reach net zero goals. And this suggests that these prices are likely to increase in the coming years. And these two facts together motivate this important debate about the consequences of carbon pricing on the, of course, overall economy, but also on labor markets in particular. And we want to contribute to this discussion by studying the labor market effects of an arguably exogenous increase in carbon prices. Of course, here we are interested in both employment effects and effects on wages, but we are also interested in whether this carbon pricing and the increase in carbon prices create winners and losers. And to do so, we use the EU ETS as our main laboratory, and we combine it with detailed population-level data sets from the Netherlands. The shock that we use in the EU ETS is the 2017 reform. In a nutshell, this reform reduced the supply of emission permits significantly. And as you see here on the slide, this has led to a big jump in the carbon prices. The carbon prices reach 30 euros per permit from 5 euros per permit. And in our setting, this is a sizable shock because in our sample, on average, an ETS plant has to surrender 155 permits per worker in a year. And considering that the size of our shock is around 20 euros per permit, this roughly translates into 3,000 additional euros per worker annual cost. And of course, we want to study this reform, but to do so, we need detailed information about the labor markets. Therefore, we go to Statistics Netherlands and we obtain great data sets. For instance, we have information about matched employer-employer data, and we also collect information about individual characteristics such as educational background or plant-level production statistics. But as we all know, almost all exercises on EU ETS suffer from this big identification challenge. That is, The ETS firms are significantly larger than non-ETS firms. They are more profitable, and probably reflecting this, they also pay higher wages. And to account for these differences, we follow the literature and we perform a standard matching procedure. In our procedure, we exactly match on industry, worker gender, and high tenure dummy. And for the remaining continuous variables, we just simply estimate a propensity score. And for each ETS worker, we find the closest non-ETS worker. And after constructing our match sample, then we employ a standard difference and differences design. So without further ado, let me show you what we find when we use the setting. And this is our baseline regression result in which we compare ETS workers to non-ETS workers. And as you see, we do not have any evidence for an adverse effect on ETS workers, at least on average. In fact, our coefficients are positive. However, the magnitudes are pretty small in terms of economic magnitude, and also they are statistically insignificant, except the last one on the employment dummy, but again, it is quite small. However, this lack of average effects on these ETS workers masks two important heterogeneities, and these heterogeneities are the main focus of our paper. The first heterogeneity is about the design of this carbon market. Similar to other cap and trade systems in the EU ETS, some firms receive fewer free permits than the others. And to capture this heterogeneity, we construct this simple variable, which we call permit shortfall, which is a difference between the total emissions a firm emits and minus the free permits. This is the amount of permits an ETS firm has to purchase from the market. And the idea behind this variable is that the negative cash flow shock of this carbon price increase is larger for ETS firms with a larger permit shortfall. And because of this heterogeneity, you can expect that, of course, these firms may share this additional burden with their employees. And indeed, this is what we find in the data. We find that workers who are employed by ETS workers with a 1 standard deviation larger permit shortfall experience a relative 1.8% decline in their hourly wages. And we believe that this result is important for policy discussions because this means that the free permit allocation, which is totally at the hands of policymakers, has a direct effect on wage distribution. The second heterogeneity that we consider here is about the workers' carbon abatement skills. And here the idea is quite intuitive. When you think about it, this shock also increased the value of carbon abatement. Before this shock, being able to keep the emissions 1 unit lower just generated maybe €5 of additional cash net inflow. But after this shock, it increased to €30, right? And depending on the bargaining process between the worker and the firm, these workers with abatement skills may be able to capture a fraction of this additional revenue that they generate. And this may lead to higher wages. And here, to be able to proxy for these abatement skills, we again follow the literature and we use educational background. Namely, we focus on workers with STEM education. And as you see here, we find that these STEM workers enjoy a generous increase in their wages after this price shock, compared to other STEM workers in non-ETS firms. So this is not only a STEM premium, but STEM plus ETS premium. And here we see that these STEM workers almost enjoy a 7% increase in their hourly wages 3 years after this shock. And this is robust also to a within firm comparison. And it is also stronger for STEM workers who have better outside option, which is in line with this wage bargaining story. I think at this point, a fair question would be that, okay, how can we know that these STEM workers really matter for carbon reduction? So to do so, we switch back to a plant level analysis. And here we find that the ETS plants with a 1 standard deviation larger STEM worker ratio before this shock managed to reduce their emissions by around 10% and their energy costs by around 15 to 18% compared to other ETS plants in the same industry and year. So this is a pretty tight comparison. And importantly, when we do the same analysis for other educational background, we do not find such effects. And on top of this, we use a representative survey for the entire Dutch population, so Dutch labor force, and we established that STEM workers indeed have greener occupations compared to other educational background. So let me just briefly conclude by repeating the main message of our paper, that is, rising carbon prices don't have to harm incumbent workers on average, yet market design and worker skills affect who gains and who loses. Thank you.
Great. Thanks everyone for having me here today. I'm very happy to share my work today, which is on levees and levees. So we know that flood protection infrastructure play a critical role for climate adaptation. In the US, for example, flood protection levees protect 22% of county, more than 20 million population, and around 3 trillion property value. And this infrastructure have an average lifespan about 100 years and require costly maintenance throughout this time period to keep it proper functioning. And in the US, levee maintenance is largely local responsibility. So although Army Corps of Engineers may help with the construction, but 80% of the levee systems are maintained by municipalities or special levee districts, which heavily rely on local property tax revenue to finance levee maintenance. And a related fact is that many US levees are already in poor condition due to maintenance deficiency. According to the rating by Army Corps of Engineers, 40% of levees are rated as having unacceptable maintenance quality, meaning that there is one or more items of maintenance deficiencies that could cause a levee to break before reaching a design protection level. And levee failure have severe local economic consequences, as we see in Katrina, Midwest flooding, Pajara flooding, California, just to name a few. So this paper looked at a concerning feedback loop between neighborhood housing value and levee maintenance. Specifically, lower income communities with lower housing value and lower property tax revenue, they have more limited capacity to properly maintain a levee system. And when these levees are not properly maintained, it could increase the risk of levee failure during flood event, which could further reduce housing value as the risk gets capitalized into the housing market, further reduce property tax revenue, and debilitate future maintenance. Thus, this bidirectional causal relationship could form a self-reinforcing feedback loop that continuously enlarge climate and economic inequality and potential economic inefficiency in infrastructure maintenance. So for this paper, I'm going to build a new national database and some identification strategy to help us to separate both of this causal link between within this feedback loop to understand its economic implication. Okay, so for the data, I'm going to measure the designed protection level of each levee, which means this levee is built to protect 100-year flood, 200-year flood, 500-year flood, etc., where a FOIL request to get the levee data used in FEMA Risk Rating 2.0. And for the maintenance quality of each levee system, I use Army Corps of Engineers inspection rating, which give a qualitative rating of each system is of acceptable, minimum acceptable, or unacceptable maintenance quality. And to measure the actual performance of these levees during flood events, not just reported quality, I use multi-satellite imagery. So these figures show example for Hurricane Katrina. The shallow blue area shows flood inundation identified by satellite imagery. Gray area show the levee protected area. And what's shown in red is the overlapping area between flood inundation and levee protection, which suggests potential occurrences of levee failure. So I do this mapping for more than 100 major flood events over the past 2 decades to have a more comprehensive measurement of levee performance. So with this data, one can just link with ACS, census tract level housing value, to do some simple descriptive analysis, and this is what you will find. Like a higher census tract level housing value, a higher likelihood that this census tract is protected by levee with higher protection, design protection standards, which makes sense since housing value actually entered the benefit cost analysis when Army Corps of Engineers designed the standards for the levees. And on the right-hand side, you see that the higher value a neighborhood, the lower probability that this neighborhood is protected by levies with unacceptable maintenance quality. And importantly, who serve as local sponsors seems to play an important role. So this value and maintenance gradient is 3 times steeper under local sponsorship. So when municipality or special districts serve as the local levy sponsor, well, much weaker when we have higher level of government involved in levy maintenance. This suggests that local fiscal capacity likely matters beyond the value of protection. And this relationship from housing value to levy maintenance is not just correlation, it's a causal relationship. So I also tried to build an instrumental variable around 1980s computerization shock, which exogenous increased the housing value growth of certain neighborhoods depending on the predetermined industry composition back in 1950, which is before most levy even got constructed. And we see that a 10% increase in housing value leads to about 1.5 percentage point increase in having levies of acceptable maintenance quality. So there's a causal link there as well. The question is, what happened when levies are not properly maintained? So to look at the reverse causal link from levy maintenance to housing value, I look at historical levy failure events across more than 100 flood events, and I found that conditional on the design protection of the levy system, unacceptable maintenance of the levy significantly increased levy failure risk. One can build a Callaway-Santa Ana approach to look at what happened after levy failure. And what I see is that after the levy failure event, there is about 3% reduction in housing value. And it's pretty persistent and long-lasting in the 10 years post-treatment within the sample. And if one look at extensive levy failure that flooded more than 25% of communities instead of just any levy failure, this risk capitalization increased from 3% to close to 9% and also pretty long-lasting. And the question is whether this is levy failure effect or just flooding effect. So as a comparison, I look at the same storm events that generate those levy failure, same extensive flooding that flooded more than 25% of communities, but for floodplain communities that does not rely on levy for flood protection. And instead of seeing a persistent negative capitalization, I actually see a transitory increase in housing price, which is more aligned with like supply effect outweigh demand and the build back better kind of theory illustrated in some previous studies in the flooding effect as well. So this suggests that levy failure likely have some characteristic that is unique, which could be like the changes in risk perception or a more persistent neighborhood infrastructure decay that actually make the capitalization more negative and long-lasting. Okay, so in a nutshell, I have shown there's a causal link between housing value and levy maintenance quality, which is bidirectional, which could form this feedback loop. It's clearly have inequality implication, but the question is, are those levies worthwhile to maintain to begin with? So I do some back of envelope benefit cost analysis to look at levy maintenance. And I found that on average, a $1 invest in levy maintenance avoids roughly $9 of damages. However, still 35% of the levies with positive NPV are not properly maintained. And if you look at the red curve, which is showing these positive NPV levies under unacceptable maintenance quality, income seems to play a role here. If you look at the bottom income decile, this ratio is about 50% of levy with positive NPV are not properly maintained. But if you go to the top income decile, that ratio is below 20%. And if we restore those levies under maintenance efficiency, it can yield at least like $258 million a year in net efficiency gain. And this is likely an underestimate since I only account for avoided property damages under current climate. There's nothing for mortality, public infrastructure, business disruption, or future climate change impact in this calculation. So it's a pretty conservative estimate. So with that, I will stop here, and I kind of want to add in this evidence, not to suggest that we should finance levies at higher level. It's mainly to kind of add in some discussion about, since we talk about moral hazard, about if we rely on like local financing for adaptation infrastructure, it could create moral hazard issue. But with this work, I hope to kind of generate more discussion surrounding another side of the story, this feedback loop, and see how should we better value and finance adaptation infrastructure. Thank you.
We have lunch. Encourage you to find the presenters and reach out to them, talk to them about their papers. We will be back here at 1:30.
All right, welcome back, everybody. We are very pleased now to have Billy Ferguson present on carbon taxes, carbon border adjustments, and the World Trade Organization.
Awesome. Thank you. I want to thank the organizers for inviting me to speak. I'm going to talk to you about carbon taxes, carbon border adjustments, and the World Trade Organization. This is joint work with Bob Staker, who's here in the back of the room, and also Ali. So the motivation for this is one that everybody in this room should be quite familiar with. Greenhouse gas emissions are a global externality, but taxes are a local policy instrument. And so we know that unilateral climate policy is going to suffer from two key issues. It's going to suffer from free riding by countries that don't have to bear the burden of the tax, and also from carbon leakage. So a potential solution that we have in our literature is the Nordhaus-style climate clubs with really harsh trade penalties for countries that do not adopt some sort of climate policy. Now, while this is something that in principle could create cooperation over climate policy, it's also something that would kind of threaten a lot of the existing trade agreements we have. We could risk kind of blowing up the WTO in the process. And so we want to explore some other solutions that respect all of these existing trade agreements. And so to address free riding, you could imagine transfers being made between countries, but in particular, something you could do that doesn't require transfers are country-specific taxes. So on that front, we'll look there. And then regarding carbon leakage, you could have carbon border adjustments, which are tariffs that sort of respond to the climate policies and the emissions of different countries. And so the key question today for our presentation is, can carbon taxes and associated CBAs respect existing trade agreements while significantly reducing pollution from carbon emissions? And so to answer this question, we're going to build and estimate a quantitative trade and emissions model to simulate a bunch of different policy outcomes. And I'm going to give you a bit of a laundry list here, although I'll hopefully contain it in a way that makes sense, of all the different kind of things that we're going to be looking at. So we're going to be looking at a world in which carbon taxes are set non-cooperatively and in Nash equilibrium versus a world in which we're cooperating in a club to set these taxes. We'll look at uniform taxes versus country-specific taxes. For the CBAs, we'll look at ones that are designed based on the domestic emissions of the importing country versus the emissions of the exporting countries that you're importing from. We'll look at what these CBAs look like when you allow and do not allow for export rebates for your domestic exporters. We'll consider these direct and indirect emissions. Do you tax, or do you include tariffs or tax for the direct fuel consumption and the emissions of that product at the end versus the whole supply chain of emissions to produce the product? And then lastly, we'll consider agricultural exemption, which is often true in real life, even though agriculture makes up a large share of global emissions. So just to preview some of the main results before we get going, we're going to see that the first best sees about a 50% decrease in emissions and over a 5% increase in global welfare, according to our objective function. The non-cooperative carbon taxes we see in Nash equilibrium are significantly lower, and so this really limits our ability to have climate action. We'll find that satisfying participation constraints in a cooperative world, if you want everybody to collaborate, is going to require massive transfers on the order of 5 to 10% of many of these countries' GDP. But we'll also find that country-specific taxes are super key to incentivizing participation and kind of can replace the need for transfers. We'll discuss one particular CBA design that will enable international cost shifting that will actually help under non-cooperation. And so the big picture thing that we see is that the optimal policies that we should be pursuing, the optimal design of the CBAs, will change as the level of cooperation changes over climate policy. And I'll show you exactly in what way as we make our way through. So there's, a very big literature on international trade and climate policy. There's also a very active literature currently on carbon border adjustments and climate agreements. I highlight 4 papers here at the end of this CBA section that I think are very similar to the kinds of things that we're thinking about, in particular 2 of Farid's papers here. And I think to differentiate what we do in this paper versus what I see in these recent papers is this emphasis on, how do we avoid blowing up the WTO? How do we not create absolute instability about all the existing agreements that we have? So we're not going to be looking at any of these tariff punishments. And in particular, when we're thinking about different types of carbon border adjustments, we're not actually going to allow countries to have full flexibility over any type of adjustment. We're going to, in principle, come up with two designs that are specifically based in theory and based on emissions so that there isn't this absolute flexibility that can concern members of the WTO. We're also going to emphasize the power of country-specific taxes, which we think is often ignored in this literature, and we'll show this evolving CBA design as cooperation changes. And then I think I've said this before, but I think it's important that we incorporate these agricultural emissions, which are really important to solving this problem. So the roadmap, I'm going to talk through just a brief framework and a little background on carbon taxes and carbon border adjustments. I'll tell you about the data we're using. I'll show you the model and estimation, and then we'll get to the results, where the results are going to kind of be organized in three sections. There's the first, what would the global social planner do if they had power over everything? There's the second, which is where are we kind of at now because we have non-cooperative climate policy. And then lastly, how would cooperative climate clubs work that both leverage these country-specific taxes under the varying kinds of participation constraints of all the countries involved. So just first on background. So again, the canonical solution here is that we would like some sort of global uniform Pigouvian tax on emissions set to equal the marginal cost of emissions. And so absent global cooperation, what happens is countries are going to start pursuing their own unilateral policies. And these policies can take different forms that have serious consequences for the performance of policy. So on the one hand, you have production taxes. What these will end up doing, so you just have to levy the tax on the producers at the upstream in the economy. What this will end up doing is it'll put upward pressure on global prices as the supply goes down in the country that passes the policy. And so then we get this carbon leakage as the rest of the world produces more to meet that raising price. If instead we were able to tax consumption, so the consumers that are consuming the objects are getting taxed for the emissions that went into making that, that would actually have the opposite effect. So you'd get this downward pressure on global prices. What this means is it incentivizes everybody in the world to emit less, because there's this depressed demand. But despite the fact that we don't like production taxes for this reason, for this leakage concern, in real life, it's easier to administer them, and it's just what we see day to day. And so we're kind of in a world where we're going to have these production carbon taxes. And so what this ultimately means for non-cooperative unilateral climate policy is that there's two hurdles. There's one thing, which is that when a country decides on their unilateral tax on carbon, they are not going to internalize the positive externality that they're having necessarily on the rest of the world. And so there's these uninternalized positive climate spillovers for the rest of the world when countries are choosing these taxes. And then the second thing is that these production taxes are going to incentivize carbon leakage. So this is what brings us to what a lot of the current policy debate is right now. In principle, you could imagine that tariffs could be designed based on the carbon intensity of producing countries and on the carbon taxes they have to try and address the second concern, which is the leakage. So the EU has implemented a carbon tax, or CBAM, as an through the ETS program, it is experimenting with carbon border adjustments. And I think it's important to note that these carbon border adjustments are pretty controversial, and they're controversial legally within the WTO. And so we're going to look at two broad classes of CBA design that have a bunch of different features that can allow us to explore how these design choices will perform in the real world, and also how those relate to the types of debates happening within the WTO. So the first CBA, we're just going to call it traditional CBA. This is the one that's most closely resembles what CBAM is currently doing. And the kind of theory behind this design is it's going to be a border adjustment that converts a production tax into a consumption tax. So if you remember what I said earlier, these consumption taxes have this nice feature that you don't get that leakage. You'd actually get negative leakage. And so how do we use tariffs to just translate these production taxes, which are easier to administer, into a consumption tax? So the way this works is if you're the EU and you have some carbon tax and you import from a country that does not have a carbon tax, upon entry, you tack onto your tariff what you would have charged that producer if they had produced in your borders. So you just apply the tax that you have domestically to imports abroad. And if other countries adopt a carbon tax, you credit them for all of the tax that they have paid, and you just charge them the extra that they would have had to pay had they been within your border. An important feature of this traditional CBA is that it's going to adapt to the country that you're importing from based on the emissions intensity of that country. So if you import steel from Kazakhstan versus steel from China, it's going to get you a different tax given your estimate of the emissions intensity of that production there. So this is one of the features that is controversial within the WTO. So Russia has actually raised a formal complaint that's being dealt with right now. do these types of adjustments based on the country amount to discrimination in a way that violates the MFN agreement within the WTO? So that is a controversial piece of this traditional CBA. The other piece that's important that will make this conversion from a production to a consumption tax full is that if your domestic producers export to other countries, then they should get a credit for the taxes that they would have had to pay internally. What this means is, if the US imports something from the EU, they shouldn't have to pay the EU tax because it's not the EU citizens that are consuming it. So this preserves this idea that we're fully translating this production tax to a consumption tax. I will say that these rebates are also controversial within the WTO. It's not clear that these rebates are a border adjustable rebate, and so that is still up for debate within the WTO as well. The second design we'll consider is what we're going to call a leakage neutral CBA. And so the theory behind this one is, the issue here is that our domestic producers are now facing higher costs, and we would just like for that product, if we import it, to go up in cost the same amount it went up for our domestic producers. So instead of thinking in terms of, how do we apply our carbon tax to other countries exactly, we're going to say, okay, now that, I make a car in the EU and it requires that I use steel and electricity and all of these other inputs. So to make a car in the EU, it's going to cost me some amount more. For all cars I'm going to import, I'm going to charge exactly that much more. So this is what we call a leakage neutral CBA because it's motivated by this idea that you want the world to face the increase in price that your domestic producers face. So this CBA is going to include both direct and indirect emissions in its construction. And a nice feature of this CBA is it will not depend on whatever country you're importing from, because the idea is you just want to increase the cost by how much your domestic producers had their cost increase. And so this is something that would satisfy, this concern about discriminatory CBAs. This design is also going to be endowed with this rebate for exports. But we're interested here in if this rebate's really necessary. And so we're going to consider both designs without a rebate for exports. And this is particularly important to consider given that the EU is now exploring adding this rebate to their CBAM design. So I'm going to tell you some more about the data. We're going to compile a cross-section of trade and emissions data in 2018. The trade data is going to come from some standard sources. If you've ever worked with trade data before, we're going to have the OECD IC input-output tables with trade floors, sectoral expenditure shares, and value added. We're also going to have this UN data on population, tariffs, and price levels between countries. On the emissions side, we're going to combine 3 different sources of data. This first source is what's often used in a lot of these papers. The OECD has data on direct emissions from fuel combustion by sector, but we're going to supplement this data with FAO data on agricultural emissions and also EDGAR data on industrial, chemical, and fugitive emissions. And so it's going to be a more comprehensive picture of all of the emissions across sectors. So not just carbon emissions, but you should think about a bunch of other greenhouse gas emissions as well. So just to ground us and where this data gets us, right here on the right, I'm plotting for you the share of global emissions by country. Sort of the big 4 make up over half of the emissions in the world. That includes China, the US, the EU, and India. So we'll be kind of thinking about these countries more today as we look through some of the results. We can also look at the share of emissions by sector. Energy we know is the largest emitter. It's nearly 30% of global emissions, but I'm going to highlight here that agricultural emissions are a quarter of emissions as well. And so this is a really crucial part of the story, and it's important that we include them in these types of papers. So the model I'm going to show you is going to be a pretty standard trade model. We're not going to have a lot of bells and whistles. It's not going to be too different than stuff you'd see in a textbook. It's going to be an Armington model of trade with production emissions. A lot of it's going to be based almost directly off of Joe's paper on the environmental bias of trade policy. Demand in this paper, we're going to have that representative households have Cobb-Douglas utility across sectors, and they're going to CES substitute across country varieties within that sector. For production, we're going to have Cobb-Douglas technology that's going to use labor and intermediate inputs. We're going to have country sector specific productivity and also country sector specific emissions based on that data that we have. Carbon taxes in our model are actually going to enter a specific per unit production cost, which is different than you'll see in a lot of this paper. The cost of this modeling assumption is that we do not get to do any sort of exact hat algebra. So we have to simulate everything through the magic machine. But it does mean that we get to represent this in a way that's more representative of what we see in real life of this kind of per quantity carbon tax and carbon border adjustment. Trade costs in this model are going to include the classic iceberg trade costs. We're going to include the tariffs that were from 2018, which we're going to leave fixed throughout a lot of this exploration. And it's going to include these carbon border adjustments. Equilibrium here is just going to be market clearing with the classic gravity-determined bilateral trade flows. And we're going to represent welfare in this way. So for the social planner, global social welfare is going to be the weighted sum of country real income net of global emissions damages, which is what you're seeing here. This delta I is going to be the per country cost of carbon, and this eta I is going to be a welfare weight that the social planner puts on each country. For estimation, this is going to end up being a model with 19 country regions and 17 sectors, 4 of which are non-traded. And so the first step is to get all of our baseline trade parameters. And so we're going to estimate the model first where there's no carbon policy at all. We have some new results where we include the 2018 taxes that we have. It doesn't change much. They're not cleaned up enough for the presentation. Offline, we're just going to set some parameters. We're going to set the substitution elasticity as 6. The expenditure shares and the input-output shares are just coming directly from the data, and those are set offline. The estimated parameters are going to be the iceberg trade costs and these country sector productivities. So we're going to target moments here, which are the bilateral trade shares and the relative price levels that we observe in the data. We're going to pick all of our parameters so we match those well, where we do estimation by GMM, subject to market clearing, with wages being set to the observed labor value added that we have from our data. So once we have all those parameters, we have our laboratory that we can experiment with. And once we have all those parameters, we can then calibrate the carbon part of the model. We're going to calibrate emissions intensity, carbon damages, and welfare weights once we have that set. The emissions intensity is just going to be the emissions we observe in that sector divided by the model's quantity of output. The global carbon damages here is going to be very low to everybody in this room, are currently set to $51 per ton, which were the old Biden administration estimates. This is active work right now to raise this up to what we think the current estimates are. For now, the country carbon damages are going to be proportional to each country's share of global GDP. And then the welfare weights are going to be chosen so that the social planner, if they could choose transfers between countries in this baseline equilibrium, would choose transfers of 0. So we're going to eliminate this redistributive desire by the social planner by choosing those welfare rates appropriately. So with all of that, we can start walking through all the counterfactual results here. So the social planner is first best. I'm showing you in this table 2 worlds, one in which all sectors face a carbon tax and one in which agriculture is exempt. I'm going to show you the uniform carbon tax that the social planner would pick, what that does to total relative welfare as a % change from baseline, and what that does to relative emissions. The social planner chooses around a $51 tax. The first best sees large welfare gains and a reduction in emissions, and I think this is a point that we want to make. Exempting agriculture reduces the benefits by a third. So it's really important from the social planner's perspective. If they had control of everything, agriculture is a very, very important part of the story. What we then do is given each country's objective function, which is the thing that the social planner sums up with those welfare weights, we're going to let every country best respond with their optimal policy, optimal tax, under different carbon border adjustment designs. And so we're going to compute in this non-cooperative regime the best response carbon taxes. What you'll see with no carbon border adjustments, the taxes drop significantly from first best. Before, where we had this uniform tax of $51, we now have a tax a little bit below $4 on average, with some variation between countries. And while taxes vary between CBA designs, you get a little bit of motion there. You can see that the tax increases by about $3 under the traditional CBA design. The outcomes don't really change that much. The effect on emissions is pretty low. The effect on welfare is almost indistinguishable. So part of how I'm interpreting these results is it looks like free riding is really dominating the problem with non-cooperative taxes. It's not really the carbon leakage that's dominating why we're getting such low taxes here. But something that we haven't explored in this table is what it would mean if we if we got rid of the rebate. So right now, every country is rebating any of their exports of the carbon tax they apply. If you have no export rebate, you'll notice a little bit of motion on the traditional CBA. So here it is right now, we get this 10% decrease in emissions. Now we get this an additional 4%, this 14% decrease in emissions. And so removing this export rebate, what it allowed us to do is it allowed countries to cost shift some of the burden of that tax onto other countries in the world. And then it leads to this sort of terms of trade improvement that allows countries to raise their carbon taxes. And this is interesting because, typically as economists, we would like this idea that you get rid of the export rebate. It's sort of the like responsible way to manage all of these distortions. And I think the logic here is that it's just, you know, the theory of second best. And so in this non-cooperative regime, you have this uninternalized positive spillover. And so all of the countries are choosing taxes that are far too low. And in this really inefficient regime, it helps to allow countries to capture some of these positive externalities by cost shifting their tax onto the other ones. And so if you remember, you know, there are two reasons that unilateral climate policy suffers. The first was that there's this positive externality that's not internalized. The second is the carbon leakage. What we're finding is that this traditional CBA without the export rebate is actually able to hit both instead of just the carbon leakage reason. You know, it's a really, really crude way to get some sort of transfer for these positive spillovers. You know, ideally you could transfer exactly if you had cooperation, but in a non-cooperative environment, we're crudely approximating some sort of compensation for these positive spillovers, which we think is a pretty interesting result in this paper, especially in the context where the EU is considering adding in export rebates right now, where they currently don't exist. The next thing we consider is a world where we all get together and cooperate, and each country comes to the table with some sort of participation constraint. We're going to consider different forms of taxes and whether or not transfers are available to the club. And so you'll see here, we're going to consider uniform taxes and then country-specific taxes with transfers and without transfers for these uniform taxes. You know, with the uniform tax and transfers, we can get very close to that. We can get basically to that first best that we talked about before, and we get a reduction in emissions by about 50%. But as I mentioned in the introduction, this requires transfers on the order of 5 to 10% of many of these countries' GDP. We just know that's not going to happen. If you don't have access to these transfers and you allow the social planner to pass their best uniform tax, there's a huge reduction in the performance of the tax. The tax drops by quite a bit and the relative emissions go down by quite a bit. However, if you allow the social planner to set a tax for each country, what you're able to do is, as if you had transfers, you're able to distribute the gains to each country while satisfying all of their participation constraints, and you're able to do this without transfers. And I forgot to mention this before, the participation constraint in this model is every country has a veto power. So if they say no, it all blows up and there's no climate policy at all. So that's the participation constraint for these numbers. I don't show you the results here, but once we've cooperated on having a really good tax, the CBAs are kind of pointless at this point. You could imagine that because we're having country-specific taxes, there could maybe be some room for transferring surplus through the CBA design if you don't have these transfers, access to actual transfers. We find that they really don't help at all. And so one of the points we're seeing here is that, you know, in where we had this inefficiently low regime, low tax regime, this traditional CBA without the export was a way to kind of get cooperation moving. Once you've got cooperation on taxes, we don't really need to consider these CBA designs anymore. The next thing we're going to do is vary the type of participation constraint we're considering. So before, the idea was that each country had this veto power, they would totally blow up the agreement. We're now going to consider a free rider participation constraint, where one country could deviate. What they could do then is they could get the welfare that they would get competing in Nash with the club, who is all coordinating. And so this is going to be a much higher participation constraint for this free riding country. We're going to compute these cooperative taxes where the free rider gets this special constraint, and then everybody else still has the baseline constraint of this veto power. And I think this is one of the important results here. If you do not have access to transfers, for the three countries I'm going to show you today, there does not exist a feasible uniform tax for the club that can satisfy all these constraints. And so in this sense, we almost view country-specific taxes as necessary once you start considering these types of free riding constraints, and if you believe transfers won't happen. We do this here. I'm going to show you three countries that we consider as free riders. You'll see that the average club tax has to go up from the $51. It goes up to 55, 60, and 50 for Indonesia, China, and USA, respectively. And you'll see that the free rider taxes are much lower than what that club gets. But the main idea that we really want to take away from this is that these country-specific taxes are necessary, and they actually end up enabling performance near first best, even when you have countries wanting to free ride. And so I'm going to go ahead and conclude. This is a quantitative analysis of carbon tax cooperation and WTO-compatible CBA design. In particular, focusing on these sort of two theory-motivated designs for the CBA, we're thinking that you're creating a menu that there's way more chance of collaboration on than allowing just kind of this free anybody choose whatever sort of tariff they want to be applied at the border. And I think there's three key takeaways that I want you all to have from this presentation. One, country-specific carbon taxes substantially improve the scope for international cooperation. Part of why we think this is interesting is a lot of the policy discussion that motivates country-specific taxes appeals to some sort of ethical argument or to historical emissions that have been applied that got us in this situation. We think these results are interesting because they show this is just a very practical argument to make international cooperation feasible. The second thing I want you to take away is this intuition from the theory of second best, that allowing these export rebates, which in principle seem like a good idea, they make the economist brain really happy, they could actually end up depressing the non-cooperative taxes and harm global welfare because this lack of a rebate is allowing for cost shifting. It's allowing these countries to internalize some kind of positive spillover from the climate policies they take. And then lastly, summarizing all of this together, we find that this optimal policy is going to evolve with cooperation. In the non-cooperative environment, Nash taxes are too low. This traditional CBA is going to help you out a little bit without the rebate. And I didn't show you this, but taxing agriculture does nothing really for you in the non-cooperative equilibrium. But in the cooperative equilibrium, the country-specific taxes are key, CBAs are relevant, and then suddenly taxing agriculture is a serious, serious concern. So thank you all. I'm excited to hear all your comments.
And discussing the paper is Ulrich Wagner.
Yeah, thank you, Billy, for a very clear presentation. Thanks to the organizers for giving me the chance to discuss it. So this paper sets out to answer two research questions. First, does combining carbon taxes with WTO compliant carbon border adjustments lead to more global CO2 abatement? And second, should a climate club adopt country-specific carbon taxes instead of a uniform one? And so to answer these questions, the authors calibrate a general equilibrium model of trade and emissions in which countries can choose carbon taxes, trade policies, and transfers. Now, in choosing carbon taxes, there's a choice between a uniform and country-specific taxes. In choosing the carbon border adjustments, there are choices between applying those adjustments to imports and exports versus to imports only. And also to levy the carbon border adjustments on the emissions embedded in trade flows or the emissions displaced by trade flows. And then, as Billy has shown, there's different ways of different equilibria that are of concern to us, the social planner solution, the climate club, or the non-cooperative Nash outcome. So as we would expect in this setting with the global public good, there are large gains to cooperation, but not much of that is realized if countries are left to their own devices. The participation constraints or the free riding incentives are very strong. And then the authors show that the carbon border adjustments themselves, they do help deter leakage, but they don't solve the cooperation issue. So this is going against sort of the Nordhaus idea. Of course, Nordhaus didn't care so much about WTO compliance in this setting, but there's a tension here if you consider the viability of climate clubs that really the carbon border adjustments by themselves won't get us all the way to a club. So the club that you guys consider is the grand coalition, as people in the IEA literature would call it, or in game theory. And so a club that would set a uniform carbon tax, as you show, sets that tax at a level that is way too low. And that connects very nicely to that IEA literature in which that would be called a broad but shallow treaty. Okay. The most remarkable and surprising result to me was that when you allow the club to set country-specific carbon taxes, then the club actually achieves nearly efficient abatement and welfare outcomes. So there's a lot to like about this paper. First of all, it's super policy relevant. I think the single most issue right now, if we look at the state of climate policy, is to deter leakage and then maybe tackle the free riding issue again. But leakage is absolutely key. And so what you bring to the table here is a very sophisticated model. It's general equilibrium. It has a very good sectoral and geographic resolution. You have the input-output linkages in the global value chains, which matter a lot for assessing the effects of carbon taxes on trade and also of carbon border adjustments. As you've shown, you have a very careful calibration of CO2 emissions data, so that's very important. Also, the focus on agriculture, which you have made very clear that is something that not a lot of papers do. So the key innovations here in the analysis are to have the Climate Club actually choose non-uniform carbon taxes. So something, perhaps an old idea that is recently getting attention. And also in the policy world with the Open Coalition for Carbon Compliance Markets that also considers a tiered carbon pricing regime. So definitely interesting to look into this. And then also, of course, we don't want to destroy the WTO to save the climate, or maybe we want to, but not today. And so here to preserve market access is for third countries is a good idea to help maintain the WTO. So it's a well-written paper with a rich set of interesting results. So I have two comments here. So the stability of the Climate Club, you mentioned it, it's based on a veto participation constraint. So what this does is if any one country vetoes the Climate Club, the entire club will unravel. And as a consequence, all countries revert to a world without neither carbon taxes nor carbon border adjustments. So the veto effectively takes away all the mitigation benefits for everyone. Free riding is assumed to be impossible in that world because there's nothing left to free ride on. And also for those countries who called upon, who are compliant, once the veto is raised, then it's impossible for them to renegotiate to a smaller club. Okay, and so this, all in all, this is a package of very harsh sanctions that sustain a lot of cooperation. But it's a collective punishment that may not be credible. It's not self-enforcing for the countries called up to punish the free rider to do that, or the veto country. And then the free riding participation constraint does relax that in the sense that you allow Nash behavior for the defecting country, but you maintain the veto participation constraint for all the other countries. So I would encourage you to limit the reach of this veto participation constraint as far as possible. I realize it may be prohibitive to compute something like a coalition-proof equilibrium here, but you could start not with the grand coalition, but with a smaller club of countries who are plausibly committed to going forward with ambitious climate policy, and then allow more free riding and see who can be pulled in to this club by using these different instruments. Another point in that direction would be to allow countries to revert to their Nash carbon taxes when the cooperation breaks down. I think that would be a realistic response. And I didn't quite get the idea why you don't want to use CBAs at all against free riding. I mean, if CBAs are part of a climate club, why should they not be part of the non-cooperative regime that is used to punish the deviation? The second comment concerns your leakage neutralizing MFN carbon border adjustment. It's an alternative to CBAM. You've explained that CBAM is discriminatory and reduces market access for the carbon intensive producers. So the idea is design a carbon border adjustment that mitigates leakage, but doesn't inherit these undesirable features. So the way you achieve it is to impose a tariff that imposes the carbon cost as if the good was produced in the importing country with the importing country's carbon price and the importing country's carbon intensity. So as you acknowledge in the paper, this tariff mitigates leakage, but it doesn't entirely neutralize it. So it shows in one of the tables that there's still a fair amount of leakage, and that's a problem because the more leakage you have, the weaker the incentives for the other countries to raise their carbon taxes. So I think you can do something about it. You have a model, and that model should allow you to compute an adjustment that fully offsets carbon leakage. So in work with my co-authors, we have derived such a leakage border adjustment mechanism. And we show that it's also non-discriminatory and preserves market access. So it would be something that you might consider to include in your analysis. Yeah, I have just a bunch of further thoughts. So the cost shifting CBAs. So it's exciting to think about how this can encourage participation or how ambition in terms of climate policy. But I think as a political reality, we see that firms who suffer producer surplus loss, they're very up in arms against it, and they've lobbied very successfully. Just a few days ago, the EU confirmed free allocation beyond 2030. And so that amounts, economically speaking, to a production tax, so production subsidy, excuse me. So maybe that's another instrument you want to include in the analysis, because that seems to be a feature that remains to stay. Then the country-specific carbon taxes, what they break with the idea of having efficient abatement, right? And so I was surprised to see that the welfare, I would have expected that to have a depressing effect on welfare, but that didn't seem to be the case, because you can achieve a distributional goal that offsets that negative welfare effect. So I would like to have seen some more transparency about this trade-off. How sensitive is it to welfare weights? And my last comment is very simple. Please do include a table with the tariffs, the magnitude of the tariffs and the export subsidies. Thank you very much.
All right, thank you. So maybe Billy can respond, and we'll ask folks with questions again to line up.
So yeah, so we've thought about, having a more complicated sort of combinatorial, figuring out the right club, who's going to participate when. In principle, we can do all of those things. Right now, we are thinking that we're just kind of like bookending these extreme examples. One where you just have this kind of veto power constraint, where you have like a low threat welfare, and then one where you have the free riding one, which is sort of the extreme good one. Because as more countries start to drop out of the club, this free riding welfare that country would get goes down as well. So there's kind of like the extreme ends of the welfare that a country could get is when they're the only free rider and when they have this veto constraint. But I think we can do more there. One thing we've considered is just identifying which countries we think would be the ones that actually have veto power and which ones don't, and then kind of looking in that world. So that's a point that's well taken, and we should look at that. We have looked at the CBAs in just the single free riding case, and they don't really help much. They do end up getting that the free riding countries, so like China or Indonesia and those examples I gave, will pass a higher tax due to the CBA, but they don't actually move the welfare margin as much as we expected. So we didn't present them here, but that's another thing that we can see. And then, yeah, the cost shifting, we recognize in the paper that, for political reasons, you might need to provide these types of export rebates, but we think it's pretty important to kind of nail and maybe make loud, if we really believe these results, that could make things worse in terms of this unilateral policy, the non-cooperative environment. So thank you for all your comments. I'm excited to talk more about your paper on the leakage neutralizing, or the one that actually neutralizes leakage, CBA. So Hans, you want to go?
I think that countries currently now have different carbon prices than might be predicted by your model in some baseline equilibrium. The EU is higher, the US is lower, et cetera. And I guess I was wondering if it's worth inferring generic residuals or different country-specific views on the SCC or altruism, and then sort of using those in the counterfactuals as well.
Yeah, we've considered doing this. So the hard part is that, the Nash equilibrium that we can get in our model, or even just like using the observed taxes that we had in 2018, you can imagine picking parameters that each country has sort of directly on emissions. And so getting it that the Nash equilibrium matches what we observe in 2018 for the carbon taxes. We explored this a little bit. And the hard part is that it's just like it's hard to understand what the welfare function of these countries are that can actually rationalize what we're seeing and what you can put the parameter on. So it's a difficulty that we're having right now. We feel like a lot of the main results don't critically depend on the fact that's true, that the non-cooperative equilibrium from our model doesn't match the 2018 one. But it's something we've considered. If you have any good ideas, we should talk more.
Yeah, super interesting paper. One question, one comment. So you have this kind of WTO compliant CBA, and to my mind, it does two things. One is it's non-discriminatory, but then it also adds the indirect emissions. And I guess I see that as kind of a unfair critique of the existing CBAM, because the existing CBAM only applies to like these very upstream industries. And who knows, as it expands, it probably will include the indirect emissions as well as the direct. So I wonder if you could kind of isolate out the non-discriminatory part of your second CBA.
Yeah. Comment too. Yeah.
And then the comment, so Ulrich referred to the Open Coalition on Compliance Carbon Markets. We worked very closely with Brazilians to get that off the ground. And I will say that the graduated, so we laid out this idea of a graduated carbon price, and that was very, very important to most of the low and middle income countries that we spoke to. So super happy to see that this is part of it. I guess I would point to two additional things that I think influence the ability of that limited coalition but hopefully growing coalition to come together. One thing, like when China expressed interest, we've heard from several other countries that like they knew that it was going to be something real. Like China being part of the coalition was important. And so I don't know, when you go to the like dynamic version of putting the coalition together, you might want to wait having the largest emitter in the country or in the world in the coalition. That said, I think China joined for reasons that are outside your model, which is they've invested so heavily in the clean energy technology. Like they just want to sell us all electrolyzers and solar panels. But I don't think that's reflected in your trade model. So yeah.
Yeah. Well, it's encouraging to hear that there is this sort of support for these type of graduated carbon taxes. On the point about the non-discriminatory, in an earlier version of this paper, we actually didn't include all of these indirect emissions in this alternative tax that was non-discriminatory, and we just applied whatever your emissions are in your country, direct emissions. And so basically what happens when you get that is it's something that just performs like worse than the traditional CBA, which already doesn't do much better in the non-cooperative environment. And so the idea behind the leakage neutral one was like some sort of theory that can inform, what would actually neutralize the increase in cost. But we've explored that and we didn't see a bunch of interesting stuff on that front.
But then that's encouraging for the existing CBA.
Yeah, that's true.
It starts going up the value chain.
Yeah, and I will note that EU has noted, I don't know if this is happening yet, but they're going to start including indirect electricity emissions in the CBAM, or at least they're making moves to try and do that. So they're going to slowly start adding these indirect things over time.
I wonder if you've thought about accounting for trade policy retaliation and whether some of these policies are better at preventing a trade war. You have this elegant analysis of cooperative versus non-cooperative environmental policy. And then as I understand, trade policy is held fixed. And I could appreciate the rationale for tariffs, but there's a lot of non-tariff trade policies, like when the EU added international airlines to the ETS a while ago, Russia canceled Airbus orders and China denied flyover rights to EU airlines. And there's this old concern with linking trade policy with other domains that you might achieve cooperation in both, but you might also decrease it, and finding what's robust to that kind of non-cooperative trade war could be informative.
Yeah, I like this question because that was the original idea for this paper. So both Bob and Ali have this paper on Nash and Nash tariff bargaining and what, rationalizing where those tariffs come from. And you could imagine nesting this inside of that and seeing what types of CBA policies are robust to that kind of like second stage where tariffs get renegotiated. We ended up thinking we had some stuff to say before we did something like that, but it's on the docket.
I was very interested in this idea that optimal policy evolves with cooperation and coordination. I guess first a minor point, somehow the word evoked for me evolves over time. And then I went down this like dynamic adventures, thinking about dynamic supply or dynamic negotiations over time. I don't think you're necessarily going in that direction, but that got me thinking about commitment versus non-commitment, which I think does relate to Ulrich's point, for example, about this veto participation constraint, where if one country vetoes, everyone drops out. Just like European policy has a long view and has commitment towards climate policy, maybe there's some value to knowing that the EU will always act no matter what, even if someone vetoes. That would be kind of the analogy of this value of commitment in this, even in the static sense.
Yeah, I think that's a cool idea. And I think it also relates to sort of the construction of a club. So you could imagine a version of the paper that's sort of like sequentially adding players that have different levels of commitment and then seeing how that relates to these veto and free rhetoric. I think that's a really cool idea. I mean, we have the machinery to explore something like that. It's just, will the computer cluster survive all of the running?
That was an awesome paper. Thank you. So if I understand correctly, you're holding fixed the emissions intensity at the country sector level. And so that seems appropriate for thinking about short-run participation constraints and cooperation. But I'm wondering specifically about how to think about that in the context of the evaluation of the traditional CBAM versus the non-discriminatory CBAM, because it would seem like that could potentially matter in the evaluation of those two different instruments.
Yeah, and so what you're thinking is that the traditional CBA, because it depends on the emissions intensity of the country, if
it gives a greater
it incentivizes, yeah.
Exactly.
So one thing we've considered, which we haven't done yet, is the energy sector right now. You know, you could imagine within the energy sector having like clean and dirty, a substitution between them, just kind of nest that in, and then we could get that dimension. We don't have that yet, but I think in principle we could throw that in, and then the traditional would perform even better relative to the leakage neutral design.
So I think there are two features that could have important implications for the results. The first is abatement. The discussion that we've been having so far when we're talking about abatement is just about leveling the playing field and reallocating output between producers, not of any producers actually reducing their emissions. And the whole motivation of adopting a carbon tax is to encourage exactly that. So I think thinking about which countries are actually adopting a carbon price and what emissions reductions you would get from firms having an incentive to abate would have an important impact on the conclusions. And then the second, and it's related to that, is of heterogeneity, that when you're having unilateral policies like this, you have to think about firms in countries who are being taxed. You're going to have selection into who's deciding to sell into the export markets and who's going to stick behind and serve the untaxed domestic markets.
Yeah. So, I mean, the first point I think is related to incorporating this substitution between clean and dirty within the energy sector. We haven't thought a lot about the second point. And so we should talk a little bit more after about that. Yeah.
My question is related to others that were previously asked about there were papers that showed the intra-country heterogeneity in carbon intensity, especially for steel, for instance. And so, the trade models never take into account the fact that, for instance, in China or in the country, you could have like shuffling, different shuffling, and that's a really important question for instance, in the debate about CBAM and the European and the EU. So, what's your views on that, and what do you see how it could be taken into account in trade model in the future?
I mean, one thing that I'm really thinking about right now is that within country heterogeneity and emissions intensity is going to be incredibly relevant for this cost shifting CPA design. If like the fact that you keep it domestically versus you become an exporter, which market you sell in, how is that related to your firm's emissions intensity? I'm thinking that that's going to be actually really crucial. I don't know right now how we'd be able to like very readily incorporate that in the model that we have. I know that there are models that have started to, you can incorporate heterogeneity and productivity. So in principle, you could have some sort of correlation of productivity with emissions, and you could probably pin this down. But we haven't thought a lot about that yet.
All right. Thank you so much.
Thanks.
And now we have someone, talking about green industrial policy in a globalized economy.
Okay, thank you for having me. Thank you for including this paper in the program. I'm Sung Hong from University of Pittsburgh. Today I'm going to talk about green industrial policy in a globalized economy. So this paper asks about how green subsidies should be assigned across countries when clean energy equipment are traded. So the renewable energy transition, if you think about it, the key is the renewable energy equipment. You need solar panels, wind turbines to generate electricity. And that gives it two kinds of subsidies. First is the subsidy in manufacturing solar panels, for example. That's an equipment subsidy. It lowers the price of equipment. Think of Inflation Reduction Act, 45X manufacturing credit. The other side of the subsidy is to subsidize the installation of solar panel. That's a deployment subsidy. Thank you. And what it does, it lowers the investment cost of installing solar panel in your country. Think of the investment tax credit in the Inflation Reduction Act. This similar subsidy can have a very different implications when we think about the geography of this too. So equipment subsidy can be implemented in a country that produces solar panel, and the country that produces solar panel and the country that installs solar panel can be very different. And the key idea is that while the deployment itself is local and the electricity generated from it is also largely local, equipment is heavily traded across countries, and that gives a very different implications of these two subsidies. And the first thing I'm going to show is that these two geographies are quantitatively very different. So in the left figure, I'm showing you the production and manufacturing and deployment share of solar equipment in each country. So for example, China is accounting for 80% of total solar panel manufacturing, while in terms of deployment, it only takes around 47%. So the remaining part is going to other countries. And who are the main importers? Europe, US and India and all other countries. Especially if you see US, for example, US is producing 2% of global solar panel manufacturing, but now deploying 9%. So 85% of their demand for solar equipment is coming from imported goods. So the geography of production and deployment is very different. And the second fact I'm going to show you is this is a well-known learning curve story. The price of equipment has been falling a lot with the cumulative manufacturing experience. And in the literature, this has been captured by learning by doing. And if you believe that learning by doing is external for some extent, there are some incentives for governments to subsidize the production of it. And on top of that, some of the learning can be reside within countries, some of them can spill over across countries. And combining these two facts, this gives the mechanism of this paper. The subsidies not only affect where the installation happens. It's not only about how much each country is subsidized, but what matters is in which margin is subsidized and which country does it. And another important thing to consider is where each country locates in the trade system in this renewable energy equipment. So this paper asks, how should green subsidies should be assigned across instruments, across deployment subsidy and equipment subsidy, and across countries when renewable equipment is traded and production creates learning. To answer this question, I first build a model and decompose the marginal welfare return per each fiscal dollar, and then quantify the policy rankings in a quantitative, dynamic, multi-region, multi-sector model with energy transition. And the brief result is like this. So first, the global welfare prefers the US, which is the net importing country, to do deployment subsidy, while for China, the global economy prefers China doing equipment subsidy. Why that's the case? Because global welfare prefers the efficient specialization. But if you think about each kind of subsidy, deployment subsidy would increase the demand of solar panels and wind turbines. And US as a net importer, that means the additional demand is met by imported goods who are already good at producing those kind of things. And on the other hand, for China, China's equipment subsidy would increase additional production of solar equipment and wind equipment. And since they're already an efficient producer, this combination of subsidy reinforces the specialization force. But unfortunately, when we think about the unilateral motive of each country, the model suggests that the US would prefer equipment subsidy and China would prefer the deployment subsidy. And the key reason why this is happening is because of the terms of trade and learning effect. So for the US, as a net importer, they would prefer to do equipment subsidy to concentrate the production and harness learning by doing. And also they face positive terms of trade by doing this equipment subsidy. On the other hand, for China, while China can also gain some learning by doing with the equipment subsidy, but as a net exporter, their equipment subsidy would face the negative terms of trade as it reduces the price of equipment once they do the equipment subsidy. On the other hand, since they are already dominating their domestic market, the deployment subsidy day China does it can increase their domestic additional demand, and that demand is met by Chinese goods. So they don't face the negative terms of trade, and at the same time, they can harness learning by doing. So we see this stark difference of the policy assignment when you think about the global welfare and the national welfare. And to highlight the role of equipment trade, I do the same experiment using the model without equipment trade. And what I found is that the US world ranking reverses. So in the model without equipment trade, the model would predict it is better for the US to do equipment subsidy to maximize the global welfare. The key idea is that since we don't have to think about specialization or comparative advantage if there's no trade in equipment, so it's better for the US to do more manufacturing in solar panel and contribute to the global economy by having more learning by doing and maximizing their welfares. And also the second takeaway of the no equipment trade scenario is that since we don't have to think about comparative advantage, China's equipment location advantage also gets smaller. So in the model with trade, I was saying that it's better for China to do equipment subsidy because they are the efficient producers, and they are going to produce solar panels and export to other countries. That speeds up the transition. That's a good thing. But here, without equipment trade, that channel is canceled out. So there's not much point of global planner assigning China to the equipment subsidy here. Okay, so I don't have much empirics, so I'm just going to the model here. So here, think of the multi-country dynamic Eaton and Kortum model with energy transition. So equipment is produced in one country, and then the equipment is traded across countries through Eaton and Kortum framework. So the price of solar panel can be explained by the productivity, trade cost, and unit cost of all other countries here, and then trade elasticity as well. And this Eaton and Kortum framework gives the bilateral trade share as well, how much country N is importing from country I. And then this equipment price, PM, is a key input for the cost of investment in country N. So think of a country N starting to install solar panel. And this investment requires solar panel, PM, and PO, the other goods as well. So this generates the marginal installed capacity cost. And the Euler equation equates the marginal installed cost and the marginal discounted marginal value that governs the investment decision. And then that gives the next period's accumulated capital stock. So the idea is like the traded solar panel can be installed in one country, and that capital accumulation drives the transition to the renewable energy. And here, these two subsidies enter in a different timing here. So the equipment subsidy in origin I reduces the delivered equipment price from country I and spread across to other countries through the trade. So what it does is directly reduces the price of delivered equipment price. And then on the other hand, for the deployment, what deployment subsidy does is that it reduces the effective investment cost in country N. So you can see that in the top equation, the additional subsidy in deployment reduces the cost of the investment. So that increases the investment in each country, in country N. And from the additional investment, it means there is additional demand for equipment. And the additional equipment demand is met by other countries that are exporting to this country country N. So that follows the bilateral trade share. And then there was learning in this model. So the output produced in country I contributes to the cumulative output at a global scale and a local scale. So the idea is like if you produce more solar panel today, the productivity of producing solar panel increases in the next period. So that determines the future equipment cost as well. And here I'm allowing both the local and global learning component here. So the first component of the learning part is the global component. So this captures the global common frontier. And the remaining part, the local component, captures the relative comparative advantage of each country that develops across time. And which one is stronger is governed by the parameter lambda L, which is the local component parameter. And then I'm going to talk about the energy part. Here, the installed solar panel as a capacity that can generate solar electricity. And same thing happens for wind equipment as well. And the generated solar and wind is combined in a CES fashion. And then the renewable energy is again combined with the fossil fuel in a CES fashion again. So there's a nested CES. And that eventually generates local energy, which is an input for production and household consumption. And here, I'm assuming fossil fuel can be traded across countries, but local renewable energy is not tradable. So think of just electricity. While people from Europe would not agree with this, but except Europe, electricity trade is very rare. Only 3% of total electricity is traded across countries. Yeah. So this is a brief diagram of the model. And the full quantitative model includes 15 regions with equipment, fossil fuel, and other goods are traded, and renewable energy is not traded. And production requires labor, non-energy capital, and energy and intermediate goods. So think of the standard input-output linkage models. And then there are market clearing conditions that close the model. Okay, so now I'm gonna decompose the impact of the welfare, impact of the subsidy here. So define R as the marginal welfare gain per fiscal dollar under each objective O. So think of the global welfare or each country's welfare. And the marginal welfare gain can be composed into 3 components. First is the terms of trade instance. Think of like export price change, import price change. And the second component is learning, how much you learn from the additional subsidy. And the last is a carbon emission impact. And regarding learning, as I mentioned before, there's a world experience component and origin component. And here, regarding learning, the reason that location matters is that low-cost origin can generate more real output. Even with the same amount of dollar, China, since they are good at producing it and their labor costs cheaper, so they can produce more solar panels. So that gives more learning compared to US doing the same subsidy. So origins, and in addition to that, the origin-specific learning can reinforce this comparative advantage story. And one thing to mention is that while I have a terms of trade effect in a country-level welfare, if there's a first cooperative world planner, then in terms of global welfare, the terms of trade effect cancels out in the first order. So the first order return would be just learning and carbon emission. So for global economy, what matters is how much learning each subsidy generates and how much carbon emission each country, each subsidy can reduce it. And through the lens of this decomposition, we can think of how each subsidy works. So there are 2 subsidies, deployment and equipment subsidy. And regarding terms of trade effect, deployment subsidy is a demand side shock. So it will increase the price of equipment. So it has it can raise input price and it can favor suppliers over buyers. So that's the first terms of trade effect. And regarding learning, as a demand shock, it increases demand of solar panels, but it doesn't mean that if US does a deployment subsidy, US is going to produce all of the additional demand. It's not the case. It will be the exporting countries who are dominating the US market get more learning. So origin experience follows its sourcing shares. And regarding carbon emissions, deployment subsidy would definitely decrease the fossil emission in their home country because it's going to replace the fossil spending, fossil use. But the problem is that there's a carbon leakage of this story. So first, the standard channel is that as US uses smaller amount of fossil fuel, it's going to motivate other countries to use more fossil fuel because fossil fuel is traded. And the another channel this model has is that with the demand subsidy, the equipment's price is going up, so it will slow down the transition in other countries because equipment gets more expensive. On the other hand, equipment subsidy has a very different implication in terms of 3 channels. Regarding terms of trade, as a supply side subsidy, it reduces the price of equipment, so it benefits foreign buyers instead of the exporters. So exporters will face negative terms of trade effect with this subsidy. Regarding learning, equipment subsidy increases the learning experience of the origin that does that subsidy. And one another consequence of this equipment subsidy is that while it increases additional production of the home country and additional learning for home country, but it has a displacement effect. So since it increases the competition, other countries who are already producing solar panel, they will reduce the production. And so that has a negative learning effect for those countries. And if they are the efficient producers in the original setting, then that would have a negative impact on total learning as well. And lastly, regarding the carbon emissions, equipment subsidy, as it lowers the price of solar panel and wind turbines, it can displace fossil fuel, not only in the home country, but in other countries that buyers source from this home country. So for example, if China does this equipment subsidy, now it can provide cheaper solar panel to all importers, and they speed up the transition to renewable energy, and they reduce carbon emission and so on. So regarding this carbon emission channel, we see very stark difference in terms of which country reduces carbon emission through which subsidy. And then calibration. So basically, we have 15 regions starting from 2022 benchmark. So that's where China was taking 80% of global market share, and US was, I think, 2% of the equipment manufacturing. And I think of the annual transition from 2022 to 2100. I'm not going to highlight all the calibration part, but the one thing that's worth highlighting is the trade elasticity. I set the solar panel trade elasticity to be 5.3 and wind to be 4.3. That's coming from country product level trade elasticity paper published in 2022. And then about learning, I'm not going to talk about how I calibrate this learning parameter. Maybe David has some comments about it. But basically, I first estimate the total learning that governs the total learning rate. And that gives a 27.5% of learning rate for solar and 14.6% of learning rate for wind. So that's quite comparable to the numbers in the literature. And for local components, for solar, I calibrate the local share of learning in solar equipment to be 0.12, meaning that 1/8 of the total learning resides within the country. And for wind, I set this to be 0.5. And then for energy elasticity, the one I like to highlight is the phi equals 3. So that's the elasticity of substitution between renewable and fossil fuel. So that's coming from the literature as well. And the key takeaway of this parameter value is that renewable and fossil fuel are not perfectly substitutable, but not like a complementary goods. And then lastly, about social cost of carbon, I set this to be $210. And that, yeah, this number changes lots of results, but that's the number I set it. Yeah. Okay, so first I'm going to show all the results without carbon emission. The world CEV, policy country CEV, all those numbers are consumption equivalent numbers, so without carbon emission. I'm going to show the carbon emission in a separate table, a separate column. So first here, I'm setting the subsidy amount to be equal to $48 billion in PV, and the policy is for 10 years. This is to match the US equipment subsidy rate to be 30%. That's the roughly the value that 45X manufacturing credit gives to the US equipment in the IRA. And the other values are the corresponding amounts, corresponding rates that give the $48 billion. And first, if you compare the US deployment and US equipment subsidy, we see that world CEV, world welfare, is improving with deployment subsidy of the US, but decreasing with the equipment subsidy. The key idea is like the deployment subsidy, now it generates more learning, and it's generate more learning for the efficient producers through the supply trade linkage. So that gives a more welfare gain for global economy. While the US equipment subsidy gives a negative impact because while it increases domestic production, it reduces the output of other countries who are already good at producing. So it has a negative impact on that side. That explains why the world CEV is negative. On the other end, if you see the Chinese subsidy schemes, Chinese equipment subsidy gives a higher welfare gain compared to deployment subsidy. And the idea is like the Chinese equipment subsidy now provides cheaper solar panel to all other countries, and it also harnesses more learning in a specialized country in producing solar panel. So that gives a more welfare gain compared to deployment subsidy. And then regarding carbon emission benefit, there's this quite clear ranking here. Even with the same amount of budget used for each country and each subsidy, the most efficient subsidy is China's equipment subsidy, which reduces carbon emission the most. And then it's China's deployment subsidy, and then it's US deployment, and then it's US equipment subsidy. And the key idea is like, since China is the more efficient producer, with the same amount of subsidy, they can produce more solar panels and wind turbines, and they can get more learning and reduce carbon emission much more than the US. And within country, equipment subsidy in China is more efficient in the sense that they can provide cheaper solar panel to other countries compared to deployment subsidy, which is to more increase the domestic production than spreading the solar panel to other countries. And we can see a little bit more about how each subsidy works in terms of how it changes the equipment output in home country and other countries, and how it affects the carbon emission in home and other countries. So deployment subsidy, if you compare within deployment subsidy across countries, US deployment subsidy has more impact on additional equipment output in other countries than the US because they aren't producing a lot, so the additional demand is met by imported countries. On the other hand, China's deployment subsidy has more impact on their domestic production compared to other countries' production because China is dominating their domestic market. And regarding the equipment subsidies, US equipment subsidy increases the output of the US, but it reduces the rest of the world output. And the relative displacement ratio compared to China's equipment subsidy is much higher for the US equipment subsidy. So that also drives the negative results of the US equipment subsidy here. And then regarding the carbon emission share, we see deployment subsidies increase the carbon emission in the rest of the world while it reduces the carbon emission in their home country. So that's the carbon leakage story that I just mentioned. And then regarding equipment subsidy, China's equipment subsidy reduces carbon emission in both their home country and the rest of the world, while US equipment subsidy doesn't do that kind of effect because now it's displacing other efficient producer solar panel production. So the rest of the world also sees small increase in carbon emission compared to Chinese equipment subsidy. Up to now, this was all about fixing the budget, and it wasn't about anything about, so what's the unilateral optimal policy? So here I'm showing you the unilateral optimal policy for each country. In the left panel is the US, equipment subsidy in the orange line and deployment subsidy in the green line. The takeaway is that with the equipment subsidy, US can achieve higher welfare gain compared to deployment subsidy. And for China, it's the opposite. So for China, it's the deployment subsidy that maximizes their welfare compared to the equipment subsidy. And the reason was just, as I mentioned before, for China, equipment subsidy has a negative terms of trade effect. If they export more, if they do equipment subsidy, their equipment price for exporting market falls, so that's a negative terms of trade effect. That doesn't happen in deployment subsidy. For the US, deployment subsidy doesn't increase their additional production because all the additional demand is met by imported goods. So there's a very different effect of each subsidy for each country. So for the US, it was equipment subsidy that maximized their welfare, and for China, it was deployment subsidy. So does that maximize the global welfare? So on the right table, I'm showing you the world CEV at the unilateral preferred rate. And the ideal combination for the global economy is the US doing deployment subsidy and China doing the equipment subsidy. And the idea is like this. So yeah. So with the US deployment subsidy, it increased the demand for solar panel. And for China's equipment subsidy, it gives additional production. So this reinforces the specialization force. But the unilateral motive is the opposite. US prefers equipment subsidy and China prefers deployment subsidy. And that gives the worst welfare gain among this 2x2 combination here. And this result, while I'm showing only the consumption equivalent, this result is robust to carbon emission as well, because US deployment and China's equipment subsidy gives the most carbon emission reduction as well. This is the last figure. So to highlight the role of equipment trade, I shut down the equipment trade and do the same experiment. The first takeaway is that the world welfare ranking changes for the US. For the US, for the global economy, it is better for the US to do equipment subsidy now, once we don't consider trading equipment. On the other hand, and at the same time, China's equipment subsidies welfare gain gets smaller if we don't think about trading equipment. And the key idea is not without the equipment trade, we don't have to think about the specialization and comparative advantage forces. So there's no meaning for which country should do equipment subsidy or not. It's just only a matter of like how we increase the learning for each country. And then both countries, it's better for due to equipment subsidy. And then if we don't think about trade in equipment, another takeaway is that China's unilateral optimal policy would be equipment subsidy, not the deployment subsidy, because they don't have to think about negative terms of trade effect. Yeah, since I'm out of time, I'm just putting the takeaways here. I really wanted to highlight the role of equipment trade when you think about the impact of subsidies. Thank you.
Thank you. And discussing the paper is David Himmel.
All right. Well, thank you very much for inviting me to discuss this great paper. So the context for the paper is the big decline in the cost of renewables, particularly solar PV. And this decline in the cost of renewable has come at the same time as China has become a major player, right? And so it's kind of on this graph here, it's pretty shocking. In the early 2000s, China is just not producing any solar panels. And 10 years later, the majority of solar panels in the world are coming from China. And how did that happen? Well, in large part, this is due to the fact that China implemented certain green industrial policies. So on the right, you have this graph from the Ray of Hope paper that shows the number of cities in China implementing different forms of industrial policy. So that's the green industrial policies part in a globalized economy. Why? Because, well, where I produce equipment, solar equipment or wind equipment, and where I use it need not be the same. And so trade in renewable equipment is very important. So with this in the background, what does this paper try to do? Well, it's going to try to evaluate what are the welfare effects, both on consumption and environmental effect of green industrial policies in a global economy. And so it's going to ask questions such as, should countries subsidize consumption of renewable equipment, or should they subsidize production of equipment? Does that depend on the trade position on that country? And does that depend on the objective of the social planner? Am I thinking about the world social planner, or am I just thinking about one national government? And so to do that, what Seungwon does, it builds this like dynamic multi-country trade model, which is quite rich. You have solar equipment and you have wind equipment. These are tradable. They accumulate into a capacity that allows you to then produce electricity. This electricity itself is not tradable. And I think it's a rich and timely framework. It's a timely paper, and it belongs to a broader question of what are really the long-run effects of industrial policies. Okay, so many countries undertake industrial policies. We don't really know very well what are their short-run effects. We know even less what are their long-run effects, and so this is one paper that tries to look at that. So Seungwon spent quite a bit of time explaining the model, so I won't repeat that. I just made a nice graph. So I didn't really make it myself, but that's a nice graph. What are the main results? Well, the main result is that these two types of policies, deployment and equipment subsidies, basically have very different effects, right? So the deployment subsidies end up going along comparative advantage. They're going to boost production in the places that are really good at producing the equipment, while the equipment subsidy, on the other hand, to some extent, try to build some comparative advantage, right? They reduce the cost in a specific way and improve the productivity there through learning. What would the world like? Well, the world would prefer to put then development subsidies in the US because it's an importing market, and equipment subsidies in China, but turns out that each country would rather do exactly the other way around. It's not always so neat. So there's this result that, for instance, at equal fiscal cost, the deployment subsidies are still also better than the equipment subsidies for the US. There's another set of results that I think you do not have the time to present that shows that the IRA end up hurting a little bit consumption for the US, but benefits the world. All right, so my comments are going to be in two parts. So the first two are kind of more, specific to the paper, and the second to try to think a little bit more broadly about the problem. The first thing that I think it would be nice to try to make the results a little bit less of a black box. Of course, it's a little bit, a downside of this type of exercise where you have a very rich model. Then at the same time, when you have a very rich model, it can be a bit hard to figure out exactly what features drives the different results. So there's a theoretical section that you spend some time explaining here that tries to develop some intuition. It, at the moment, doesn't work completely well because it's not totally connected with what you show then in the quantitative section, right? So the same type of decomposition that you show with terms of trade effect, with learning effect, it's not there in the quantitative section. There's a little bit of that, but that's relegated to an appendix. So how to understand what's going on? I think this you explained. So you have these terms of trade effects. These terms of trade effects are important to understand what the national government wants. And in these terms of trade effects, you get that an importer really likes to see a decline in the price of the good that it's going to import. Okay. Well, the US is an importer, so the US is going to benefit from an equipment subsidy because that causes a decline in the price. And on the other hand, it's going to be hurt if it subsidizes deployment because that's going to raise the price. And then for China, which is an exporter, then it's going to be exactly the other way around. So this is part. The subsidy also causes a reduction in emissions. And then that's going to be, what's going to be important is how large this reduction is. That's going to depend on trade linkages. That's going to depend on how much different areas are going to easily substitute with fossil fuels. And then the equipment subsidies are going to favor local learning, while the deployment subsidies are going to favor learning in the places that are important export market for the place that put on the deployment subsidy. Now, this learning is going to have global welfare effects, and these global welfare effects, you can think of them through the lens of Alton's theorem. So we're going to have bigger welfare effects when the increase in productivity affects a sector that is a bigger share of world GDP. Okay, so that's why you want to really boost learning in the countries that are going to produce a lot. Here, spillovers matter because how much of my learning is domestic versus local is going to, explain whether all countries benefit or whether it's only the place that where the learning occurs, where the production occurs, that is an improvement in production. So what I think you could try to do is show how these welfare effects change over time. That could allow you in particular to decompose, really the static effects compared to what happens with the learning, work on decomposing them, and then also trying to shut down some channel. So the key parameters in this paper are really actually these learning parameters. It's because you have the learning in the first place that justifies the production and deployment subsidies. So where do these parameters come from? Well, the wind parameters are to some extent largely assumed. For the solar parameters, total learning is identified from an experience curve, but of course there are many other things going on behind this experience curve. For the local component, there is actually an IV strategy here that comes from feed-in tariffs. So we try to look at the effect of demand shocks. This is nicer, but even that's not completely perfect because, of course, demand shock could also affect other channels such as R&D. Now, to be fair, this is kind of not a nice comment because it's quite a cheap shot. It's very hard to estimate macro learning parameters. So I think you actually do probably the best you can do. But what you could do is to try to see how different should the learning be for you to get very different results? Okay, so I don't think you're going to be able to really estimate that much better, but give a bit more of a sense of, should I need to have completely unrealistic parameters in order to see very different results or not? You could also think a little bit more about whether some channels that may be confounding the learning, so R&D, for instance, would have similar economics, and part of it would be similar, but also part of it may be quite different. You would have a role for different type of policies, for instance. Now, one question that I'm particularly interested in, and I think this paper can look at as well, is where the countries can build comparative advantages. So in fact, in the previous version, I got to see a few versions. In the previous version of the paper, you spent a little bit more time looking at the IRA, and the previous version showed that the IRA allowed the US to temporarily build up some market share. But this effect was very much temporary, and then it disappeared over time. And so I was kind of trying to understand how much this is a feature of your model or your parameters and what's going on there. So I looked at this in a simplified setting. And in that simplified setting, you can characterize when is it the case that the model is going to have a unique stable steady state. That is, when is it the case that regardless of initial conditions, the economy is eventually going to converge to the same outcome. And that's the case when the elasticity of relative market shares with respect to relative experience share is less than 1, which if you look at the parameters of your model would correspond to, so this is the total learning to the right, then the local component, and then an adjustment that depends on the trade elasticity. And then if I plug in your numbers, I get that, well, we are way below 1. Okay, so indeed this economy seems to have, at least in the simplified thing, but I think it would be true, seems to have a unique steady state, which means that whatever policies you do, you're going to end up in the same place. Okay, so in particular, it would suggest that the Chinese industrial policy actually maybe accelerated the transition of having the production moving up to China, but did not really generate it. It was bound to happen anyway. And so you could wonder whether that's realistic or not, or whether we should think that maybe some of these parameters underestimate the true extent of learning, or maybe there are other factors such as R&D and architectural change that also push in the same direction and therefore can generate more of this multiplicity. And I'm out of time, so I'll stop here.
Thanks so much. Again, we'll have someone respond and if folks want to line up for questions.
Okay, thanks, David, for your thoughtful comments. I agree for all the comments you gave. Just to respond of some of it. Yeah, so I should work more on writing a better model part, theory part. And yes, I think I should work on decomposing the impacts through by shutting down some channels and like how welfare changes across time. I all agree with that. And then regarding learning calibration, yes, I should admit that this is somewhat imperfect in some sense. But one excuse is that the trilemma that most of the renewable energy learning curve studies are, it's hard to decompose the effect of learning, R&D, and static economies of scale. I think that's the trilemma that every people face. And I just chose learning by doing to be the key, the driving force of the model. If I also be able to control R&D and like static economies of scale, then I would guess the learning rate would be a bit lower. And while that wouldn't change the qualitative results, but quantitatively, that will definitely affect the results. Yeah. And then for the simplified setting to see how the comparative advantage can be built or not, I think that's a very interesting question to think about, especially through the lens of my model. Currently, I'm only fixing the timing length of the subsidy to be 10 years. That might be partially why the US cannot become a dominant player even after they shut down the subsidy. If I like allow the subsidy to be like 20 years or 30 years, as China has been doing and has done, there might be a chance for the US to be a dominant player in this model as well. But still, one caveat is that the unit cost of production was already not that expensive in China when they started to do the industrial policy compared to top producing countries during that period in solar panels. But now, like Chinese solar panels are around like 40% cheaper compared to US solar panels. So that's the price gap we have to keep in mind when you think about whether US can be a dominant player and whether it's worth spending that money to be a dominant player to go over the China's dominance. I think that's a different question. Yeah, so I think that's all. Thank you for your comments, and I'll try to adopt as much as I can in the next version of the paper.
Great. And on the sort of conclusion of the paper, just this subsidies for equipment, I worry it's a little bit circular. You're inferring from China's large market share and low prices that costs are also low. But there's a lot of subsidies already baked in. So you use that to suggest the government ought to offer equipment subsidies, but there's already massive subsidies on R&D and capital and other elements. And it's hard to read the tea leaves from outside, but it looks like a lot of the companies in the sector, especially upstream, are barely breaking even or maybe losing money. So there's no policy that's called as China equipment subsidy, but it may already be there and driving the inference that you're making from the data today. So I worry about a little of circularity in the logic to then suggest we should subsidize further because the government is already subsidizing, which allowed them to capture this large market share. And then just separately on the equipment, I understand a lot of the cost advantage actually comes upstream. The cost of refined polysilicon in China, just the mining output is like 1/3 the international price. And so I think that it's less likely that a lot of that cost dominance is coming from learning an environment where it's not actually in the downstream PV manufacturing, as opposed to sort of economies of scale in mining or subsidies to the mining sector upstream, which are then prevented from passing to foreign producers through export controls.
Yeah. Oh, thank you for the comments. So about the first one, yes, you're right. In my current setting, I don't consider the current China subsidy when I interpret the 80% of dominance of Chinese market share. So Ignacio's paper has studies that kind of thing, like how much China subsidy is in it. And in their model, they use like 15% of ad valorem equipment subsidy in China. So if you believe the numbers, then we can, using the model, trade elasticity in this model. So that will give around like 60% of market share without subsidy. So that will reduce the argument I was making, right? So China's cost efficiency will be relatively smaller compared to the version without subsidy. But still, since China would have around 60% of market share, they will still be a dominant player in this model. So qualitatively, I think the story would hold. And regarding the second comment about vertical integration in China's solar panel supply chain, I think that's definitely true. But what I want to argue, one thing is that, so when I do the regression for learning, I also control the key input price for polysilicon for solar and like steel price for wind. After the learning rate I got is after that part. So that's something that I'm controlling. But still, yes, the price, if we just directly regress the price pattern on cumulative output, then we wouldn't see the effect of polysilicon. Yeah, so that's something we should consider as well. Yeah, thank you.
Really impressive work. Dynamic general equilibrium is not easy at all. And very interesting presentation. I just have one comment about like your assumption or interpretation of learning by doing. So, and this is maybe hard, and your discussion also pointed it out, that do you have any evidence to what extent this cost reduction or learning by doing is happening within firms versus kind of like at the level of the country or industry? And the reason I ask, I know it's hard, but the reason I ask is that like, if it is all within firms and firms, to the extent that firms internalize that, then it means that we don't need any policy for that, right? But if it is like external economies in a dynamic setting, then we need some policy to correct for that.
Yeah, thank you for the comments. So that's one of the hardest questions that I can answer. So basically, I've never seen any in the solar panel and wind turbine industry to estimate the internal learning by doing and differentiate with the external learning by doing. But there's a recent paper in battery that estimate the learning by doing, and it seems it's like 1/4 of the total learning rate is being internalized in the company in a firm level. So I'm not sure whether we can just directly use the number for solar and wind, but since battery also shows a similar patterns of learning comparable to solar, so maybe that's the number we can think about and do some kind of robustness check for that. Yeah. Thank you.
Yeah,
Just a question on the case where you don't have equipment trade in the model, which I realize you're sort of using kind of primarily as a compare contrast. But it looks like you're still finding sort of a preference. I think it was in the direction for equipment subsidies in that case. And I'm wondering where that's coming from. I would have thought that, like say a case where the US, if I produce solar panels in the US and that means I have to install them in the US, they're not traded. I would have thought that the economic incidence of the subsidy would have been the same regardless of who's directly earning it because there's no trade anymore.
Okay, so one of the key difference between deployment subsidy and equipment subsidy is that deployment subsidy reduces the total project cost, while the equipment subsidy reduces the price of solar panel directly. So it hits the learning more directly. Equipment subsidy hits the learning more directly. So in that sense, if that gives the genuine difference between equipment and deployment subsidy, even without trade. And one thing that I'm having here, even under the model without trade, is that I'm keeping the global learning component as well. So by US producing more solar panels directly using the equipment subsidy, it gives more global learning compared to deployment subsidy. So that gives a higher welfare gain for the global economy when US use the equipment subsidy.
Thanks for a great presentation. I'd love to hear more about where the calibration of the elasticities of supply and demand for equipment come from and kind of what the underlying macroeconomic studies are doing. Because that seemed pretty central to the terms of trade force and this key qualitative result that optimal unilateral policy is different for the US and China.
Oh, sorry. So are you asking how do I estimate learning by doing or?
Yeah, where does the elasticity of supply, because all the terms of trade effects depend on how much you immiserate yourself by buying a lot of stuff and putting up the price of equipment and selling a lot and reducing the price of equipment.
Yes. So here one assumption I have is that learning has a log linear relationship. So another aspect of that is that even the big country and small country faces the same elasticity of learning. That's the first thing. And regarding how I estimate it, so what I do is for the country level, local, so there are two aspects. First is about total learning. So what I do, I just regress the price on quantity and controlling price. And then regarding the local share, I'm using the productivity proxy variable on the left-hand side, and then I regress the productivity proxy on the quantity. So that gives the learning rate for each country. And another assumption I'm having is that the learning, local share of learning. And then the assumption is that the learning parameter is same across countries. So that doesn't give the variation here. But here, since what matters is the real output, not the nominal output that drives the learning. So cheaper countries can produce more output given the same amount of subsidy.
Sorry, not to be insistent, but I was not learning, as I think you explained that pretty well. I was curious where the actual just demand curve for equipment comes from.
Oh, so demand curve for equipment, that comes from the investment, all equations. So all equation in each country determines how much you demand for solar panel. And regarding that, so the price of renewable energy drives the decide for each household how much to invest in solar panel and wind turbines, and that's generated within the model where the renewable energy market and fossil fuel market clears and so on. Maybe you can talk a little bit more, but I didn't give a good answer.
No, thanks so much.
I have an unfair question that you can just interpret as old man shaking his fist at clouds, but
go ahead.
So when I think of the policy implications of industrial policy, and I've seen a few of these papers now, it always strikes me that we need to see the examples that didn't work. The Japanese hydrogen cars and the US cellulosic biofuels, and what's the denominator here when we think about the payoffs to industrial policy, because it's not just the cases that worked, it's the ones, where we bet on the wrong industries as well. And I think in your context, it may be just that the learning never happens or something, but we might just learn how to do something that no one actually wants. And so, I guess for just all of us in the room, how do we think about this in terms of what the actual kind of implications of industrial policy are? Because there's roads not taken that, that are just inherently not present when we study one specific case. And I almost always see papers on the successful ones. And I'd really like to see a paper on a just absolute failure industrial policy, I guess, at some point. So.
Okay. So my result, I'm not sure how I should interpret my result in that sense, because if you see the numbers I'm showing you, all of the numbers are very small, while most of them are positive. While that's partially because the GDP share of renewable energy equipment itself is so small. So think about Hulten's theorem, then the welfare implication would be also very small. But the question I wanted to ask more fundamentally is that, can we actually reduce carbon emission in a serious amount if we do green industrial policy rather than using carbon tax? And the numbers I'm showing you says, actually, it's quite hard to do that. In that sense, the idea of the green industrial policy might be actually just an industrial policy with a green mask. In that sense, while I'm not going to call this as a failure of this green industrial policy, but most of the motives that drive the green industrial policy is more industrial policy than green. I think that's something that I can convey with this results here. Yeah.
All right, thank you so much. And we now have a break until 3:50.
Thank you.
Oh, is it emphasis on the first sub?
Is there? Yeah.
All right, welcome back, everyone. So for our last talk of the day, we're very pleased to have Keisuke Ito presenting on the competitive effects of vertical integration.
Thank you for including our paper in the program. I'm going to present the competitive effects of vertical integration under incomplete hedging. This is joint work with Ali Hotats and Eric Richard. So risk allocation is a key problem in market design. In many commodity markets, price and quantity fluctuate, and someone must bear the risk. As you all know, the natural gas price spike after the Russia-Ukraine war starts, and agricultural commodity price swing with the climate risk. In particular, electricity price fluctuate very sharply. So this figure shows Texas electricity price. Despite the price spike to the $10,000 per megawatt hour, which is a few hundred times higher than the usual price. So electricity price is very volatile. And this happens because of the winter storm. So extreme weather event creates this kind of price spike. And the electricity prices becoming more volatile recent years because of the climate change and also the renewable entries. And these high price risks could be amplified because of the market power, particularly when the market is very tight. This has big implication in the economy. So as you all know, in the Texas and California electricity crisis, the extreme spot prices bankrupted the retail companies. And crises like these prompted the regulators and economists to think about how market should be designed. And they make choices about forward and retail market regulations, and also about whether to permit vertical integrations. It's these choices that ultimately affects market outcomes and who should bear the risk. In electricity, the forward contracts are usually used to hedge these kind of market risk. But forward contracts do not just manage the risk, it also affects many market outcomes, including the market power. The effects of the forward contracts depends on the market structure. What we want to argue in this paper is the effects of the forward contracts hinges on vertical integrations. So who bear the risk affects market outcomes through vertical linkage. Let me talk about the forward contracts. So most deregulated markets in Europe, North America, and Asia, although not in Latin America, have financial forward markets. And economists widely view the forward contract as pro-competitive in the spot electricity market. The key intuition is the forward contracts fix the price on most output in advance, so the firms gain less from the higher spot prices. They compete to sell more. Vertical integration in our context is generation and retail integration. This is also very common among the dominant firms. Often the majority of top four companies in these countries. And energy economists also view vertical integration as pro-competitive in a spot electricity markets. There is this seminal paper, Bushnell-Mansell Arabia 2008. They focus on this LED regulation period when forward market is still thin. They argue that VI, vertical integration, works as substitute for the financial forward contracts. The key intuition is the following. So generation-only firms benefit from the higher spot prices, but the VI firm also have retail customer on the fixed retail rate. That means they are also the buyers in the spot electricity market. So for these VI firms, the high spot prices are their retail side, so their incentive to push prices up is weaker.
But we're going to show that the VI and forward interaction could be anti-competitive. So we theoretically and empirically show vertical integration can become anti-competitive when VI farm buy more contracts than expected demand with standard forward contracts. There are many papers related to our projects, but let me highlight 2 papers. So in the vertical integration in electricity market, Bushnell, Mansa, Sarabia empirically show vertical integration is pro-competitive. And in complete hedging literature, Borenstein applied McKinnon 1967 paper's theory to the electricity market, and he shows that risk-averse buyer optimally hedge more than expected demand. And we're going to show these 2 forces interact to make vertical integration anti-competitive. Let me mention one more paper, the Gans and Wallach. They also show that vertical integration could be anti-competitive. But their mechanism is different from us, like they use this forward market illiquidity that makes VI farm anti-competitive. Okay. Now let me briefly walk you through some simple institutional details. So this is showing the very simplified version of the spot electricity market. So there are generators. They generate electricity and then submit the supply curve to the central electricity market. And then these retail companies submit the demand curve, and then system operator intersect this supply and demand curve to determine spot electricity market price. Generator, they sell Q and receive PS, the price, spot price PS, and then they pay production costs. So they benefit from the higher spot prices. And the retail company buy QR, their retail demand, from the spot market. They pay this PS, spot price. And then they receive this retail revenue, PR, and QR. So they benefit from lower wholesale spot prices. Markup is proportional to the inframarginal quantity, so the production minus the vertical integration farm is a combination between the generation and the retail in our context. So they're the seller at the same time they're a buyer. So their inframarginal quantity is, so the sale quantity Q, production, minus their purchase quantity QR. So because of this QR, purchase quantity, VI farm have less incentive to raise spot prices. That's why they're pro-competitive. But today, the farms actively choose forward position, so financial forward position. The fixed quantity swap contract is the most dominant contracts in the financial market. The swap contracts pays this cash payment. So this is the payoff from the forward contracts. So the PF, which is contract price, minus spot price, which is uncertain spot price, times contract quantity. So this is kind of like the betting on whether the price becomes higher than contract price or not. And the 2 key incentive drives these forward contracting. One is risk hedging, so usual risk hedging to stabilize your profit, and then strategic commitment. This is found by the Alasville 1993 paper. They show that even risk neutral producer wants to use forward contracts to gain Stackelberg leader effects. Generator usually sell the swap contracts, so they take positive position. And retailer usually buy the swap. That means they take negative position. The generator usually sell the swap, so like the forward payoff rises when the spot prices falls. So this is like the opposite incentive to their physical market incentive. So they gain more when the spot price is higher, but they take opposite position in the financial market to do risk hedging here. Okay? So the vertical integration is a combination between this generator and the retailer. So the net incentive is unclear. So the concrete question we want to ask is like, how do endogenous forward position change the competitive effects of vertical integration? Okay, so let me show you some like intuition of our theory section. So first, I'm going to show why people think the VI and forward contract is pro-competitive. So in the spot market, vertical integrated firm maximize these 3 terms. So the retail payoff, and the spot payoff, and the forward payoff. If you take first order condition, then you can write the markup equals to net spot exposure, which is production minus their purchase quantity minus their forward position times price impact. So the higher purchase quantity or higher sale forward contract leads to lower net spot exposure. That's why lower markup. But like the key question here is what's the equilibrium level of F, forward position, chosen in the first stage? I'm going to show the retail overhedging drives this F for the vertical integrated firms. So this F becomes very small or even becomes very negative. That push net spot exposures up. That leads to the higher markup. And the key economics here is like the incomplete insurance of swap contract is incomplete insurance that leads to the this overhedging incentive. I'm going to show you why this overhedging arises in the next slide. Okay, to isolate this retail overhedging incentive, let me focus on the retail only firm here. And first, like I want to consider the edge case where the retail quantity is known. So now price is uncertain, but retail quantity is known in advance. So to consider a single retail firm who must procure 2,500 megawatt-hour tomorrow at uncertain spot price PS. So this single retailer can buy 2,500 megawatt-hour from the forward contracts at the price $40. Then you pay this like market cost tomorrow, but you receive this like forward payoff. So if you add up 40 times 2,500, it doesn't depend on the spot market price. So for any price scenario, you always pay the same cost. But in reality, electricity market has like uncertain demand. So this shows actual supply curve in electricity market, and then retail demand also fluctuates. So this is like showing the retail demand density. So depending on the realized demand, price can be very low or price can be very high. This convexity of supply curve creates mechanical price and quantity positive correlation. In this situation, so as you can see, the spot price and their retail quantity are positively correlated here. And consider again single retailer who have expected quantity tomorrow equals to 2,500, and they hedge this 2,500 from the forward market. Then in a worst case scenario, so in high demand scenario, you realize the price rises sharply and you realize, oh, I need more power. Then you lock in through the forward contracts, in this case, the 500. You have to buy the amount from the spot market. So you're exposed to the high price precisely when you need more power, okay? That increases like your total costs. That leads to the higher variance. But in this case, if you buy additional 500, in this case, in total 3,000, your expected quantity is 2,500, but you buy additional 500, provides additional insurance against the costly state. So now, like if you buy additional 500, as you can see, unhedged quantity becomes 0. So you can stabilize the variance. So in this case, you can reduce the cost variance by 96% by just buying additional 500. So that's a key intuition. So theoretically, the swap payoff is like a linear contract in P in the price, but your procurement cost is a P times Q. So you're facing a nonlinear uncertainty. And the price and the quantity spike together in electricity markets. So hedging only expected quantity leaves residual quantity exposed to the spot price. That's why you need to buy additional to insure against the costly state. This retail only overhedging incentive applies to the PI farm too. So again, like markup can be written as like price impact times spot exposure. And this is like generation only farm case. So you can consider this is generation arm in the VI farm. But now, because they have the retail arm, they have this retail overhedging time. That push spot exposures up, that leads to the higher markup. This is our theory intuition. Now, to test whether the VI is pro or anti-competitive, we collect the data from Alberta electricity market in Canada. So they have the single hourly real-time uniform price auction, and we have hourly unit level bidding data. And we also have like engineering estimates of marginal costs for each unit. This market is moderately concentrated. So the 3 non-vertically integrated firm, 1 VI firm that has 10% market share on the 20 in generation side and 25% market share in the retail side. So this firm is net buyer. They have, so Alberta has active exchange trading, and the swap is the most dominant contract. So we can calculate the bid price minus marginal cost, which is markup. So the view without the forward market suggests that they're the net buyer. So they purchase more than they sell. So they should have like a lower markup. Or they even mark down their bids. But we found that VI farm put the huge markup compared to other generation only farms. So this figure suggests that we should also think about how the financial market affects their behavior. So this is like the evidence that like the financial market models here. But we don't have their forward position data. So we don't observe the forward position. But like the high markup means little output is hedged. So we can, in a sense, like infer from the markup, but the markup also reflects the cost, market power, and ownership. So we need to isolate the forward channel from these competitive factors. So we borrow the technique from the multi-unit auction literature. So we follow the Regan 2014 and the Frank Wallach 2007 paper. So from observed bids, we can invert each firm's first order condition to recover marginal costs and forward position. The key identification intuition is you can use unit level variation to back out the marginal costs. So some units bid higher, some units bid lower, and we can control for the competitive condition to isolate the marginal costs. And we can use the farm level variation. So financial forward position affects like the farm level incentives. So the short position affects drive the bid price lower, or like long position push the bid price up at the farm level. So we can use this variation to pin down the forward position. We can control for each farm's generation portfolio, expected output, and also residual demand elasticity using multi-unit auction data. This isolates the forward position channel. This is our estimates. So again, the markup is proportional to their net spot exposure. That means the production minus their purchase quantity minus their forward position. That determines their markup. And then we normalize that net spot exposure relative to their expected production. So because the farm is like heterogeneous. And what we found that the VI farm looks like the big net seller. So again, in the physical market, they're a big net buyer, but we found the opposite. That suggests they purchase a lot of contracts and then behave as if they're the big net seller. And the other 3 generation-only farms have around 20% of the net spot exposure. So they hedge about 80%. Okay, so that was the evidence of the overhedging for the VI farm. So again, the overhedging happened because of the contract structure. So the standard forward hedges price for a fixed quantity because of the linear contract. But if you think about it, you can design more complete contracts that index this contract quantity to the percentage of actual realized demand. Because you're facing the P times Q, you can design a contract so that it insures against the P times Q. This solves the overhedging problem because now, like in a worst case scenario, the contract expand and then it provides more insurance, especially in the worst case scenario. This leads to the lower incentive to the raise prices. So using the previous example, previously in the standard contract, you have to commit to the quantity F, but now the F is like the shrink and expand depending on the actual market scenario. So your unhedged quantity becomes 0. Now you can stabilize your costs. So you don't need to overhedge. Actually, in Alberta, they introduced this kind of more complete contract. It's called the load following forward contracts at the end of the 2020. So we estimate the forward position before and after this contract introduced. Here's the estimate. So consistent with our theory, this VI farm's estimated forward position falls sharply once more complete contract become available. So this restores the pro-competitive incentive. As you can see, the VI farm started having around 12% of net spot exposure. So it's like very close to other generation-only farms. Okay, now we have shown that the VI farms overhedge and more complete contracts restore their pro-competitive behavior. Now there are remaining two questions. So how much does this mechanism affect price and welfare? Can separation or more complete contract mitigate these effects? To answer this question, we built this two-stage Kruno model with risk-averse farms. And we use Kara utility. And in stage 1, farms choose forward position. And in stage 2, they choose production decision. We have data on uncertainty and residual demand and cost. And risk aversion parameter are chosen to match the estimated forward position. And we found that VI farm is more risk averse than generation-only farm. And we tried the 4 scenarios. The first, swap plus VI. That's a baseline scenario. So in this scenario, contract is swap contract, so incomplete contracts, and a 3 generation-only farm and a 1 VI farm. So this is baseline, which is close to the Alberta before more complete contract introduced. And the second scenario, we try swap plus gen. So the contract is still swap contract, so incomplete contract. Now we separate VI farm into generation-only farm and retail-only farm. So there are only 4 generation-only farm, 0 VI farm. So this relaxes vertical integration. In the third scenario, we replace swap contracts with more complete contracts, which is load following forward contracts. So in the third scenario, we relaxes incompleteness. And the fourth scenario, first best benchmark, so the farms beat their marginal costs. I'm going to report all results relative to the first best. So this is a competitive effect. So the overhedging raises price by $8.1 per megawatt hour. This is approximately 11% above the first best. Separation of VI reduced the markup by $4, which is about $332 million per year in consumer saving. And complete contracts achieve comparable reduction, $2.8 per megawatt hour. This is about $233 million per year in consumer saving. Here's the welfare effects. So the overhedging generates $46 million per year in deadweight loss. And this is about 3% of total costs. And separation of VI eliminates 85% of that loss, and complete contracts eliminate 75% of that loss. Okay. Finally, this is policy implications. So we show that when VI farms are constrained to incomplete contracts and they cannot pass risk to the final consumers, more complete contracts or splitting VI can mitigate VI farm spot market exposure, spot market power. But this does not imply generators or financial player who sell the contract, more complete contract, should bear the risk in general. Okay, we want to emphasize this point. So the passing risk to the consumer could also discipline the VI farm's market power and also avoid moral hazard problem, for example, using real-time pricing. But in practice, real-time pricing also had other issues. For example, in the Texas crisis period, Greedy, which is real-time pricing retailer, went bankrupt when the spike in prices left consumers unable to pay. So consumer couldn't actually pay, and they couldn't collect these market costs. Okay, so here's the conclusion. So we show that vertical integration can be anti-competitive when hedging contracts are incomplete. So the VI farms overhedge retail demand that leads to higher markup, higher spot exposure and higher markup. This contrasts with the view that vertical integration is pro-competitive. And we used the empirical case study of Alberta electricity markets. We estimate the forward portions, and then we found that VI farms overhedge and bid less competitively. And a more complete contract reduce overhedging and restore competition. The implication is that the contract format is central to understand the competitive effect of vertical integration. Separation of VI or more complete contracts can improve competition and welfare. Thank you.
Thank you very much. And here to discuss the paper is Jim Bushnell.
Okay, thanks. Thanks to the authors and to the organizers for the invitation. This is a favorite topic of mine. I really enjoyed working through the paper. It really challenged my priors. I'm still not sure if it changed my priors, but it definitely was thought-provoking, and I had to, as we'll walk through, I mean, there's definitely new elements here that that I think are really important to consider. And this is the reason this is one of my favorite topics. Just to sort of take a step back, those of you who aren't sort of deep into power markets, the not so secret to this room, not so secret to probably the outside world, the secret sauce of competitive power markets is adequate forward contracting. When we sort of think about the fundamentals of power markets, there are all these reasons why they should be just horribly vulnerable to market power, very low elasticity of demand, all these other things. And yet when we empirically study performance of these markets, California 2001 aside, they are reasonably competitive. We do not see sort of disaster. Your favorite oligopoly model would predict disaster, but it's not what we see in the empirical data. And forward contracts, my own research and lots of other people sort of point to why that is. But the big remaining question is, where do these forward contracts come from? A lot of my work and others is they were regulatorily imposed. And so there's still a lot of research needed on asking the question of what types of policies, regulations, market structures promote a healthy amount of forward contracting, and which types of policies, give us the opposite. And this paper by Lesvia, which is kind of a cult classic within the electricity IO groups, it offers one sort of framework for thinking about this problem. Now, what does this have to do with vertical integration? Keisuke kind of walked through this, but it's worth sort of thinking. If you're used to thinking about grocery stores or gasoline stations, electricity is different. The traditional model you learned in your IO class, it's like there's a wholesale price and maybe there's market power there, and the retailer sees it and marks it up some more, and you get double marginalization and some other bad stuff. In electricity, it's not that way because they commit to the price to the retailer when you sign them up as a subscription sort of service. So at least for a month or maybe more, 6 months, a year, you're fixing the price to your retail customer as an electricity retailer before you know what your actual wholesale costs are of serving them. And so that's what gives the retail relationship a flavor of a forward contract. And that's why in my earlier work with Aaron and Celeste, we sort of thought of this as pro-competitive. What this paper then brings in is another kind of unique aspect of retail arrangements in electricity, which is that they are what's called requirements contracts. And so customers get to consume all they want at the price that they're signed up at, which is also kind of unique. We've spent a lot of time trying to think about other retail settings where the price is set to the retailer before the wholesale price, and like home oil service in the Northeast is kind of one example. Couldn't find many others. The requirements contract is pretty unique, and that is the emphasis of this paper that gives this correlation of quantity risk with price risk that leads to these interesting hedging developments. Okay, you already saw what this paper does. You saw a really good presentation, so I'm just going to go through that. Basically, you saw some of this too. This setting here is Alberta, where there's one vertically integrated company. They got a lot more retail than they do generation. I had 34%, so I'm not sure. Anyways, they got more. And so that means they should want lower prices because they are selling more than they are, or they're buying wholesale more than they're selling. And in our previous work, it's buried in an online appendix, but we did see that net short retailers in like the 2001 period were in fact bidding below their marginal cost and kind of dumping power on the market. We think because they benefited from lower wholesale prices because they were net buyers. So in some settings, people did behave that way. Here, it seems to be the opposite, where what these guys find is that the vertically integrated firm is bidding as if it wants higher prices. which, you know, in a simple sort of approach, if you think the retail is all that's at play here, doesn't seem to make sense. And then this behavior changes in 2021. So you saw a version of this. I'll fill out a few more dots. The dots are what you already saw. That's like the pre-period where you're seeing really the red is the vertically integrated firm and the other colors are the generators. And the squares are the post period after the type of contract changes. And you can see that the dots go down, the squares are below the dots for the vertically integrated firm, meaning that they started behaving more competitively after they switched their type of forward contract procurement. Now, also, they don't behave that much more competitively than the generators in the post period as well. And what really also jumps out here is that the generators behave a lot less competitively when you get to this post period. There is other stuff going on in this market that might actually favor their identification, or it's stuff that makes it a little messier. Now, they mentioned this other paper that studied this market, similar sort of punchline for NMAX is the vertically integrated firm. These guys didn't want to give away names, so sorry. The other paper did. NMAX is this one in the lower corner here, and you can see the higher, this is basically a measure of how high they're bidding above marginal cost on sort of an average. And in the pre-period, they're definitely bidding above, and then it drops down to a lower level in 2021. But what also jumped out to me when I looked at this paper is in 2013 to 2017, they were actually bidding a lot lower even than in 2021. So one question is sort of, I don't know, I didn't know what was going on then, but sort of what was going on then, because they were even more competitive in that pre-period. So the thesis here is that they had this correlated quantity risk because they had requirements contract customers correlated with their price risk. And that led them, because they're buying simple sort of forward hedges that were just fixed quantities. You had to buy a lot of them to try to cover the excess risk of a correlated price and quantity spike. And that made the vertically integrated firm effectively long. And bought so many contracts that it was now more interested in higher prices because it was holding all of this stuff that they bought from other people as well as their own generation. And for a while here, I was thinking, like, why doesn't this affect all retailers? And the reason in the paper is the contracts here are purely financial. So they're shifting kind of the marginal revenue of the firms, but they're not giving it any more structural market power. It's not like they're buying power plants. They're just buying basically futures contracts in electricity prices. And so you still have to have some structural market power for this to actually have an effect on the market prices. And so that means in this setting, then the vertically integrated firm, which has some generation, becomes anti-competitive because interested in higher prices and apparently has some ability to influence it as well. And then the key here is that when they move to these load following contracts, that removes the correlation of the price and quantity and allows them to sort of right size their hedges, and they're no longer over hedging. Although again, they're still like bidding somewhat above their marginal cost. So the policy implications here, vertical integration is harmful because it can turn short gentailers into long gentailers when they have this correlated quantity and price risk. I'm not sure like what happens with long gentailers. They're already covered. We'll get to this, like maybe that's a good place to be actually if you own more generation than retailers. And that the other sort of policy implication was that load following contracts are beneficial, at least in this setting where the vertically integrated firm was short. They had less generation than they had retail. And so a key missing piece here was, you know, load following contracts could be really expensive though. The paper basically assumes they're being purchased at kind of an actuarially fair price. It's the quantity weighted expected price, but there's no kind of insurance premium being charged because it's assumed that this sort of energy is available at kind of a risk neutral, perfectly competitive financial price. I'm not sure that's really true, but it's an empirical question. I think somebody knows the answer of how much these guys paid for the contract. I'm not sure if you guys can find out. Okay, a few other comments. This is jointly estimating with the GMM the marginal cost as well as the contracts. I was used to Polar-Horchatsky, where I thought you had to do one or the other, and I wasn't sure you could do both. But yes, when you make enough structural assumptions, you can kind of nail down both. And the engineering marginal costs are kind of close to the estimated GMM, but kind of far enough away that it makes me wonder what would happen if you just used the engineering marginal cost, what the implied sort of forward contract story that comes out of it would be. As we saw, in order to estimate kind of the risk aversion parameter here, they use a two-stage Cournot model where they plug in the forward positions coming out of a bid equilibrium model. So they're kind of mixing two different oligopoly models. And it made me wonder, what if both stages were Cournot? So if you were estimating forward contracts using Cournot and use that to back out the risk parameters, or alternatively, if you're using a bid response sort of model, a more sophisticated kind of spot model, that changes the impact of the forward contracts on the bidding behavior in the spot market. That'd be a more complicated sort of two-stage model, but it makes me curious as to what would happen. All right, I'm running out of time. So just quickly, they're assuming here that there's kind of infinite supply of financial contracts. So you can buy all the hedges you want. I'm guilty of this too, but it does make me wonder if there should be some kind of adding up of contract positions at some level, where if I'm Goldman Sachs and I'm selling a bunch of electricity contracts, sooner or later, I'm probably going to want to line up some supply to back my position. And so if a lot of people are, even if they're financial intermediaries, are they eventually going to some physical suppliers? And at some place, if the retailers are buying a whole lot of extra contracts, I would think ultimately that means some sellers are selling a lot of contracts as well. And then finally, I think this is the high level question: how do firms get to be here in the first place? The paper estimates that the vertically integrated firm is far more, like 30 times more risk averse than the generation firms. And if it's that risky, they're so risk averse, why did they choose to be in this business then, if it's such a risky business? And I think, one of the things that they get into in the paper, but this is a retail regulated procurement setting where they're serving kind of regulated default customers. And in a way, I think the behavior we're detecting here is sort of what the regulator is letting them get away with. So there's letting them behave as if they're super risk averse, rather than maybe being fundamentally so. And I'm not aware of settings where competitive retailers are actually, covering their positions with these load following contracts. All my experience with them is in sort of settings of regulated procurement. I'm not sure what that means, but I think it means something in terms of kind of trying to think about how we fit these pieces together. All right, so again, I really shed new light on the implications of this requirements retail service and what it does to the risk profile of especially vertically integrated companies. I think the policy competitive implications are kind of context specific. Are they net short? Are they net long? And so forth. And then as Keisuke said, the entity that's best positioned to handle the price quantity risk correlation is the actual one using the electricity. They can always choose not to use the electricity if the price is really high. And so this is another of many sort of examples of why having some exposure to more volatile prices by end users is probably efficiency enhancing. So thank you.
Thanks so much. So Keisuke will respond, and if folks want to line up for questions.
Okay, thank you so much for the very careful and constructive discussion here. I want to mention the Brown and Eckhart, the markup measure. So they actually use different, they don't use the markup measure. They use this withholding measure. So which is the share of the bid offer that are above the market clearing price, but have the marginal cost is above the clearing price. So that is that measure is influenced by where the marginal cost is located. So before 2018, in Alberta, the carbon cost was much lower. So after 2018, the carbon, so before 2018, the marginal cost is much lower. So even quite big markup doesn't flip the market clearing price. So after 2018, the marginal cost curve goes up. So even small, the markup flip that, push the offer cap above the clearing price. Yeah, so it's directly affected where the marginal cost is located. So that's so they use a kind of different measure from the markup. And the second point, why the difference between the GMM and engineering marginal cost, the difference between the engineering marginal cost and GMM estimate. So actually, like this like engineering marginal costs in the we use the engineering marginal cost from the documents about 5 to 15 years ago before the sample period. They use like that document reports the nameplate heat rates, and any changes over time or like any actual deviation from that nameplate heat rate are not reflected in engineering marginal costs. So we don't use the engineering marginal cost for any our estimation or counterfactual. So we prefer our GMM estimates because that's more accurate. And also their heat rate provides only constant marginal cost, but we also estimate the slope of the marginal cost. Yeah, I'm gonna take questions.
Sure. I just want to build on Jim's last point about the vertically integrated utilities being rate regulated. I mean, my understanding is that in rate setting hearings, the revenue that they get from the wholesale market just gets netted off their revenue requirement. So ultimately, they're making money from owning capital and not from engaging in market activities one way or another, because it's just going to get passed on to the ratepayers. Is there some kind of like tunneling going on to an unregulated affiliate? Like who's holding the forward contracts that they're standing to actually make money from these financial transactions? Because if it's part of their regulated business, they should be indifferent to it, no?
Sorry, like your question is about the whether they can pass their cost to the final consumers?
Yeah, that typically, you know, whether their expenses in the retail market or in the wholesale market are high or low is going to be their customer's problem, because ultimately they're going to go to a regulator. They're going to say, okay, here are your costs. Here's what you're allowed to recover. And what they're making in the wholesale market is just getting netted off of that. Like if they have a very good year in the wholesale market, then the prices for retail customers will just be lower subsequently. They're like not the residual claimants to wholesale market revenue. It seems like here they're behaving as if they are, and I'm just wondering, like, do they have a financial trading arm that is not rate regulated that can behave this way, or like, what is their incentive to?
So the so in Alberta, so only a few percentage of the customers are actually have like real time pricing, and most of the retail rates are like in a sense like the fixed retail rates, and then about the 40% of the market share is like the regulated plan, and like the another 60% are like regulated plan in residential and commercial. So in this, even like monthly fixed rates, these like the VI farm are exposed to the spot risk because they cannot like pass these risk, the hourly risk to the final consumers. So I don't think like they can like I don't know how that like violates like their incentive to do overhedging here.
Follow up on it later.
Yeah.
How risk averse are firms substantively, and how does that compare to what might make sense against some external benchmark?
So how the risk aversion affects the results?
What is the magnitude of the risk aversion, and does that magnitude make sense?
Yeah, so we did in appendix, we did the back of envelope calculation of this like risk aversion makes sense. So if you're risk averse, you sacrifice expected profit, but you can reduce your variance using the overhedging. So we mapped that like the reduction in the variance to the interest coverage ratio, which determines their credit rating. That leads to their external financing costs. So we compared that like external financing cost change with their profit sacrifice by the overhedging. And the external financing cost reduction is bigger. So that means like this risk aversion parameter like kind of makes sense, that they want to be the risk averse because they want to gain some benefit in the external financing. So they can reduce the interest rate from their debt volume from the to finance themselves through the debt. with much lower interest rate by reducing their variance.
Oh, two small questions. One is purely technical, which is, does any of this hinge on exactly how firms compete? Like if they competed in Bertrand or Cournot or supply function competition, it seems like it would affect the kind of demand risks that they're exposed to. And second, I mean, since this seems to hinge, and I don't know very little about these markets, but on complete contracts that did not used to exist, but you sort of think would be very valuable to exist and were introduced at some point. Do you know why? Like why that market didn't exist? Is there an issue of describability, or is there like an arbitrage opportunity if you can issue forwards linearly as with these companies? I'd just be curious to know more about that. Thanks.
So in reality, they submit the step function supply curve. So like the actual reality is step supply function equilibrium. So we did in the estimation, we followed that like the multi-unit auction literature and apply the necessary condition at the step bid. And then in the Cournot model, so this is answer to the Jim's question too. But in Cournot, we assume away this step function supply curve.
Okay.
And we assume the Cournot model because of the step supply function equilibrium is very hard to compute in a counterfactual. In an estimation, we can just like use a necessary condition of that.
Okay.
So the full equilibrium is like
Got it.
hard to compute in asymmetric bidders. And second question, why they were able to introduce the load flowing forward contracts. So the first so load flowing forward contract is not common in like many US regions, and one reason could be the because of the accounting treatment, load flowing forward contract creates like earning volatility, and that is not good signal for the shareholders. But this firm is not publicly traded. They finance themselves through the debts, and they don't care much about this like earning volatility, and they wanted to use load flowing forward contracts to hedge the risk, and also the price. They want to price the retail rates more correctly, because the load flowing forward contract theoretically reveal the correct risk compensation.
Cool. Thank
Yeah.
Two questions or comment and a question. So first, you motivated the need to overhedge based on the convexity of the supply function. This is not surprising that it's convex. Just to the point about whether you use the heat rate in the actual marginal cost estimate data from the engineering models. If you are going to be estimating it, you know it's not a linear function, right? The whole reason you have overhedging is because of that convex cost function. And so I encourage you to have a cost function that reflects that in your estimates, that has that convexity as well. And see if you can pin that down a little bit across firms using different characteristics of the different plants that they own. The second point I want to make is with regard to the equilibrium effect of the contracts. So if these firms, if the vertically integrated firm is buying a lot of contracts through, whether it's through third-party financial companies or directly through other generators, you think it's going to feed back to the other firms in the market. And so the question is, what does the counterfactual look like? If they're not allowed to hedge at all, do these financial contracts actually change the net positions of all the other firms in the market? Do they actually become more net sellers as a result of removing these contracts, and it becomes even less competitive? And so just food for thought on what is the overall effect of it.
Okay. So the first point, we actually use a convex marginal costs. So like so that's the answer. And for the second question, so in about 40 or 50% of the participants in the financial market are the financial players. So if you think about like Bessem Binder and Lemon's paper intuition, let's say like there is no financial player. Let's start from there. And then if the firms overhedge, there is the price wedge between the contract price and expected swap price. So the contract price becomes higher. And then, So that's a Vincent Banda and the Lemon's like central kind of the theme. And then now if we introduce financial players, they try to profit from this wedge. So they take the short positions in the contract market that eliminates that price wedge. So in a sense, like financial players are the key, the players that add the liquidity to the financial market. And then actually the AWADA allow the financial players trade. So, and they account for 50%. And then also we don't see when the VI firm overheads, and then after the more complete contract, they start bidding competitively, and then they started reducing their long positions. But the other firm didn't change that much. So that's the, I think, answer. The financial player add the liquidity, and then we don't see the generator change their forward position much.
So I'm going to encourage you now to think not just about something Jim said, but now what Aaron said, which is to think more or to sort of explain more about what you have in mind in terms of the counterparty in the hedge. So I think the assumption is that you can buy these load following contracts at the same forward price as the fixed contracts. And that seems like a more risky contract. And so I, with Jim, wonder why that's not something that's more expensive. And so to think about both and then also the question of sort of who the quantity is and you know, modeling sort of where that quantity is going to come from, but especially the price risk.
Okay, yeah. So this private of last resort contract or load following kind of contract is unpopular in the US. Mainly because I think often the retail rate, especially the risk compensation part, is like contested between the regulators and the retailers. And then if the regulator can have like the more bargaining power, and then they can reduce that like risk compensation, which becomes the cost to the retailer side. But in a sense, the load forward contract can reveal that like the actual risk compensation part that push the retail rate up. So, but that's like justifiable price increase for the retail rates. But the next question is like when you procure the load forward contract, the hold auctions, and then if there is the lack of the participants, which leads to the weaker competition in the auction, that could increase the price, which is not justifiable. So the information rent creates like higher load forward contract price. But I think that's an open question. And actually in Alberta, there's like 40 or 50% of the market participants are financial players in these load forward contract auction. So I think they have like enough liquidity there. Like they have like enough participants here. But the information rate part is open question, I think.
Yeah, just a quick question about what the typical maturity is of these forward contracts and whether the kind of anti-competitive effects will scale with maturity. If it kind of, it matters if it's a day or if it's 2 years. Yeah.
So I think it's typically like the monthly, but like it tracks all your realized quantity. And then usually like when they do the load forward contract auction, they sell like, they make the strip of the percentage of the realized quantity for each month. And then for every hour that track their realized quantity. So every month, but it tracks every hour's their quantity and the price.
All right, thank you. Right on time. So thanks so much again to Keisuke and also the other presenters and discussants. We'd like to remind everyone that we start tomorrow morning again at 9 a.m. and breakfast will be served starting at 8:30. Thanks.